Jedan, 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 dva. Tu, 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 tu. Jedan, dva, tri, četiri. Četiri, pet, šest, sedam. Sedam, sedam, sedam. Daj da vidimo. Delay je 5 sekundi.
Sigurno. Kad nema.
Daj da vidimo.
Ok, ko kuća.
Da li je bilo zaista moguće? I ajdemo mjeriti kada će zvuk doći. Hrvoje, zapeli ste na ravnom. Ali strašna latencija.
Je, ali to je samo to je samo YouTube. Aj sad ću čekaj da vidim kako je ti imaš mobitel koji nije logiran na Zoom, ne se automatski logiran. Dakle, ne tvori please samo.
Vidi na jedinicu. Dobar vam dan i dobrodošli na Govori. Sad se čuje. Čuje se, čuje se. Do. Da li je? Dakle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ti si mali crni pesek. Zeka peka. Guantanamera, Guantanamera. Guantanamera. Tu. Da li je?
Da, čini mi se. Ja, muzika nam nije dao, samo nam je dao. A može dodati to?
Hej, jeste li zaista, krenite i nemojte nikada stati. Dobrodošli. Da li je zaista Simpozij o inženjerskoj geodeziji SIG 2024. od 12. do 14. rujna. Zagreb, Hrvatska, 11. rujna, srijeda. Koktel dobrodošlice. Otvorenje. Pozvano predavanje. Da li? That's it. Ok, govorimo. Da, govorimo.
Povrat. Svijet? A, tu svijet. Spajavi spoj.
Gospod ministar, spasili se, ne hvala. Vi ste dobar čovjek.
Ovo bi krasno kad mogu. Ima je ovo ne vrem što takvi. Nemam pojma ko je to takvi.
1, 2, 3, 4, 5, 6, 7.
Znači onaj jedan, sad još je ostao problem što jedno predavanje nam je online. Znači trebali bi ga uskupiti. Jer će nam neke Poljakinje preko Zuma pričati.
To nije...
Ovo je sve vreme upati. Daj mi samo.
Daj se prije ono kao ugasiš. Ovdje još na mikrofon govori, kako bi otprilike govori. Ja sam na 85, da si hedromal stavim.
Ovako bi govorio, ali to sad prejako ti letim van. Dobar dan. Bla, 1, 2, 3. Jel me čuješ?
Čujem te.
A ako se neko nagne ovako, onda ti izleti van. Ali ne bi smio to raditi, mislim. Stojiš i pričaš. Aj sad ugasi. Možeš samo 2 sekunde mikrofon. Samo da vidimo da li radi, da li skače. Čujemo se.
1, 2, 3, 4, 5, 6, 7,
Možete
8,
tebi
9,
da
10,
još malo govori, a mene slušaju. Tamo imaš 10 ljudi već.
5, 6, 7. Dobro?
Kad bi govorili po vi, bilo bi super.
Super. Može, kako vi? Da mi možda malo i vokal uhvati, ali ne znam kako će vam gain tu problem raditi. Vjerojatno dosta. Kuću ga na 12. Ovo će vam biti mutno. Uđeš naći uvijek sa zvezde, ruke pismati, nema znati. Ja dobijate tamo? I'm a virgin. When I'll say clear, see my gaze of which I'm certain. I live the life that's full, trickle deep, byway, and more, much more than this. Baby. Šljaka, mislim da se čuje već vanje sada, je spojeno tako da. Ajde, kažem da se čuje vanje tako da. Dakle, čisto malo. Pa da, da ga nije.
Sad ću krenuti sa timom, nakon toga ću imati govor. Ti ćeš doći na red tek nakon što izlistam ovih 17. Onda...
Hoćeš me najaviti? Samo kuću, strane stati. Pa mislim da ću sjesti na taj klub tamo.
Onda imam ponovno nešto predstavljanja i kad to završim, da ću ti ponovno pozvati za primjer, nakon toga kick-off conference.
Dobro. Ok. Dame i gospodo, dragi naši gosti uzvanici, prije svega dobro jutro vam želim. Evo, nadam se da smo se svi smjestili, pa za početak bih vas sve zamolio da ustanemo za himnu Republike Hrvatske. Hvala vam puno. Evo, možete se ponovno smjestiti još jednom. Želim vam dobro jutro i dobrodošlicu na naš 5. simpozij o inženjerskoj geodeziji SIG 2024. Službeno, evo, startamo jutros. Moje ime je Ermin Preljević. Čast mi i zadovoljstvo ovdje otvoriti zapravo vaše današnje i naredno druženje koje vjerujem da će biti jako korisno, zanimljivo, a nadamo se možda čak i malo zabavno. Pa krenimo službeno, poštovane kolegice i kolege, članovi Hrvatskog geodetskog društva, sudionici našeg simpozija o inženjerskoj geodeziji, još jednom dobrodošli. Sve vas srdačno pozdravljam u ime svoje kao i organizatora konferencije i drago mi je da smo se skupili evo u ovako velikom broju, te sam siguran da će se ugodno provesti i kroz cijelo trajanje konferencije. Za početak trebao bih napomenuti i spomenuti neke od ciljeva društva, koji su recimo između ostalih promicanje etike tehničkog i inženjerskog poziva, promicanje, razvoj i unapređenje geodetske i geoinformatičke struke, a onda možda i najvažniji, najbitniji cilj u cijeloj toj priči je promicanje neprekidnog stručnog usavršavanja svojih članova u sklopu cjeloživotnog obrazovanja. To je jedna dosta važna funkcija, evo zbog toga smo i danas na kraju krajeva ovdje. Društvo kroz svoje djelatnosti tradicionalno organizira u suradnji s domaćim i stranim geodetskim organizacijama znanstvene i stručne skupove poput ovog, predavanja, simpozije, radionice i slično, i izdaje glasilo vlastito, časopis Geodetski list koji spada među 10 najstarijih geodetskih listova na svijetu, što nije mala stvar i evo možemo biti ponosni na to da održavamo takvu jednu ozbiljnu i hvalevrijednu tradiciju. SIG 2024. je 5. simpozij o inženjerskoj geodeziji koji tradicionalno organizira Hrvatsko geodetsko društvo, skraćeno HGD, u suradnji sa Sveučilištem u Zagrebu, Geodetskim fakultetom, te pod pokroviteljstvom Međunarodne udruge geodeta FIG komisije 6. Simpozij također pokriva i glavne teme FIG komisije 6 i njezinih radnih skupina, to jest grupa.
Ovu seriju simpozija HGD je započeo još 2007. godine, tad je održan prvi simpozij, u međuvremenu su onda slijedila iduća 3, tako smo danas došli do ovog 5. jedna lijepa jubilarna okrugla brojkica. Kao i Hrvatski kongres u katastru koji HGD održava još od 1997. godine, i ova konferencija je postala jedna tradicija HGD-a, te od samog svog početka iznimno njeguje međunarodnu komponentu. Drago mi je da danas ovdje imamo predstavnike i kolege i stručnjake iz raznih zemalja. Tu su i iz Slovenije, iz Bosne i Hercegovine, Srbije, Grčke, Austrije, Slovačke, Njemačke, Švicarske i mnogih drugih zemalja. Pa svima vama isto još jednom dobro jutro. Welcome, guten Morgen. Ostale jezike ne znam, oprostit ćete mi to. Simpozij se od početka organizira uz usku suradnju Sveučilišta u Zagrebu, Geodetskog fakulteta, a pod pokroviteljstvom Međunarodne udruge geodeta, kao što sam ranije spomenuo. Tradicionalno tu su nam renomirani stručnjaci kako iz prakse, tako i iz akademske zajednice. Pa za početak, evo, još malo formalnosti prije nego startamo. Dopustite mi da sada pozdravim sve naše uzvanike i goste ove konferencije, pa redom predsjednike županijskih udruga geodeta i članove predsjedništva Hrvatskog geodetskog društva. Hvala vam što ste došli i dobro jutro, dobrodošli, može pljesak. Jasminu Trupković, tajnicu HGD-a. Slobodno ustanite kad vas prozovem, ko u školi smo ovdje sad malo. Ozdren Šukalić, zamjenik predsjednika HGD-a i predsjednika organizacijskog odbora simpozija. Izvanredni profesor dr. znanosti Hrvoje Tomić. Evo ga tu. Profesor dr. Ante Marendić. Profesor dr. Siniša Mastelić Ivića. Profesor dr. Miodrag Rojić. Profesor Thomas Wunderlich. Das war korrekt. Wunderlich ist korrekt. Okay, danke. Profesor Heiner Kuhlmann. On će nam biti i prvi naš speaker ovdje, držat će nam i prvu lekciju danas ovdje. Profesor Alojzije Kopačik. Jesam li to točno? Jesam. Profesor Jan Erdeli. Tu nam je i pročelnik odjela za geodeziju i geomatiku Sveučilišta Sjever, izvanredni profesor doktor znanosti, profesorica doktorica znanosti Danka Markovinović. Darko, profesor. Oprostite, profesore. Tip Feller se podvukao. Tu nam je i predsjednik Hrvatske komore ovlaštenih inženjera geodezije Ivan Kalina. To sam pogodio. Prodekan za međunarodnu suradnju Sveučilišta u Zagrebu, Građevinskog fakulteta, profesor dr. Tomislav Kišiček. Također tu. Pozdravljamo i dekana Geodetskog fakulteta Sveučilišta u Zagrebu, profesor dr. znanosti Mladen Zrinski. I predsjednik HGD-a, profesor dr. znanosti Rinaldo Par. I on je tu. Sad smo se malo i nasmijali, opustili smo se, onda taman je ovo dobra prilika da imamo jedan mali glazbeni intermezzo, pa molim vas sa pljeskom da pozdravite našeg zagrebačkog glazbenika Matej Mudrovčić, koji će nam odsvirati jednu kratku glazbenu skladbu.
So I think the final curtain, my friend, I'll say it clear, I'll state my case, of which I'm certain. I live the life that's full, I've traveled deep in every highway and more, much more than this. I didn't mind way. Regrets, I've had a few, but then again, too few to mention. I did what I had to do,
Saw it through without exemption. I planned each charted course, each careful step along the byway, and more, much more than this, I didn't mind. Yet there were times, I'm sure you knew, where I bit off more than I could chew. But through it all, when there was doubt, I ate it up and spit it out. I faced it all, and I stood tall, and didn't move. I laughed and cried. I had my fill, my share of losing. And now, as tears subside, find it all just so amusing to think I did all that. And may I say, not in a shy way, oh no, not me. I didn't mind. For what's a man? What has he got? If not himself, then he has not to say the thing he truly feels, and not the words of one who knew. The record shows I took the blows and didn't more.
Zahvala našem Mateju. A moje isprike još jednom moraju ići sada gospodinu glavnom ravnatelju Državne geodetske uprave Antoniju Šustiću, jer evo, kako smo imali nekakve korekcije u rasporedu, nisam ga pozdravio, tako da molim vas da pozdravimo i njega jednim velikim pljeskom ovdje koji nam se pridružuje danas. Sad smo ovaj dio službenog programa odradili. Sada pozivam da se prigodnim riječima obrate neki od ovih naših nazočnih predstavnika organizatora konferencije i predstavnici njihovih krovnih organizacija. To je još eto par malih formalnosti koje imamo prije nego službeno krenemo sa današnjim programom. Tako da za početak, evo, zamolit ću profesora Rinalda Para, predsjednika Hrvatskog geodetskog društva i našeg domaćina, da se s nekoliko riječi obrati skupu.
Poštovane kolegice i kolege, dragi svi, ja se na početku ipak moram, kako se zove, malo ispričati, s obzirom da sam nešto bio malo bolovan, tako da imam malo problema s govorom i tako dalje, pa sam doslovce napisao svoj govor i ispričavam se ako neće to zvučati onako kako bi trebalo, ali evo ga, ja ću se potruditi napisati kako to, pročitati kako sam to napisao. Evo, nemojte se ljutiti na početku, ali evo moram se ispričati na početku. Evo ga. Evo, tako da ovako. Poštovani visoki gosti, predsjednice, članovi geodetskih udruga i predavnici institucija, uvažene kolegice i kolege, dragi geodetkinje i geodeti te prijatelji. Sve vas srdačno pozdravljam i želim dobar dan i ugodan boravak u našem Antonović hotelu u Zagrebu na našem Međunarodnoj konferenciji 5. simpoziju o inženjerskoj geodeziji SIG 2024. Iznimna mi je čast i zadovoljstvo danas biti ovdje, ispred svih vas ovdje. Organizacija ovog simpozija inženjerske geodezije je počela prošle godine, 2023. u rujnu prošle godine. Do danas smo ovdje i ponovno se okupili u iznimno velikom broju. Sve ukupno nas ima skoro 400 sudionika, sve ukupno. Od toga malo više od 150 sudionika uživo, iako je danas, kao što vidite, gužva, pada kiša i tako dalje, pa ljudi nisu stigli svi doći, ali pomalo još dolaze, tako da će se popuniti. Hrvatsko geodetsko društvo je 1997. godine organiziralo prvi hrvatski kongres o katastru. Od tada pa do 2022. godine organizirano je ukupno 7 kongresa koji se tradicionalno održava svake 4 godine. Osim kongresa o katastru, društveno održava i razne skupove, među kojima se ističe Simpozij o inženjerskoj geodeziji na kojem smo danas ovdje. Te isto tako tradicionalno dane hrvatskih geodeta. Dani hrvatskih geodeta organizirani su prošle 2023. godine 20. puta. Simpozij o inženjerskoj geodeziji organizirao se prvi puta 2007. godine. Tada smo imali prvi simpozij o inženjerskoj geodeziji, te nakon toga smo imali 4 puta od tada, znači od 2007. 4 puta do ove godine, znači 5. simpozij. Ove godine održava se znači 5. simpozij o inženjerskoj geodeziji SIG 2024. Osim ovih većih događanja, društvo organizira i niz znanstveno-stručnih predavanja svake godine. Uz navedeno, Hrvatsko geodetsko društvo izdaje i svoje glasilo, časopis Geodetski list, koji se kao 100. godište navršilo prošle 2023. godine. Geodetski list izlazi 4 puta godišnje, to svi znate, a počeo je izlaziti prve 1919. godine, a ove godine izlazi 101. godište, znači 2024. Isto tako, prošle 2023. godine Hrvatsko geodetsko društvo je obilježilo 70 godina svoga samostalnog djelovanja od 1953. godine i 144 godine od prvoga strukovnog udruživanja mjernih, znači geodeta na ovom prostoru. Trebam zahvaliti mnogima, iako moram istaknuti da sam okružen jednim malim krugom ljudi, jedne male struke za velike stvari koji su od početka stalno uz mene, koji mi stalno pomažu. Hvala organizacijskom odboru na pripremama simpozija. Zahvaljujem Sveučilištu u Zagrebu, Geodetskom fakultetu i Međunarodnoj udruzi geodeta FIG, znači FIG, komisiji 6 za inženjersku geodeziju. Također moram se zahvaliti svim fakultetima izvan Hrvatske, našim prijateljima i kolegama, te prijateljima. Zahvaljujem se i našim dragim sponzorima i izlagačima geodetske institucije i opreme. Posebno na kraju trebam uputiti vama, autorima, recenzentima i sudionicima zbog kojih se organizirao simpozij o inženjerskoj geodeziji SIG 2024. Jer vaše sudjelovanje govori o prepoznavanju vrijednosti simpozija što jamči njegovu opstojnost i dalje u budućnosti. Zbog zbornik koji ste dobili i predavanje koje ćete slušati za vrijeme trajanja, znači ova 2 dana, simpozij zasigurno će nadopuniti i obogatiti vaše znanje i vještine iz područja inženjerske geodezije, a koji su od iznimne važnosti u cjeloživotnom obrazovanju koje nikada ne prestaje. I na kraju, Hrvatsko geodetsko društvo mora i radi na tome da spaja i ujedinjuje sve dionike struke i sve geodete na jednome mjestu. Odnosno djeluje kao nacionalna organizacija s ciljem koordinacije strukovnih interesa svih geodeta i svih instituta i organizacije na području Republike Hrvatske. Hvala vam svima, te živi, zdravi i veseli bili. Hvala vam svima.
Ja ću samo kratko ovo ovdje pogasiti. Znači, idući ćemo zamoliti zamjenika predsjednika znanstveno-stručnog odbora simpozija, profesora doktora Antu Marendića, da se obrati skupu. Pa, profesore, evo, tu ste, podije je vaš.
Poštovane kolegice i kolege, dragi uzvanici i gosti. U ime znanstveno-stručnog odbora iznimna mi je čast i zadovoljstvo pozdraviti vas na otvorenju 5. simpozija o inženjerskoj geodeziji. Ovaj simpozij koji tradicionalno organizira Hrvatsko geodetsko društvo u suradnji sa Geodetskim fakultetom Sveučilišta u Zagrebu održava se pod pokroviteljstvom Međunarodne udruge geodeta FIG komisije 6. Simpozij koji danas otvaramo ima značajan cilj predstaviti najnovija domaća i međunarodna znanstvena i stručna postignuća iz područja inženjerske geodezije. Ove godine simpozij se održava pod naslovom Inženjerska geodezija, definicije, temeljne kompetencije i jedinstvene značajke, koji je ujedno i tema pozvanog predavanja profesora Kulmana koje će uslijediti nakon otvorenja. U sklopu simpozija očekuje nas 28 zanimljivih prezentacija radova, podijeljenih tematski u 8 tehničkih cjelina, u 3 pozvana predavanja koja će dodatno obogatiti naš program, pružajući uvid u najnovije trendove i tehnologije. Također vas pozivamo da poslušate predavanje našeg generalnog i zlatnih sponzora, kao da i posjetite štandove naših izlagača. Ovim putem želim izraziti zahvalnost članovima znanstvenog odbora za njihov predan rad u recenziranju radova, čime su značajno doprinijeli kvaliteti simpozije. Također, posebno zahvaljujem autorima radova, predavačima, svim sudionicima, sponzorima, recenzentima, članovima organizacijskog odbora, te svima koji su svojim trudom doprinijeli organizaciji ovoga događaja. Na kraju, želim vam uspješan i zanimljiv simpozij, te se nadam da ćete uživati u boravku u Zagrebu i druženju s kolegama i prijateljima. Hvala.
Hvala profesoru Marandiću. Iduće ćemo najaviti i zamoliti zapravo da nam dođe tu na pozornicu, to jest na podij, dekan Geodetskog fakulteta Sveučilišta u Zagrebu, profesor dr. Mladen Zrinski, da se i on obrati skupu.
Poštovani predsjedniče Hrvatskog geodetskog društva profesore Par, poštovani zamjeniče predsjednika Hrvatskog geodetskog društva gospodine Šukaliću, poštovani glavni ravnatelju Državne geodetske uprave gospodine Šustić, poštovana zamjenica glavnog ravnatelja Državne geodetske uprave gospođa Pupačić, poštovani predsjedniče Hrvatske komore ovlaštenih inženjera geodezije gospodine Kalina, poštovani prodekane Građevinskog fakulteta profesore Kišiček, poštovani pročelniče Odjela za geodeziju i geomatiku Sveučilišta u Sjever profesore Markovinović, uvaženi profesori i gosti iz inozemstva, uvaženi profesori i drugi gosti iz Hrvatske, dragi predsjednici udruge geodeta, županijskih udruga geodeta, poštovane kolegice i kolege geodete i dragi studenti. Sve vas srdačno pozdravljam u ime zaposlenika i studenata Geodetskog fakulteta Sveučilišta u Zagrebu i svoje osobno ime. Geodetski fakultet baštini svoju samostalnost od 1962. godine, a visokoškolska ustanova u Republici Hrvatskoj odvija se od 1919. godine kontinuirano do danas. Gdje je Geodetski fakultet Sveučilišta u Zagrebu danas? Geodetski fakultet danas u rujnu 2024. godine upisao je novu generaciju studenata na Geodetski fakultet i to u punom kapacitetu od 115 studenata. U znanstveno-istraživačkom radu Geodetski fakultet ima iznimnu suradnju sa svim sastavnicama geodetske struke u Republici Hrvatskoj. Ja ću ovdje izdvojiti naravno Državnu geodetsku upravu posebno na prvom mjestu. Zašto? Zato što je najveći poslodavac našim bivšim studentima, odnosno magistrima, inženjerima geodezije i geoinformatike. Naravno, suradnja postoji sa privatnim sektorom i sad u interdisciplinarnom smislu sa svim drugim strukama u kojima Geodetski fakultet pronalazi svoje mjesto pod suncem. Također, Geodetski fakultet Sveučilišta u Zagrebu ima dobru suradnju sa međunarodnim institucijama, međunarodnim fakultetima, kroz različite Erasmus projekte i druge znanstveno-istraživačke projekte. Geodetski fakultet je posebno ponosan na svoje alumni, naše bivše studente. Bivši studenti Geodetskog fakulteta danas rade na svim kontinentima kugle zemaljskog. Tamo gdje god kročeva ljudska noga, tamo rade i naši bivši studenti. Naravno, s obzirom da je Geodetski fakultet mali, to su mali brojevi, ali mi se s time ponosimo. Što se tiče ovog simpozija o inženjerskoj geodeziji, simpozij o inženjerskoj geodeziji u 2024. je 5. po redu. Prvi bio tradicionalno počela organizacija od 2007. godine. Geodetski fakultet kao suorganizator ovog simpozija ponosi se sa tradicijom. Velike napore uvijek tome daju naravno Hrvatsko geodetsko društvo je na prvom mjestu, međutim tu su sve predstavnici i geodetskog društva su naši zaposlenici geodetskog fakulteta, profesori, asistenti, odnosno studenti. Ovaj simpozij uz ostale simpozije koje je naveo predsjednik Hrvatskog geodetskog društva ima tradiciju organizacije i nastoji se redovito organizirati svake 4 godine. Svima vama, sudionicima ovoga simpozija, drage kolegice i kolege geodeti i druge srodne struke, želim vam ugodan boravak u Zagrebu ako ste naši gosti, domaćinu želim da bude dobar domaćin, želim da razmijenimo iskustva ova 2 dana i naravno da obratimo pozornost o onome što ne znamo pa probamo svoje znanje nadopuniti. Hvala vam lijepa.
Hvala gospodinu Zrinskom. Iduće onda bih pozvao prodekana Građevinskog fakulteta Sveučilišta u Zagrebu, profesora doktora Tomislava Kišičeka, da se i on obrati skupu.
Poštovane kolegice i kolege, visoki uzvanici, dragi gosti, iznimna mi je čast da vas mogu pozdraviti na ovom skupu u ime dekana Građevinskog fakulteta profesora Domagoja Damjanovića i svoje ime i mogu slobodno reći svih svojih kolega sa fakulteta. Drago mi je da sam ovdje zbog toga što sam sreo mnoge drage prijatelje koji smo nažalost zbog potresa i obnove razdvojeni pa nismo više u istoj zgradi, ali ako ne znate, a vjerojatno znate, vrlo brzo ćemo se naći opet tamo, nadamo se u proljeće negdje početkom ljetnog semestra da ćemo možda čak početi organizirati nastavu u našoj zgradi, te da ćemo se nadam se opet viđati na kavama ujutro i komentirati svakodnevne teme. Neću puno duljiti, mi građevinari smo ne samo zbog toga što smo u istoj zgradi, ali i krenuli smo od iste ustanove, kao što je dekan Zrinski rekao, u uskoj smo vezi sa geodetima i bez vas naša struka ne bi mogla zapravo funkcionirati, jer vi ste oni prvi koji stupate na teren prije nego se možda nešto počne graditi ili i kad se gradi onda i kontrolirate to što se gradi da bi to bilo sve u dimenzijama i u nekakvim tolerancijama kakvim treba biti. Zato vam želim svima uspješan rad, gostima koji su u Zagrebu da upoznaju malo Zagreb, da se ugodno osjećaju i eto, sve najbolje svima i hvala vam puno.
Hvala gospodin Kišiček. Idući bih zamolio evo da nam se, to jest da se meni ovdje gore pridruži predsjednik Hrvatske komore ovlaštenih inženjera geodezije, gospodin Ivan Kalina. Pa evo, podije je vaš.
Dobar dan svima, prije svega nakon najave podije vaš, ja bih trebao zaplesati, ali neću. Dobar dan svima, drage kolegice i kolege, uvaženi gosti, cijenjeni profesori i svi koji ste danas tu s nama. Posebice bih pozdravio, neću puno, ali našeg glavnog ravnatelja Državne geodetske uprave, gospodina Šustića, zatim predsjednika društva u čijoj smo organizaciji danas, mog dragog kolege i prijatelja i asistenta profesora Para, također i dekana Geodetskog fakulteta Zrinskog. Evo, što se tiče samih tema koje ćete danas vidjeti kroz ovaj simpozij, ja se nadam da su sva ta tehnološka i ostala dostignuća kako na polju i umjetne inteligencije i sve to zajedno nama jako dostupno u današnjim vremenima. Ja moram jedino naglasiti da evo mi u Hrvatskoj komori ovlaštenih inženjera geodezije kao osnovni cilj bi bio čuvati ugled, prava i dignitet samog ovlaštenog inženjera geodezije. Stoga vas ja, evo, lijepo ću vas sve pozdraviti, u tom duhu prepustiti i našem organizatoru i zaželiti vam svako dobro.
I sad je jako bitno da za sami kraj ovog dijela programa najavim čovjeka kojeg sam ranije preskočio, vjerujem da mi nije zamjerio, mi smo se već upoznali ove godine na konferenciji prije. Nije bilo namjerno, događa se, nekad se mijenja program, pa eto, malo propustimo, ali evo, sad ćemo mu dati priliku da me prozove i da se obrati vama kratko, pa molim veliki pljesak za glavnog ravnatelja Državne geodetske uprave, gospodin Antonio Šustić.
Skoro mi suza na oko. No, tko radi, taj griješi, naravno, i to je potpuno prirodno, a ja sam čovjek koji baš ne zamjera puno, pa evo, dobar dan prije svega svima. I ono što mi je iznimno zadovoljstvo, pozdraviti vas sve ovdje skupa, prije svega našeg dragog predsjednika Hrvatskog geodetskog društva koji nas evo po 5. puta, dakle ne svih 5 puta, ali ovaj 5. puta pa i 4. nas je ovdje okupio. Jednako tako predsjednika organizacijskog odbora i zamjenika predsjednika Hrvatskog geodetskog društva, gospodina Šukalića, našeg dragog dekana, profesora Zrinskog, prodekana na Građevinskom fakultetu, našeg bivšeg ravnatelja i sadašnjeg pročelnika, profesora Markovinovića, jednako tako moje drage profesore Rojića, profesora emeritusa, gospodina Kapovića, profesora Medaka, našeg dragoga Antu Marendića, sve vas uvažene goste iz inozemstva i oni koji ste svi došli i na kraju evo ga i moju zamjenicu gospođu Pupačić, pročelnice i pročelnike koji su danas područnih ureda za katastar koji su danas ovdje sa nama, načelnike i načelnice i sve vas drage goste, studentice i studente, evo i to smo čuli. I sad pozdravljam vas u ime potpredsjednika Vlade i ministra prostornog uređenja, graditeljstva i državne imovine koji vas pozdravlja, evo ispričava se na nemogućnosti dolaska, do sinoć je zapravo bilo sve potvrđeno, no međutim evo uži kabinet je upravo sada, tako da se ispričava, želi organizatorima i svima vama koji ste ovdje uspješnu konferenciju. Naravno ja vas pozdravljam i u ime Državne geodetske uprave, a i u svoje osobno. Na početku naravno čestitke Hrvatskom geodetskom društvu i Geodetskom fakultetu kao partneru u organizaciji ovoga važnoga simpozija kojeg se održava svake 4. godine, kao i organizacijskom odboru, znanstvenom odboru i svemu onome što je zapravo učinjeno da imamo ovako zapravo odličan simpozij. Pozdravljam naravno i one, nadam se da jesu nazočni, oni koji su putem online platformi zapravo koji nas prate. Ja bih rekao da ovakvi simpoziji zasigurno imaju ulogu u promicanju najviših standarda u području geodetske struke. A vjerujem da kroz različite projekte, inicijative i edukativne programe možemo osigurati da geodetske usluge budu prepoznate kao ključni temelj u razvoju održivih društava. Kako to u životu obično biva, ovaj naš simpozij, ja vjerujem da predsjednik kada je predlagao termin vjerojatno nije znao da će se upravo za vrijeme održavanja našeg simpozija u inženjerskoj geodeziji zapravo sutra u popodnevnim i predvečernim satima zapravo otvoriti jedan velebni projekt koji je evo ga završen u Republici Hrvatskoj, a to je druga cijev tunela Učka, a svi otprilike barem znamo, možda su neki čak i radili, što znači zapravo geodetska struka u probijanju jednoga tunela od samoga projektiranja, mikromreže i svega ostaloga što slijedi da bi se zapravo takva jedna velebna građevina otvorila. Jednako tako moram spomenuti i sljedeći mjesec otvaranje i autoceste do Siska, također ogromnog projekta koji bez nas geodeta vjerojatno ne bi moglo biti. Neću ni spominjati zapravo Pelješki most koji je ovako jedna impozantna građevina, a koju sada nakon što je izgrađena opet u okviru aktivnosti inženjerske geodezije zapravo naši geodeti prate što se događa sa tom građevinom. Ažurni podaci o prostoru postali su temelj današnjeg suvremenog društva. Imaju ključnu ulogu u gotovo svim područjima ljudske djelatnosti. Stoga će Državna geodetska uprava i u sljedećem 4-godišnjem razdoblju nastaviti provoditi aktivnosti usmjerene poboljšanju kvalitete prostornih podataka i registara iz svoje nadležnosti. i dijeljenju prostornih podataka putem mrežnih usluga kako bi se omogućilo građanima, javnom, ali i realnom sektoru dostupnost podataka u realnom vremenu na lak, jednostavan i interoperabilan način. Državni programi zasigurno su put kojim će se osigurati planiranje, financiranje i kontinuitet, te predstavlja snažan okvir koji omogućava visok stupanj efikasne suradnje i koordinacije svih aktivnosti nositelja i sudionika provedbe programa. Državna geodetska uprava, i to znate, ali nije zgorega za ponoviti, pogotovo zbog naših gostiju izvana, da se provodi realizacija višegodišnjeg programa katastarskih izmjera i time se radi zapravo ogroman iskorak koji će poduprijeti razvoj društva i rast gospodarstva. U tom kontekstu želim naglasiti da ažurni i pouzdani katastarski zemljišno-knjižni podaci zasigurno pridonose vladavini prava i osnovna su pretpostavka za kvalitetno i učinkovito funkcioniranje prije svega tržišta nekretnina, te pokretanje investicija i provedbu kapitalnih, razvojnih i infrastrukturnih projekata čime se stvaraju preduvjeti za efikasan gospodarski razvoj, a to je ono na čemu doista ova Vlada teži. Kako bi se unaprijedio sustav izrade i ažuriranja službenih državnih karata svih mjerila, a radi potrebe evidentiranja promjena u prostoru i zahtjeva korisnika za geoprostornim podacima, neophodno je nadograditi postojeće sustave službene državne kartografije s novim funkcionalnostima koje će podržavati postupke digitalne transformacije u prikupljanju, ažuriranju, obradi, upravljanju, kontroli kvalitete, izradi službenih državnih karata. Stoga Državna geodetska uprava je izradila i upravo prema poslovniku Vlade je u postupku donošenja novoga državnog programa, a to je višegodišnji program službene državne kartografije za razdoblje 2025-2034. Vlada Republike Hrvatske stvorila nam je generacijsku priliku, ali prenijela i odgovornost za koju sam uvjeren da smo je u stanju i opravdati, da ćemo učinkovitim postupanjima osigurati provođenje razvojnih politika i strategija s naglaskom na podatke i njihovu kvalitetu kroz kvalitetno pruženu uslugu. Vjerujem da će i na ovome simpoziju da ćemo doći do novih spoznaja, a sve u cilju daljnjeg napretka naše struke. Na kraju doista želim organizatorima, svim predavačima i sudionicima ovoga simpozija da se osjećaju ugodno i vjerujem da će simpozij kao i uvijek biti uspješan. Hvala vam lijepo.
Hvala gospodinu Šustiću, hvala zapravo svima koji su imali lijepe uvodne riječi i želje za sve nas. Prije nego krenemo sa službenim prvim predavanjem dana, još jednom kratko ćemo pozvati našeg glazbenika, našeg dragog Mateja, da nam izvede još jednu glazbenu numeru, pa slobodno njega pozdravite još jednom pljeskom.
Ćeš naći uvijek dom, srce koje kuca za te, ruku da te prati, majku da te shvati, znaćeš sve što treba znati, znaćeš kako boli plać, kada tvoja zemlja pati, ali iznad svega sigurno ćeš znati što ti znači ovaj kraj. To je tvoja zemlja, tu sagradi dom, tu je stari temelj, tu na kršu tvoj, tu čini uvijek i dali su nju, a čovjek tu je sve dok nismo tu. Čini uvijek da li su nju, a još uvijek tu je, sve dok vi ste tu.
Hvala lijepa Mateju na ovoj predivnoj izvedbi stvarno divne pjesme Vice Vukova. Sad je onda vrijeme da zapravo završimo s ovim nekakvim formalnostima i da se primimo, kako se kaže, posla. Ja ću još jednom za start pozdraviti i sve naše goste koji dolaze iz inozemstva. Još jednom na engleskom. Good morning, welcome to Zagreb, welcome to our symposium. We are hoping that you're going to have a really good time here, that you're going to learn something, that you're going to connect with your colleagues here from Croatia or from other parts of the world or Europe. And now it's finally the time to announce our first speaker of the day, our first lecture of the day. Znači, još jednom, zahvale svim gostima, uzvanicima, sudionicima i pozivam evo da se krene s radom. Želim vam svima ugodan boravak, uspješnu konferenciju i rad ovdje kod nas i vrijeme da pozovem profesora Heinera Kuhlmana da počne s predavanjem. Pa profesor Kuhlmann, würden Sie bitte hier, also sozusagen die Bühne gehört Ihnen. Dame i gospodo, molim onda s velikim pljeskom da pozdravite našeg prvog spikera i predavača.
Okay, yeah, thanks for this nice introduction, distinguished guest colleagues. But first of all, I need some help regarding the presentation to start it. Yeah. The laser pointer.
The pointer is here.
Okay. Yep. Yeah. So once again, good morning. It's really a pleasure and an honor for me to give this talk here. So thanks a lot for inviting me. Yeah, I will directly connect my talk to the title of this symposium. So sorry for this self-citation here, but the title of this publication is very, very similar to the title of this of this conference. So this definition of engineering geodesy will guide you through this talk. Not necessary to read it here because I will come to the keywords during the talk, and I structure the talk also with two kinds of fields of application. One is dedicated to infrastructure monitoring. It was already mentioned here in the introductory words. And one is maybe a little bit strange. It's about crop production. And we will see what this means. And I will start with monitoring of infrastructure, and especially with laser scanning, because it's immediately after my talk, the session is about laser scanning. So I will talk about monitoring, and as probably know, we have substantial issues with aging infrastructure. This image here from Norway and from Germany. As you can see, my slides are not that actual because 3 days ago, another bridge in Dresden collapsed suddenly, and luckily nobody died, but substantial issue. And we have trouble with bridges. I don't know how the situation in Croatia is. In Germany, most of them are created in the 50s or 60s, and they're pretty old now, and they're going to fail. And especially the right one here, A45, is very prominent one. It was closed a couple of years ago, and has to be blasted, and reopening will take some years. And if you see here the consequences for the whole region, the remaining traffic goes on other roads, and these roads are destroyed as well in substantial amount. So this is a really critical issue about infrastructure, and the same is for water dams. This is not that many in the world. We have only 60,000, not as much as bridges, but they are getting older as well, and they are in a critical lifetime. And the United Nations stated that it's a real issue. We should take care about this. So this leads automatically to deformation monitoring. What is our task? At least one task of engineering geodesy. And what we would try to do is to make an early warning. Yeah? Before the building collapses, we should detect small geometric changes as indicators for something going wrong. And this means that we have to have a high accuracy because detecting small changes needs millimeter or whatever. And then we have these chain here about deformation analysis. And we know this probably take care about the water level and dams or temperature and going for the results as a geometric output, measuring the deformations. And I will have a quick look on this measurement of deformations. We do it usually with, for instance, with total stations, right? We select some measurement points, as you can see here, and we measure this in 2 or more epochs, and this leads to some differences of discrete points. These discrete points, we have to make a decision. Are these measurement deviations or are these real movements of the object? And this leads to this congruency test here. Don't care about this equation. You can look it up in textbooks, no problem at all. But you can see here what we need. We need these differences, what you have shown here in blue, and we need the uncertainty of these differences described in this covariance matrix. So this is all well known. And now I'll hand over to laser scanning. So if we have laser scanning, we will use this instead of a total station, for instance. Then this has a big advantage. We would like to discover unexpected deformations. And with a total station, we have to select certain points. And how can you select a point where the deformation is unexpected? This is not easy, right? So this is for laser scanning, this is very good because you can cover the whole object with a high spatial resolution. And this means that no selection of individual point is needed anymore. So no decision from the engineer. This is good, but we have to think about some issues. One example here, we measured this water dam twice, and we have here some differences between these 2 epochs indicated by the different colors. So this is the question is this measurement noise? Looking here, some millimeters, centimeter, or is it real deformation? I don't know. I know, but because we know we have experience with this water dam, then we know from total stations that this is blue colors indicates with the with the true deformation derived by total station. But if you have only laser scanning, it is not easy. We have some gross errors, as you can see here. Here, coming from vegetation, most likely. We have some systematics. We have why is these edges here are in green, the rest is in blue. This is coming from the MC2 algorithm for the experts with us, because you have to compare these 2 point clouds. We have some systematics, as you can see here. All of a sudden, there's a change from green to blue. Where does it come from? We know that's come from the instrument, from systematic errors. But so we have to do something, right? We can't use the point cloud and make a difference and that's done. That's not possible. So we have to take care about this. And to go a little bit more deeper inside, once again, coming back to this equation, we need the differences D. They're not easy because we don't have identical points. If you measure with a laser scanner epoch 1 and epoch 2, there are no identical points on the water dam. So we have to take care about this issue. And we need the uncertainty. And the uncertainty in terms of laser scanning are coming from the instrument, coming from the georeferencing, coming from the object properties. This is we don't have this total station. Roughness, angle of incidence, color, reflectance, this all plays a role. And we have an influence of the surface representation. And this is something new we don't have for total station. What does it mean? Going for these surface representation, if we do a comparison from 2 point clouds, we have to introduce some assumption regarding are there curvatures or not, and how flat is the object. And just to compare, we can't compare individual points. Because we don't have identical ones. So we have in a certain area, we have to approximate the surface by some functions, right? So and this are needed to to calculate these differences d and to get an idea about the uncertainty and to highlight this a little bit more. Yeah, let's assume this yellow here is a true surface of an object, and then we can approximate this object by, for instance, B-splines or whatever. Doesn't matter which kind of representation we choose. And if we do it very, very precisely with a high complexity, number of parameters to estimate, we have adjustment problem there, or a little bit not that detailed, then we introduce here in blue an uncertainty of the model, of the introduced model, but we have to introduce it. And this we don't, if you're going back to total station, we don't have this problem because we are marked, we have marked points by prisms or whatever, or targets, and the accuracy of the prism is much higher than the description of the object. So this is new. You have to introduce this new and should think about this. What does it mean for the uncertainty of our calculated differences? I will come to this back later. And the second part I would like to highlight is the calibration of the instrument and the uncertainty introduced. Of course, these differences D should not contain any systematic errors, only random ones. So we'd have to talk about the systematic errors of the instrument in terms of laser scanner, at least panoramic ones. All has contain systematic errors. We have here, refer to Medici, Tomislav here. No, yesterday he's been there. Okay. Ah, here, Tomislav. Okay. This is part of his dissertation project he did in my group. We have some of these systematic errors, and in terms of laser scanning, they are larger than the random ones. And we have a couple of them, according to the literature. We have 18 of these. There are eccentricities and all these things. Yeah. We made some investigations in Bonn regarding the calibration. We developed a special calibration field consisting of 2 stations for a laser scanner, 14 targets, as you can see here. And we measure these 2 stations within 2 phases. And this field here is about 25 to 20 meters and 75.5 meters high. This is especially designed to estimate the 10 of these 18 calibration parameters. And this works pretty well, I think. As you can see here, for example, we measured this stem with a Leica P50 and with the imager. And you can see on the left-hand side, if you don't do any calibration, except from the manufacturer, right? The instruments are right and coming from the manufacturer, and all the deviations are within the specification. Don't get me wrong, the instruments are okay, but you see clearly some systematics here. So in a range of some millimeters, and these systematics are coming from the calibration of the instrument. And if we apply our calibration, then it looks different. So there should be 0 because it was the same point in time. Yeah, so there should be no movement. And so this is clearly better. But if you look here, this is not perfect because you can have still some smaller, but some effects are visible. And where do these effects come from? This has 2 reasons. One reason is the calibration parameter, for instance, this mirror tilt, are changing a long time. And they are mostly changing with temperature in 2 different time frames. We made some investigations here coming from March to August. And if you see here, the outside temperature with respect to the estimated angle of the mirror, then you can see here a clear connection. So this means that the angle here of the mirror is clearly correlated to the outside temperature. And if you do the calibration with temperature A and your real measurement with temperature B, then you have this effect included. And the second time frame is the internal temperature. you can see here, if you do it very, very, very frequently with the scanner, once again for a couple of hours, 270 minutes, here you can see here, there's a clear decline, especially during the warm-up phase. I mean, we can handle this easily. Yeah? If you have to take care about a very, very precise measurement, then you put the scanner on, let's work the scanner for 90 minutes and then start. So, but you have to know this. So this is one reason. So this means that due to this temperature effect, if we know all the temperature effects with respect to the influencing factors in the calibration parameter, then would be fine. Or another option would be we have to do the calibration during the measurement itself, because it's very, very close in time. So the other effect why this is not, there are still some systematics. We only can estimate 10 of these 18 calibration parameters. The remaining 8 are related to the angular encoder. We have 2 angular encoder, one for the vertical axis and one for the horizontal axis, and each of them has 4, meaning the translation in this direction for the vertical one and the inclination with which we so and so. And so this means 8 parameter. And if you have an Leica P50, you don't have to take care about this, because these Leica P50 has 4 reading heads for each circle, and so this is already done by measurement techniques. By ZZF, for instance, has only 1 reading head, as many of the other scanners as well. And so you have to take care of it. But we can't do this on our field. If you look to a comparable field here with 18, the number of targets would not be 14, but more than 100. This is an issue. And this leads us to the option to do the calibration online. Online means a lot of points during the measurement itself, and it's also time-wise very close by, so we have the same temperature and leads to the same calibration parameter. So in this needs, is it possible to identify from 2 points, from two stations with 1 scanner, measuring the object from different location, different incidence angles, and all these things. During your monitoring measurement itself, identify identical points, which needs to somehow feature detectors out of these 3D point clouds. Yeah, you need to identify identical points, and then out of this different configuration, you can estimate the calibration parameter. This is not done yet. we are trying. Yeah? There are several of issues. If you look on the literature for these feature detectors, most of them are related for 2D. They're coming from photogrammetry, computer vision, right? And they are not that much for 3D, but point cloud is 3D. We have to see if it works. And we have, and it's not possible to estimate all 18 calibration parameters, because configuration is not good enough, and the measurement noise is not good enough. So we have to identify first which kind of calibration parameters are sensitive to temperature changes. We don't know the exact. I showed it's one of these, but we have not that much experience about the other ones. So this is what we would like to do, and then we should make a combined estimation of these a priori within our calibration field and the in situ during the measurement itself. So just to give an idea, luckily the German Research Foundation sponsored a large-scale project related to deformation analysis with terrestrial laser scanner. You can see here these 6 points, 7 PhD students, 4 years funding, and I'm the spokesperson, luckily, of this endeavor. And we started last October. Let's wait for 3 to 4 years, then I can show more results. How is it going? So this was the first part, and the second part I come to crop production. Well, this is not a usual topic we have in engineering geodesy, but maybe we should have. Just to give you an idea why crop production is important, we have 2 crises in crop production currently. One is related to the increasing demand of crops. This has to do with the growing world population. Just to see here, from 2010 to 50, we have to produce the same amount of biomass since the beginning of mankind. We are growing fast. And this is not only because we would like to eat something, but we would like to fill this biomass within our tanks or heating the houses and all these things. And we have other changes, especially the dietary habits of the society in the world is changing, and this needs more because. So this is the one thing, increasing demand. And the other thing is, due to these production, we have substantial impact on the environment. There are a few items, but I would highlight one, and this is due to the spraying we do, pesticides and all these things. We have a substantial reduction of biodiversity. For instance, as you can see here in Germany, we lost 75% of the flying insects, and this is true for the world itself. In general, on the worldwide scale, we are losing per decade roughly 9% of the insects. And if you multiply this, since we do it since 50, 60 years, this is a lot. So, and imagine about the role of the insects within the whole chain of things. We are running into trouble there. This is only one issue. So our approach is to reduce this negative impact. Not mainly increasing the yield, but mainly reducing the negative impact. And with this, our PhenoRob approach, clusters of excellence, PhenoRob, robotics, and phenotyping for sustainable crop production, we try to tackle this approach with digital technologies, right? Digital technologies like flying or moving robots, we would call it kinematic multi-sensor systems, right? Some machine learning approaches, and with this data we collected, we can better understand how the plant is reacting, what is this about the soil, what you can see here, some measurements from plants and soils, and putting this into a broader perspective regarding the environment and especially regarding the economy, because it doesn't help if we can do this, you follow this approach in our research station, but for the impact on the worldwide crop production, the farmers worldwide has to do this. So, and to show you more what it's about, the connection to engineering geodesy is, I mean, following the definitions. This is reality capture, this is monitoring, this is staking out, and this is very similar. So build maps of the field of these individual plants, follow these plant growth during time is monitoring or doing something on the field. So get rid of a weed, make fertilizing at a specific spot, not spraying the whole field, but very precisely only the plant who needs, which needs. So this is this is very close in my mind. And once again, if you're looking on a water dam, so we are measuring here, have input parameters like temperature and water level, and the dam is reacting somehow, and we measure the output called deformation and inclination or moving of points with our measurement technique. Yeah, right. This is what we do to detect these critical deformation, and it's very similar in plants. Yeah, if you have a plant here and the input is the genotype, which variety of the plant is it, the environment, meaning weather, rainfall, temperature, soil, wind, and management means fertilizing, plant protection, spraying, these things are. So and then this reacts. You have CO2 and biomass and oxygen is coming out of this as an output variable. So, but the goal is awfully clear different. We know that plants are growing, so they're moving, but we would optimize the production process. So, and to show this, what is this cluster of excellence is about these, it's running for 4 years. We have a certain budget available. Around 50 professors are involved, and Cyril Stachnis and myself, we are trying to guide this team through the whole endeavor. And we have roughly 150 PhD students involved. And of course, this is not only geodesy, right? For sure. I mean, this is, you can see the keywords more from the technical side, but also from the plant side and soil and ecology and economics and so on. This is for sure. But I will stay within this domain for some minutes and starting with some with setting out. One of our tasks in engineering geodesy, right? As you know, and I will apply this concept of setting out for weed control. To get rid of the weed, keep the crops, and get rid of the weed. This is the task. It's needed. Yeah. If you don't do, you will lose around 50% of your yield at least. So because also the weed tries to pick up water and nutrients and light and so and obviously this is an option which is not feasible in a large scale. So this is which is applied with the resulting I explained. So, and I will show you three different approaches. One follows coordinate driven, very, very clear for geodesists what coordinate driven means. I will explain in a minute. And the other one is a little bit different. So what we tried, it was a project, this is more than 10 years old. We tried to seed, in this case, sugar beet, on a specific position. We pre-calculated the position where the sugar beet should grow. Each one of these 90,000 plants per hectare, and try to stake out. So put the seeding pill of the sugar beet on the right position. And if you do so, you can make weed management after this because you know where the plant is. And the rest you can, I will show you. So, and this we did it with a kinematic multi-sensor system, of course, RTK, gyroscope, filter approach. So, and this is a conventional sewing machine. We didn't invent this; we bought it simply. So, and it's not that complicated. If you see here this conventional sewing machine, the purpose is here. These pills are within this bucket, yeah, and you only need to steer to control this motor, and this motor drives this wheel here, and the wheel picks up a pill out of this bucket and delivers is on the bottom, falls down. So you'd only have to make sure that you control these motor accordingly to your position, right? And if you do so, and the plant is growing, then you can measure if the position is right. And so we did. Yeah, we followed this approach and measured with the total station the true plant position. And this is the difference of the true plant position with respect to the pre-calculated position. And you can see here 5 centimeters, maybe the standard deviation will be 2 centimeters, right? Not that bad. And 50% of this 2 centimeters are coming from our sowing process and 50% coming from the growing of the plant because the plant doesn't know that should grow exactly on the position where we put the pill. So that's it. And this is already implemented. You can buy it. It's a Danish company called Farmdreed FT20. And what you can see here, this is the machine, and already the seeding has happened, and now it's the weed control. Yeah, so it's weeding the whole thing and leaves out where the sugar beet grows. Right, this is already on the market. You can buy. Okay, here's something that sound is okay. Okay, this works, and the two following approaches are a little bit different. They are not using the position of the plant, but they are using an image and deciding in real time if on this image is a sugar beet or a plant, a crop, or a weed in real time. As you can see here, this is a machine learning approach, was already mentioned a couple of minutes ago, and it works in real time. We can do this in real time with a conventional machine driving there. So, and then if you know where the weed is, you can kill it. And I'll see here, I'll show you how we have two approaches. This is, first one is selective spraying. We identify with this image the weed and move these sprayer nozzles to the weed and applying some liquid, not spraying the whole field, but only reduces the amount of herbicide substantially. This is one thing, and the other one is still more fancy. If you identify where the weed is, you can use a laser and burn it down, right? And this is a spin-off of our cluster, Escada Technologies. And in reality, it looks like that, still a little bit large, right? And what you can see here, I will show you in a minute what will happen here in these compartments. This looks like that, right? These are here tomatoes. The tomatoes are kept, and you can see in the flashlight, this is a laser trying to hit the stem of the weed, 20 milliseconds time impact, but the laser is 400 watt. So clearly not eye safe. So you can burn a metal plate with it, no problem at all. So, but this is what the current status and what we have. I would share with you these ideas about setting out a little bit new application, but maybe a little bit interesting. So I'm staying within the plants and coming to reality capture. And so we are driving with a robot along these plants and collecting the data coming from images or laser scanner, doesn't matter, right? And then it looks like this. And then we create such kind of point clouds with this. And to give you an idea, the current version looks like this. This is clearly experimental, right? So, and there are a lot of cameras and laser scanners inside. We can do this the same, not on the ground, but with flying, right? With a drone, also with camera or with a rotational laser scanner. So, and what is needed? We need from different crops. We need crop height, biomass, leaf area, leaf inclination. Such kinds of information are needed from the plant scientists for this. And this leads, if you're looking especially here, leaf area, leaf inclination, what does it mean? We create a point cloud of the plant, and out of these point clouds, we have to identify the leaves and then calculate the leaf area, given the noise of the measurement. So this is not easy. To give you some ideas. This is soybean. Well, you can see here the border. Maybe we can calculate the size of the leaf, maybe. If it's going to some cereals, this is wheat. This ear looks more complicated. How to describe the surface? I mean, we usually describe surfaces, and if you take a building, this is comparably easy. This is flat surface, rectangular. So this leads to some more things. We have to think about this. But the good thing is, I come to this later, is the good thing is, if you're talking about georeferencing, we are experts in georeferencing, right? We can use a GNSS receiver, inertial measurement systems, unknown points, or whatever. So, and this, if we do so, we just to show this image here, for these plant phenotyping, there are different wavelengths and so are important. This is multispectral. It's important for plant diseases, for instance. And this is UAV LiDAR. This is the robot I showed. This is a simple RGB image. And what I would like to highlight, this data should be collected and they fit together because we did the georeferencing, and the plant sciences loves this image because they say, okay, we don't know that this is that easy. It's obviously not easy because, but we can do this issue. So this is important for us. And coming back to geodesy a little bit more, what we have seen are these kinematic multi-sensor systems, right? Doesn't matter if you use this for reality capture of a tunnel or a city or plants, right? So, and I would like to spend a few minutes about this quality assessment we have to do. Yeah, obviously every geodesist makes the measurement itself, and explicit or implicit, the uncertainty is always integrated. So we have to know the uncertainty, what we are doing, especially for staking out and for monitoring. This is important. Is it true the position or not? Is it a real movement or whatever? So, and And what we usually do, I apologize, this is the only equation I will show, right? So what we do usually is we are looking on the observations and describe these observations as a covariance matrix and look how these observations are going within our result. And results, this is here a point cloud or whatever. Simple error propagation, as we learned, everybody learned in the study program, right? And what does it mean? To do so, we need the influence, we need the relation between the result and the observations, and we need all observation errors and the corresponding distribution functions. So there's assumption behind, right? So the assumption is usually normally distributed. Theoretically, it's also possible for other distributions, but then we have to think about and look in our textbook as well. So this should be really tough, but at least we have to know the distribution function. So, and what's about this two demands? If you're going for a kinematic multi-sensor system, right? For instance, this is our bus. It looks very similar to all the other buses which are available. They have GNSS and IMU and a rotational laser scanner. And so this is, and when you look on the, you measure here for, could be camera as well, no problem at all. So we measuring here from this laser scanner is a difference in a certain direction. And then we have to take care about the system calibration, meaning that there are different positions. This is the antenna and this is the scanner, and they have different position and orientation, right? And this blue is here the trajectory estimation. We are driving along and know to every point in time the position and the orientation of the vehicle. So, and this leads to the coordinates of the point cloud. And if we now coming back to this error propagation, what we know is all the measurement errors and the distribution function. We did an estimation about all these measurement errors relating to these kinematic multi-sensor system, and it looks like that. No need to see this figure. The main message is there are a lot of influencing factors, yeah, coming from all these GNSS stuff, multipath, etc., coming from the inertial measurement, random walk process, biases in the accelerometers and all these things, and some more. So this is a lot, and our conclusion is the distribution function is unknown. Geodesists tried since Thomas helped me 4 decades to identify the distribution function of GNSS. It's failed up to and especially if you go here for GNSS IMU, there are decisions within the algorithm. If it's the situations like that, do it like this, and if it's different, do it like this. So you can formulate this with an error propagation. And then additional to this, there are some, I call it black box phenomena from the manufacturer. So there are lookup tables in terms if the temperature is 70 degrees, and do it like that, and all these things. It's not possible to handle this issue in an error propagation. So this approach will lead to suboptimal solutions as well. And you could argue, okay, this is a complicated measurement system, but this is true for all the stuff we have as well. We have this for laser scanner, and even for total station we have this. And I don't know, in a modern total stations there are around 10 to 15 temperature sensors. And the manufacturer does something with these sensors. So this is what my message is. We have to rethink not these equation, but the approach. Is it feasible or not? Still feasible. We are trying, probably you noticed in this example from deformation analysis with laser scanner, to try to do it distribution free. Leading to some different mathematical concepts. And we follow in Bonn the approach not to do it theoretically by error propagation, but empirically. Probably it's possible to identify typical quantities we would like to have. Distances, engineering geodesy, typically we have distances, inclinations, curvatures, some of these. Is it possible to identify these amounts? Is it then possible to build a test field representing these quantities. And then we can measure with our measurement demands the test field, going empirically for true deformations. We will see, but maybe that's possible. But the question is, because if you do the measurement on this test field, you do it in a certain environment with certain circumstances, is it possible to transfer these things to your real measurement you need? So this is still unsolved, but we will see. So this is what we are trying to do. Coming back to the definition, right? So what has changed since 2014? Is a reformulation needed or not? Maybe one of the younger ones can do this. So what's clear for me is the three tasks: reality capture, monitoring, and staking out is clearly our task. What has clearly changed is we are measuring surfaces, not that much individual marked points, measuring surfaces from different sensor modalities. So we have to think about surface objective description. This should be introduced in our study programs for sure. I'm convinced about this. I don't have a solution for this, but he should do this. And to give you an idea, some of our examples, if you do these surface description, it's very comparably easy. If you have here a flat surface, this is our test wall where we test our laser scanners, right? It's flat. If you look on this water dam, it's not that easy because you have here maybe these areas here, but they are consisting of individual stones. How to formulate this surface to make a comparison between two epochs with different realizations of the measurement. And even here, as you see here, these edges, and so this is clearly difficult. Different is here, this retaining wall in a harbor, right? This was monitoring of these. I could tell a story again about these retaining walls. It's the same issue with bridges and dams. They're getting older and all, so critical infrastructure. So, and even especially for these plants, this is extremely crucial. So this, I think we need a more a toolbox regarding the object surface representation more than we have today. So the other thing is, as I have shown, the sensor systems are getting more complicated for sure, and maybe new methods for quality assessments are needed, but I'm a little bit uncertain about this. We are trying things, but this will go in the direction. But the good thing is the reference frames, georeferencing are still a unique selling point of our disciplines. So thank you a lot. So I don't know if there are questions allowed or not from my side. Yes, but I'm not. You are the master of the program.
Professor, thank you for a very interesting presentation. Is there any questions from the audience? No?
Ah, you're right.
Thank you, Mr. Kulman, for your
microphone.
Thank you, Mr. Kulman, for your interesting presentation. Ja sam profesor Rojić sa Geodetskog fakulteta Sveučilišta u Zagrebu. Inače, you spoke much more about interdisciplinary work, especially at the project agricultural crops, and further things are much complicated today. We need to work with another professions. Have you detected some knowledge that we don't have today in geodetic education that we need implement in the future in our study programs to keep in line with the changes happening in this time? Thank you.
This is a very, very important questions. within the German Geodetic Society, where you're also belonging to, we discuss this issue a lot. If you remember your own study program, at least from my side, we had these lectures in 7 to 8 of these neighboring disciplines. And all, at least in Germany, and Austria and Switzerland, all these lectures are gone. They are not more in our study program. I don't know how it's in Croatia, but they are not. And the problem is, okay, why is it the case? Okay, this has to do with the number of students and capacity and all, some university stuff, right? So, but in terms of the discipline, the problem is, I mean, what should it be? We are working together with geoscientists, with civil engineers, with computer science, with agriculture scientists, and maybe 7 more. So you can't have a lecture for each of these disciplines. But I think what, at least for what me helped is that we are trained to talk to other disciplines. And this is, it's not necessary, maybe it's not necessary to have a dedicated lecture to this, but our students should be able to think interdisciplinary, and so this, at least this, we have to ensure. So, but what are the right means for this? I'm a little bit uncertain. I hope this answers your question.
Are there any other questions? No? Okay, once more. Thank you,
Okay,
Professor,
thank you.
for presentation. Sada je... Sada po programu imamo pauzu od pola sata, pa nastavljamo sa tehničkom sesijom broj 1 o terestrijskim laserskim skleranjima. Hvala.
Reci nešto. Reci nešto. To je to. Ok. Aha, imam i ove. Ne, to je za publiku. To je za publiku, a? Onda moramo ovaj malo približiti. Aha. Ok. Da, mi ćemo ovdje biti. Ne, samo vidjeti da li na Zoomu me ima. Zvuk, da li dole lijevo skače. Daj, Josip, reci nešto. Da, vidiš ga dole, na.
Ali ti je ovaj crni gore prezentacija.
Jel me čuješ? A neće on biti.
Ali ako se uči na ljude, ne stavi.
Rekao meni prijasno. Za ove da mogu. Okay. Hello. May I ask you to sit down and take your places? Just in the beginning, a few informations. First one in Croatian. Znači, svi oni uživo sudionici koji trebaju slušalice za prijevod možete uzeti na registracijskom stolu. Ok, vidim da neki možda nisu shvatili, prijevod je u oba smjera, tako da ako vam, znači sad će biti nekoliko predavanja na engleskom, možete uzeti slušalice i imat ćete prijevod. Ok, so first one was for the on-site participants and the other is for our online participants. Just a reminder that they cannot ask questions using the mic, but they can write a question in a question and answer the chat box. So we'll do our best to answer the both on-site and online questions. So I think that we can start. So hello everyone. My name is Hrvoje Tomić, and together with my colleague Josip Grižanović, we're going to try to chair this session. Is the technical session number 1, and the name of the session is TLS, or terrestrial laser scanner. We've got a total of 5 presentations and a time slot of 1.5 hours. So one presentation will be held online. Hopefully that everything is going to everything will be all right with the connection. And I'll ask. So our first speaker is already here. So Tomislav Medić, he's going to present a paper named Geomonitoring using a long-range TLS in Swiss Alps. So Tomislav, floor is yours.
Hi, can everyone hear me well? Works, okay. I'll jump directly into the topic. And the mountains are moving, they are falling apart. That's something that they always did, and they will just continue doing. However, in the recent years, days, we have additional problem that we are losing a lot of snow and ice, and it's all over the newspapers. It's happening across the whole Europe, but particularly it's impacting Switzerland. And what's actually happening, or what is relevant for us, is that when we are losing all of this ice, we are losing something that keeps all of the earth and stones anchored at the same place. So while we are losing permafrost, we are actually having much more of the landslides, rockfalls, and similar events. And it's not just that it's happening somewhere remotely in the mountains. In Switzerland, it's actually a real threat that is threatening infrastructure and also some of the villages. And this is a picture of one of the very famous landslides in Switzerland in village of Brienz, where they are considering to remove the whole village and move all of the people around there. So because all of these things are happening, if you Google a little bit Swiss geodetic offices in online, you will see that most of them actually offer geomonitoring as one of their core services. And so there is a response in industry to this crisis or a problem. And they mostly use old-fashioned devices, total stations, GNSS, and it works reasonably well, but it's quite expensive and a little bit dangerous to monitor such areas like landslides. There are some development in the industry. So there are companies in Switzerland that are developing new solutions for geomonitoring. One of the more prominent one is GeoPrevent. They are by now already bought by Leica and Hexagon. They are developing radar-based solutions. So radar is actually, terrestrial radar is quite useful for early warning. In these deformation monitoring scenarios, because it can detect quite small deformations in a really high temporal resolution. So they're developing often some solutions which are, for example, coupled with these traffic lights, and then as soon as they see some movement in the mountains, they kind of block the streets for some periods of time and so on. But it has some limitations, so we can't really easily interpret this data or understand it, and it's not possible to kind of visualize what is actually happening in 3D if you don't have some additional measurements like the ones with the laser scanners and so on. Some of the new solutions that they are also working on are based on the cameras, but these are still kind of being first time implemented well. They are just tracking the velocity of the motion of the land masses in the pixel space, and in order to actually understand what is happening in 3D, they need quite a lot of additional information. So this is kind of all a bit under development, something new in industry that they are trying to implement. And as there is industry response, of course, there is scientific response. Yeah, in academia in Switzerland, there are projects being developed that tackle this geomonitoring problem, and one of them is Alpine Measurement Laboratory, which is a collaboration of ETH and their Federal Office for Environment. and I'll actually show you a little bit what is happening in this project. And in this project focuses on investigating how well we can use satellite-based radar interferometry for geomonitoring, and we are analyzing some use cases of GNSS and TLS. And focus of my group, or group of Professor Andreas Wiese, where I'm a member of, is terrestrial laser scanning. So I'll show you more or less what we are doing with laser scanners in this case. I will show you everything on a case study that is happening in the south of Switzerland in Matter Valley, which is close to famous mountain of Zermatt, if you are aware of it, the Toblerone one. So the region that we are monitoring has approximately 6 square kilometers, and it's on the east part of the valley. What we have there is we have a lot of GNSS stations in place that are kind of used as a ground truth reference for analyzing what we can do with the TLS and with INSAR. These are in-house developed GNSS stations based on U-Blocks technology, having dual frequency receivers, and they can offer us or deliver us positions better than 1 centimeter and some millimeter range on a daily basis. How we are monitoring with TLS, we are actually having a laser scanner on the other side of the valley on one rock face. And how it looks from the laser scanner side, it looks like this. We are using a Regal VZ4000, which can measure up to 4 kilometers distance. And how our monitoring strategy looks like is that we are coming twice a year, every year now for a certain period of time. And we are staying there with our laser scanner for 1 day, and then we are continuously capturing scans in a sequence. So we usually capture like 5 or 6 scans. Each of them takes around 2 hours, and we are mostly capturing them during the night because the systematic influences on our measurements, primarily due to refraction, are much smaller, and our data quality is better. Just to get a feeling, the resolution of the point cloud that we get in the end is around 2 decimeters to half a meter, and this is approximately how the point cloud looks like if it's colored with RGB information from the inbuilt camera. And now I'll try to briefly walk you through the data processing pipeline that we implemented for deformation analysis with TLS. So we generally want to just generate comparison between point clouds of 2 epochs, E1 and E2. And before we do any serious pre-processing, we apply atmospheric corrections because we saw that they can have already significant impact on the accuracy that we can achieve. After these atmospheric corrections is necessary step of registration or alignment of 2 point clouds in the same coordinate system. There we actually investigated quite a lot of different methodologies to check which one works the best, from the classical target-based registration, plane-based, which is very common in urban environments, a lot of different cloud-to-cloud algorithms, and some relatively unestablished, still kind of part of scientific efforts, non-rigid registration algorithms that could absorb some of the systematic effects on the point clouds. And unsurprisingly, so far we noticed that these non-rigid algorithms do work the best, but as they are not really established, so far we are kind of just toying with them and not really using them. As a standard part of our pipeline, we use cloud-to-cloud approach, which is robustified by incorporating both RANZAC and ICP, and it's based on Open3D library in Python, their core implementation. In order to try to kind of improve the results, we played a lot with vegetation removals based on machine learning, deep learning, commercial software, doesn't matter. Most of them work quite well, actually. But what happens is that once we remove all of the trees, then we have a lot of holes, as you can see on the point cloud or the image on the far right. And yeah, and then if we try to use such point clouds for registration or later for deformation monitoring, we have a lot of systematic bias, and the data in the end looks pretty bad. So we kind of decided that as long as we don't really have a good interpolation strategy, vegetation removal, not the smartest idea ever. The most interesting or useful part of our pipeline is actually computing the deformations, or how do we do the deformation estimates. And there we are relying on the algorithm that our very smart colleague from Slovenia, Žan Gojčić, actually developed based on deep learning. What we are doing there is we are picking all the points one by one in both of the point clouds. We are computing the spherical radius around these points. We are cutting out all of the points around them, and we are feeding this information in a deep learning network, which learns to kind of encode how the geometry around each point looks like in order to be able to find the corresponding points. So in the end, we have more or less one-to-one match for almost all points in the point clouds. Then besides that, we are doing some kind of separation of the point cloud into small patches. And then these small patches, together with these matched points, are fed in the second deep learning pipeline, which does a smart outlier removal. And in the end, we have very dense 3D vector fields showing how each point in the point cloud is moving in which directions and with which magnitude. And this is more or less how everything works that we are using. We also played a little bit with the averaging, and we noticed that averaging point clouds after registration, but before deformation monitoring, also helps to improve our measurement quality. That's it. I'll show you now quickly some first results. The displacement map, so the magnitudes of the displacement that we can estimate based on TLS point clouds, you can see here. So we can estimate well the displacements from around several decimeters to several meters. You can see based on these colors, blue, light blue, green, yellow, that it looks pretty reasonable. And the red points are either outliers where we have really sparse point clouds, or some places where the deformations are happening so fast that sometimes these red points are actually indicating for us that we should come with the scanner more frequently in order to be able to correctly quantify the motion. The gray points are below our sensitivity threshold. So that means that if the deformations are smaller than that, we are at the moment not capable of distinguishing it. If we compare the magnitudes that we estimated from the data against ground truth GNSS, we are achieving accuracy, or so difference with GNSS, of around 5 centimeters, which is pretty strong for such long range monitoring observations. And this is what we can currently achieve. So our future efforts will focus on improving the sensitivity so that we can kind of reduce these areas which are currently colored by gray. So we can kind of detect smaller deformations that we currently can. We would like to improve the accuracy to the level of 1 centimeter, because people from industry which are interested in using TLS in their portfolio are marking this as the main benchmark they would like to achieve. And finally, we are playing with some new algorithms that are trying to exploit deep learning stuff with images that can be done right now. So we are either using RGB images that are captured with the scanner, or we are trying to project point clouds into images, do something there, and then project that stuff back. And that's it. These are our related works, and thanks for your attention.
Yes. Thank you for a very interesting presentation. I'm sure that you got a lot of questions. Are there any questions? Is there any question?
Thomas, I have a question regarding the results you showed us. This slide with this blue and yellow and
On to it.
Yes. In which direction are the differences? Is it perpendicular to the surface? Is it in direction to the scanner, or is it within the surface?
So these are the magnitudes of 3D vectors. So they are mostly showing in the direction of the gravity. So these are not like differences that will be computed with N3C2. These are literally having one-to-one point correspondences and then showing differently in space, mostly along the surface normal, along the surface, perpendicular to the surface normal.
Perpendicular.
Yeah.
Mostly, I think.
Yeah,
This is
yeah,
what I assume.
Yeah.
Okay, but this, I mean, probably you should distinguish exactly these components because it would be interesting for the persons who are responsible, right?
Yeah. It's possible, but for nice visualization, we in the end up with just magnitudes in most cases.
Okay, and the red ones are really movements or gross errors because of something?
It's hard to distinguish. So in most cases, there are gross errors, but the high frequency of these gross errors like that usually indicate to us that there is a lot of movement in that particular area. Otherwise, we would have more matches.
Okay.
Yeah.
Yeah, thanks.
Thank you.
Okay. Any other questions? Yeah, to me, it sounds really interesting because it sounds very challenging to set the thresholds.
It is.
Yes, because it's difficult to it's signal to noise ratio. It must be difficult.
It is pretty
right. Okay, so online we all got
Also
some
not-
greetings. So there are no questions. Yes.
All good.
Yeah. So there's no
Thank you,
questions.
John.
Yeah, thank you. Right, so thank you, Tomislav, and going to ask our next presenter is going to be Ela Ključarić, and she has together with Mate Botica, Lovro Klarić, and Vanja Miković, she's going to present a paper titled "The Implementation of Terrestrial Laser Scanning for Bridge Inspection and Reconstruction Purposes." So Ela, please.
Hello. Hi, my name is Ela Ključarić, and today, as my colleague Tomić said, we'll give you a presentation on application of terrestrial laser scanning for bridge inspection and reconstruction purposes, which I made with my colleagues Mate Botica, Lovro Klarić, and Vanja Miković. Thank you. First of all, we wanted to address a problem, which is that heavy traffic and strong environmental conditions can cause some severe damage on bridge structure. So inspection of the condition of a bridge structure is necessary. Although inspection can be done with some traditional surveying methods, we chose alternative approach, which is terrestrial laser scanning, which would be a leading surveying method for collecting spatial data in a fast and precise way. There were two project tasks. First one was to compare a dense point cloud with an ideal beam as design model, and the other one was deformation analysis in relation to flat surfaces. In order to explain why we decided to use laser scanning, on this slide there are some main advantages of the method. So first of all, it is non-contact technique. It's possible to collect spatial data in fast and precise way. It provides direct, fast, and highly detailed 3D measurement of an object, and all the points in the point cloud are set in 3D Cartesian coordinate system. Our study area was a bridge in municipality Dvor na Uni at Sisačko-moslavačka county, and all data was acquired with terrestrial laser scanner Farofocus 3D X330 HDR, and processing has been done in software such as Trimble RealWorks for inspection, Autodesk Revit for modeling, and Autodesk Civil 3D for creation of some additional display. So as I said earlier, first project task was to determine deviation of a point cloud from the ideal surface. So the inspection wasn't done at on the entire bridge, but just on some of its parts. So for example, in this case, we used one of the pillars of the bridge. And so the first step was to extract that pillar from the initial point cloud. Next step was creation of an ideal model of a pillar in Autodesk Revit. Although as designed model usually implies that model is made before the construction. In this case, this wasn't the case. Case like that. We actually created it subsequently from the point cloud, but I would like to say that to highlight that to avoid overfitting of the compared surfaces, we used only the dimensions necessary for setting the scale or defining the mutual relations between of individual elements of the model, and that part was extracted from the point cloud. There were 3 elements that were extracted, 3 values. First one was length of a pillar. Second one was diameter of these rounded edges. And the third one was height of the pillar. And this is this slide represents, in this slide we can see how it looked like when point cloud and ideal model were overlaid. Second project task was floor flatness inspection. So same as in the previous example, first one part of the bridge that was of our interest was extracted from the initial point cloud, and in this case it was upper part of upper structure of the bridge, that is, say, the road. And yes, I would like to say that for this specific example, no additional models, ideal models were made, since floor flatness inspection tool is already exists in software that we use. As for the results, there is in this slide there is an inspection map that represents deviation of the point cloud from the ideal model, and with a color scale, and blues and reds represent where bulges or some dents in relation to ideal reference surface were. And we can see on this scale bar that maximal deviation is around 5 centimeters in absolute units. Here is one example of horizontal slice, which is at around half meter height. And here we wanted to show that cross sections at preferred heights can be given for CAD inspections and layout production. Here is another inspection map that represents deviation of the point cloud from the reference surface. Here, blue represents parts of the road that were under the reference plane surface, and the red part represents parts of the road that were above that reference plane surface. On the scale bar, we can also see that most of the maximal deviation was around 9 centimeters in both directions, and table is also in this table on the left side, on your left side, is also cut and fill volume representation, and area is present, and area of area of the road that is above reference surface and of the road that is below reference surface. So in conclusion, terrestrial laser scanning and its products are far superior in comparison to classic bridge surveying methods. TLS data enables a more detailed insight into the bridge construction with high accuracy. Various inspections and information analysis between model and point cloud are available, and TLS can be combined with photogrammetry data for even more detailed insight. And that's it. Thank you.
Yes, thank you. Interesting results. I've got one question. How many series of measurements did you have?
Just one cloud.
Okay.
One measurement.
Yeah, okay. So, are there any questions?
From your results, it seems to me that your bridge is not in good shape. Was it closed after your report?
What?
Was the bridge closed after your report?
No, this work paper was actually done just for educational service, educational purpose. So I guess it wasn't.
Maybe after this conference.
Maybe, maybe yes.
Any other questions?
Yes, so no online questions also.
Thank you.
So our third speaker will be Maria Elżbieta-Kowalska. So she's from Poland, and she's going to present the paper named "The Selected Aspects of the Use of Point Cloud Expansions on Planes in the Analysis of Deformation of Cylindrical Surfaces." So hopefully we'll manage to.
Hello, do you hear me well? Okay, I can show my view because it's closed by the by you, so I have a little problem. But give me. Do you hear me?
Yes, we can hear you.
Okay. Okay, so in a minute I will. Okay. Okay. Do you see my presentation?
Can you try to share your screen now?
So you don't see my presentation still, yes?
We cannot see it yet.
Okay.
So in the middle, it should be.
Now you see? It's okay?
Oh, great. Yeah, you can proceed.
Okay, so we can start, I think. So good morning, ladies and gentlemen. On behalf of myself and Professor Janina Zaczek-Pepińska, I would like to present you our research work, which we titled Selected Aspect of the Use of Point Cloud Expansion on a Planes in the Analysis of Deformations of Cylindrical Surface. My name is Maria Kowalska. I'm PhD. I work at Warsaw University of Technology at Faculty of Geodesy and Cartography in Poland. I will see me now. I think it will be better. Okay, so first of all, I would like to outline you the need for preparing this type of studies. In engineering geodesy, we measure objects with various geometrics, size, and specification. We often perform work in difficult, unfavorable conditions, while at the same time we are facing with the need to achieve high accuracy, what all speakers before me says. And in this type of work, we most often use laser scanning technology. It can be terrestrial laser scanning technology, mobile, photogrammetry, UFI, all of this type of stuff to measure. And as a result of our measurements, we obtain a quasi-continuous model of the measurement surface object. This model can be an element of the beam system, but in engineering geodesy, primarily it's intended to be used to assess the technical condition of the facility or to do inventory of it. So assessment of the technical condition on a three-dimensional model requires not only specialized software, but also a change of approach to this type of work. So the basic form of studies on point clouds are flat visualization, on which we can perform some measurements in scale. On a three-dimensional model, for example, of a tunnel or an arc, it's difficult to conduct measurements along the tested surface. Therefore, in our research, we proposed the idea of using the plane expansion for a curved surface. So if we have something curved, we propose to do the expansion of it. And in practice and in the literature, the formation analysis based on point cloud for objects with complex geometry are performed in two ways. And first way is to do the vertical or horizontal sections. And they can be done in a different level, in the different points, whenever we want to do this. And the second option is to make a three-dimensional model, which we colored in the accordance with the adopted color scale for the determined deformation values. So these are popular. But as I mentioned, the main problem in assessing a surface condition based on a three-dimensional model is performing any measurements on it. So while we are analyzing a flat surface, the problem seems to be insignificant because we measure from point to point in a line. But when we, for example, want to measure the width or a length of a crack in the arched vault of the church, so we have church vault and we want to measure the length of the crack. So then available measurement tools become a barrier, because we can't measure alone. And that was the point why we start our research, how to solve this problem. And in order to present you the aspects of expanding a surface into a plane in our study, I would like to focus for a moment on the theoretical foundations. I would like to draw your attention to the parameters that we use to develop the surface. And here at the beginning of my presentation, I will limit myself to the cylindrical surface, because for each surface, it will be different way to develop it on a plane. So the parameters we need to develop the surface will be the radius of it, then will be the coordinates of the cylinder axis and the starting point of the development, when we want to start the development. And depending on how precisely we determine or adopt, if we have a project, these parameters, the accuracy we get will vary. And in the drawing on the right side, I present an example of a point cloud of a metro tunnel. So here is our example, point cloud of the metro tunnel, with its expansion, which we done. So here start the expansion. The top of the tunnel was taken as a starting point for the development. And the conducted experiments by our team show that the selection of the radius value has the greatest impact on the correctness of the surface development. So the figure which you see on the slide shows how the expansion of the same point cloud, so in both cases it was the same point cloud, changes depending on the adopted radius value. So here on the top, the radius value has been underestimated. So this expansion, this development was incorrect. If we measure on it the distance, we will get incorrect data. So that's why it's not as easy task as it seems to be. And in practice, we encountered two situations. The first one in which we have a project of the object and we can take these parameters from the project, and in my opinion is the easiest way. And the second option when we have only the point cloud and we have to calculate to find this value. When we have to determining the radius value based on the point cloud, we can use two options. First option can be fitting the circle into the cross section of point cloud, and we can use then the least square method. Or the second option, we can base on the values of the extreme coordinates of the point cloud. So we can find the extreme values via axes Z, Y, X, and then try to find the proper parameters. But we must remember that each of this method, project, point cloud, and then the other option, has certain advantages and disadvantages, and also limitation, which resulting from the fact that engineering objects are not reproduced on the scan as a perfect cylinder. It's because part of it, for example, can be covered by technical infrastructure, or the object is only a section of the cylinder. And this two situation I will show you on the next slide. So here we have the church vault, and it's just a part of the cylinder. It's not even a half of it. And second option, second situation, not option, we have the metro tunnel, and here we have mostly whole circle, but is covered by some technical stuff. And also we have some problems with this, which points are on the surface, which are on the technical infrastructure, which are some outliers. So another problem, as I mentioned, is when we have only a fragment of cylinder. In this case, it's difficult to determine both the center axis of the cylinder and its radius. So it's really hard to properly expansion in a proper accuracy to do this for this situation. And as a part of our research, we developed manually the surface of the Warsaw Metro Tunnel. We using formulas we derived and the determined parameters of the cylinder. We calculate then new coordinates of the points on the expansion. And the results of these are presented here on the slide. So you have here the point cloud which we measure. Then you have the expansion of the point cloud, and it is colored with the distance of the points from the fitted plane based on the least square method. So after expansion, we fitted a plane into the point cloud, and then we analyzes the distance from the fitted plane to find somehow the deformation of the metro tunnel. And in our work, after our manual works, we then developed a similar surface, so the part of the tunnel, using the tools available in the Cloud Compare software. And at this point, you might ask me a question, why do it manually if we have the software? So the programs only develop basic surface, like circle, sphere, but our research aims to develop various surfaces. And an example of this can be volutes of the church. As I said, they are not cylindrical. Maybe they look like, but they are not. Actually, they are completely different surface. So we start from the cylinder to find the other way to do the expansion of the other surface. And another issue why we do this manually is that when we're doing something manually, we can determine how accurate it was. And when we find that it's not enough accurate, we can change the method, we can change the way we do this, or find other solution. When we use the program, we just look at some kind of black box, and the program do something, and we have the results, and that's the end. And what I would like to show you now is an example that the results which we obtain from both methods, so our manual and using the program, are consistent with the respect to the range of values. You can see here, it means that in both cases, it was found that the point cloud representing the selected part of the tunnel differ from theoretical surface of the cylinder within the range of -1 centimeter to ++ centimeter, and similar here, -1 + 1 centimeters. However, it's worth noting that the histograms, so this, of the distance of points from the theoretical surface differ for both methods. So they are not identical. And the point is that in geodetic work, what matters is the reliability and certainty of the results we obtain. When we're developing point clouds, we often rely on automatic solution without fully knowing what is hidden beneath them. So we can find the wrong conclusion after that if we don't know how properly do this. And as I mentioned, the expansion parameters affects its accuracy. And so when we are making studies based on point clouds, we often forgot about this. Or we provide some global value of the root mean square error for the entire study. We don't analyze each point. And it's important to remember that each point has measurement error, as it was said at the first presentation. Each point has some measurement error, and I omit them because it's hard to analyze them, it's hard to find the proper value of them, and each point has also an error related to the accuracy of the study. So if we do the expansion, each point has some accuracy which is related, some error related to the expansion. And here on the slide, you can see at top the feature that present the deformation which we obtain. And as you can see here, here is this feature. The deformation, most of them are between 2 centimeters to 3 centimeters. We have some other points, but in my opinion, they are outliers, some wrong measurement points. And then here you have the map of the distribution of average errors in the position of the points on our expansion in 3-dimensional space. So if you look at this, you will see that here we have about 2 centimeters error of the expansion. And in analogous place here, we have deformation on about 1 centimeters. So the clue is to find if the thing which we represent as a deformation is truly deformation, or is connected of how we reproduce our material. how we find the radius of the circle, how we fit the cylinder in it, how we do all this stuff, preparing to find the last information, the deformation. And our study goes to find the best way to do this for curved surface. At this point, we are not at the end of these studies. We are in the middle, I think, of them. And at the end, I would like to tell you some conclusion which we have. So first of all, the problem of the proper interpretation of laser scanning results is a kind of element which, in my opinion, inhibiting the introduction of the technology as a reliable solution for measurements during the construction process. In Poland, it is changing. More and more companies use terrestrial laser scanning to do their geodetic work, but still mostly laser scanning is connected to the visualization, inventory, not it's sometimes it's used to the to find deformation or displacement, but it mostly is a supplementary study. It's not the first one. It's supplementary, and we think that expanding a surface into a plane is a way to create clear maps of the deformation of three-dimensional objects. And if we have properly expanded surface, more specialists maybe will use it in their work, because 3D models have some problems to be interpreted, to be used by specialists from other fields. And also on a flat surface, we can easily perform distance measurements, and they are impossible or difficult to perform on a curved surface. We have some tools to measure during the arc, but different objects have different surfaces, and not all are flat of them. And at the last, my slide, I would like to show you some advantages of using spatial expansion. First of all, it can improve legability of the measured point cloud of the object. We can obtain information about the distance of the point from the object construction axis in the form of the coordinate of the project point. So it can be easier to interpret than in 3D model space. We can obtain information about angular spatial configuration of individual elements of a measurement symmetrical objects, because when we measure some angle of the 3D model, we measure the 3D angle. I'm not sure if I can explain you, but sometimes if we do some work, we want the angle, but in 2D space. And we have ability to create two-dimensional datasheets which contain detailed geometric and descriptive information on the point cloud. Okay, and that's all. Thank you for your attention. Thank you for being here at the symposium. I'm not sure how it will work, but if you have any questions to me about the work or some suggestion, please contact me. You have my email on the presentation, and thank you very much.
Thank you, Maria. I can see that there are no questions online, but I believe that there is at least one. No, so I have to make some question. As you mentioned that terrestrial laser scanning is still not, I said, the first first choice for some measurements, and you said it's supplementary. Do you think that this is going to change in some near future or not, and why?
You asked me some philosophical question. I think I see in Poland, in companies, is changing. More and more is buying scanners, terrestrial scanners to their company. And I think that if we do more tools, accurate tools, it will change, I hope soon, because this technology have a lot of opportunities to make some great measurements, but it's hard to say when it's changed. In Poland, it's changing, but still supplementary.
Yes, thank you, Maria. So for any additional questions, I believe that you'll get some email, and we're going to move to the last speaker in this session. It is the Richard Honti, and he wrote the paper together with Jan Erdelji, Tomasz Funtik, and Peter Kirinovic. The title of the paper is Analyzing Different Techniques for 3D Capture of Geometric Information of Building Structures. So is everything ready?
Okay, so thank you for the introduction. So I will jump directly into the introduction part. So I think we can all agree that accurate 3D data is needed more and more. And this is the base data for various applications, like some reconstruction processes, modeling, indoor navigation, and so on, and many more. In some cases, traditional field measurement techniques can be a little bit slow or inefficient, also time-consuming and resource intensive. It means that you need at least a few people to measure a building or to measure a site. These can be the main reasons for the significant progress in 3D data capturing methods or methodologies in recent years, where new technologies are emerging. For example, methods based on SLAM, like SLAM-enabled handheld scanners, or some methodologies using mobile devices with LiDAR sensors, or methods or systems like Matterport, and so on. These methods are in some cases most effective or faster, and maybe less time consuming than, for example, terrestrial laser scanning or photogrammetry. However, the usability and the accuracy of these methods are questionable, and also it is not truly compared or investigated. So with this presentation, I would like to scale this gap a little bit and compare some of the selected methods with the survey-grade terrestrial laser scanning. So in this topic, 3 methods or 3 systems or methodologies were selected for the evaluation. First, the Matterport method using a 360 camera. The second is the Matterport system using their only developed Pro 3 camera, which has and LiDAR sensor. And the third one is the SLAM-enabled handheld scanner GeoSLAM ZEPGO. So the first system is the Matterport. It was chosen because it offers an interestingly low-cost indoor mapping solution. It doesn't require some hard planning for the field measurement, and it can be faster, for example, than terrestrial laser scanning. They call it a 3D camera system. that can capture real-world objects and create some digital virtual photogrammetric model from it. And in case of Matterport, several sensors can be used for capturing, from mobile devices through 360 cameras. Also, they have two only developed cameras, the Pro 2 and the Pro 3. And also some laser scanners also can be used for the data capturing part in case of Matterport. Of course, the accuracy of the resulting model depends on the sensor the user is using. In general, Matterport relies on two primary data types: images, of course, which are used for the visualization part, and depth maps, which are used to estimate the distances between the sensor position and also the points on the object surface. Then they have their own AI method, the Cortex AI, which is then used to couple these data together to create a 3D photogrammetric model, as you can see on this slide. So the whole processing part is done by the Matterport system. The users done only the capturing part. So as I mentioned in this topic, we use two sensors. First, the 360 camera Ricoh Theta Z1, which is also recommended by the Matterport, and this easily affordable 360 camera with two CMOS sensors with wide field of view lenses to create a panoramic image. So in case then of processing to create a virtual model, these panoramic images are used. And the second one is the only by Matterport developed Pro 3 camera, which I mentioned has a LiDAR depth sensor and an imaging sensor. The range of this LiDAR sensor is from 0.5 to 100 meters, and the scanning speed is up to 100,000 points per second. And the third system selected for this evaluation was the SLAM-enabled handheld scanner, GeoSLAM ZGO, which consists of also two main systems from a 2D time of flight LiDAR and then inertial measurement unit, which are coupled together on a motor drive. And then in post-processing, after the measurement, GeoSLAM is using their own SLAM algorithm to combine these data together to get a detailed 3D point cloud. For the evaluation part, 4 test scenes were chosen, which varied in size, shape, complexity, geometric structure, density of objects like furniture, and so on. And also to be able to compare these methods or the results from these methods with something. The reference data was captured with Trimble TX5 3D laser scanner. So the first test scene or the first building site was our laboratory of surveying at our faculty. As you can see, it is an oblong room with windows on both sides and also with some columns and with some furniture. The second one was a long hallway because, as we can see, in these types of building spaces, sometimes also we have problem with the terrestrial laser scanning, or the resulting point cloud can be shifted and so on. So we wanted to check if it's also true in the case of these methods. The third one was a bit larger lecture hall with a step structure, and the last one was a smaller office with lot of furniture. Okay, so the measurement process in case of the Matterport was divided into two parts. So first we measured with the using the Ricoh Theta Z1 and then with the Matterport Pro 3. And also we, in both cases, we did 3 measurements with varying distances between the camera positions. So with 5-meter distances, 3 and 1.5 meter distances between the camera positions. We also wanted to check if this setting or if has some something to do with the accuracy of the final results. And in case of the Geoslam ZEBGO, so the handheld scanner, we created loops with closures. As you can see on this slide, so with green color, the resulting point cloud is shown, and with red color, the trajectory of the measurement, where several loops of the same parts of the building space was measured. On this slide, you can see some basic measurement detailed comparison for all building sites, and also for all the methods compared. So for the Matterport with the 360 camera, with the Pro 3 camera, for the handheld scanner, and also for the reference model, which was the terrestrial laser scanner. We compare the number of positions and also the time needed for the measurement. If we're talking about efficiency, then of course the time is more important in our case. As we can see, the fastest method is the Geoslam ZEBGO and also the Matterport method with a 360 camera. In most cases, the time needed for measurement is half of the time needed for measurement for the TLS. For the evaluation of the results from these depicted methods, we used the control point approach. So first we selected some control point parts, some corners of building structures or window openings or doors, and then we measured the distance between these control point parts on these models from Matterport and Geoslam. And also, of course, we calculated or we measured the distance, the same distances in the point cloud. I forgot to mention that in case of the Matterport models, first is the capturing process, of course. Then after the capturing process, the user uploads all the captured images into the Matterport cloud for processing. And the result is a virtual photogrammetric model, which can be accessible only through the Matterport app. So it's not possible to download it into your own computer and then use it or reprocess it and so on. But you can access it only through the Matterport app. Of course, this Matterport app has some other functionalities. So you can, for example, do some measurements on these models and so on. So in our case, the distances for this comparison were directly measured on these virtual models. And in case of the Geoslam, the distances were measured directly on the resulted point cloud. And here you can see the results for all 3 methods. So the comparison of these distances between the reference, so between the terrestrial laser scanning and the compared method. On the left, you can see the table for the Matterport model with captured with the 360 camera. Of course, these models had the biggest differences. The differences were from 4 or 8 millimeters to 400 something millimeters. And in average, these models has error or the difference up to 23 centimeters, which is 26 centimeters, but still we are talking about an easily affordable 300cc camera, so not some surveying equipment. The second was the Matterport model with the Pro3 camera, and we can see that the differences are from 4 to 23 millimeters, so it's around up to 2.5 centimeter differences between the models from the Matterport with the Pro3 camera and between the terrestrial laser scanner. And the third one was the GeoSlam. Also, we have here differences from 3 to 31 or 40 millimeters. So it's still, in average, it's still below 3 centimeters. As a conclusion, we compared three methodologies. So the first was the Matterport using a 360 camera, which of course is the most affordable, the fastest, so the most time efficient. The disadvantages of this method is that it's really dependent on the camera positions, the overlaps, the number of stations. The distances or the distance differences were from 41 to 23, 230 millimeters, so 23 centimeters. And as I mentioned, this model is accessible only through the Matterport, so it's not possible to somehow download it and then use it for other purposes. And also from these models, it is not possible to generate point cloud. The second system was the Matterport using their own Pro3 LiDAR camera. We can still call it somehow a low-cost scanning solution. The difference is below 2.5 centimeter. And since it has a built-in LiDAR camera with range up to, built-in LiDAR sensor with range up to 100 meter, the differences between various spacing. So if we were using spacing between the camera positions 5 meters, 3 meters, and 1.5 meters, were insignificant. And in this case, also the point cloud is not the direct result. So in case of Matterport, the direct result is always this virtual photogrammetric model, but it can be point cloud can be generated for extra charge. And the last system was the GeoSlam ZebGo, so the handheld scanner, which we can still consider as more time efficient than TLS. Also, it is the most costly from these compared systems. And the differences we are below, in average, we're below 2.5 centimeter. But in this case, the biggest advantage is that the point cloud is the primary result after the measurement. Okay, and this is all from my side. So thank you for your attention.
And thank you for your presentation. Questions? So usually there are no online questions. So yeah, so it seems that I've got one question. So it seems that we can use all those devices to survey for some purposes, for sure. Yeah. So even mobile phone. So yeah. But do you think that those data are reliable for some? Yeah.
It depends on the purpose that you want to use this data, of course, because sometimes people who don't really know the accuracy of this data, they are using it, so they just got some virtual model and then they don't know the accuracy or how they can use it. So it really depends for what purpose you want to use it. So in case if you want to get some sub-centimeter or accuracy, of course not, but for some virtual presentation of spaces and so on, it
Okay,
can be.
but is this Matterport device a black box solution? So it's triggered by
completely-
itself.
It's completely a black box solution.
Yeah, so
It's completely
cannot do
the whole
anything.
processing part. Only the capturing part is done by the user, but the whole processing part is done by the software itself.
So basically, anyone can scan it.
Yeah.
Okay. Any other questions? Mate. Mike. Sorry.
Thank you. Very nice presentation. Do you plan to further expand experiments or continue this research?
Yeah, of course. We would like to test also some mobile devices with LiDAR sensors and some other solutions, because there are a lot of other solutions like Matterport. So Matterport is only one, but there are, for example, Cupics and so on, which is also using, for example, 360 cameras. And in their case, they are using videos to create some virtual models. So we would like to also check these other solutions.
And what about iPhone? Did you maybe try out this?
Yeah. This is our next future plan.
Okay, thanks. And for mobile applications, do you also plan to do such comparisons? I mean, not with the same setup, but maybe it's part of this game or part of this research.
Yes, because now not only for iPhone, but for example, for iPad, if it has some inbuilt LiDAR sensor, there are a lot of applications for scanning, if we can call it like it. So we will try to compare these applications.
Yep. Thank you.
There was, I think, so.
Hi, just one more curiosity question. Can this Matterport be also used successfully outdoors? Did you check that, or it's only indoor stuff?
They call it an indoor solution, but maybe. We didn't try it yet, but we will.
Okay, thanks.
Okay. Thank you. That was our last speaker. And so now it is time for lunch break. The lunch is going to be served in the hall next to us. And afterwards at 1:30, there is a general sponsor presentation. And at 2, we start with the technical session number 2, building information management and 3D models of buildings, chaired by Professor Miodrag Rojić. Ma nema veze.
Dobar dan svima, ja sam Edi Smolčak i danas ću vam pokazati jedan naš demonstracijski automatizirani monitoring sustav. Proćemo kroz par poglavlja koje su prednosti automatiziranog monitoringa, vrste, to jest odnosno vrste senzora, nešto o Trimblovom softveru za monitoring T4D, proćemo kroz demonstraciju uživo i reći ću vam par smjernica kako ih možete više naučiti. Gdje je bitna sigurnost ljudi i infrastrukture? Tu je neophodan automatizirani monitoring zbog trenutnog alarmiranja. Ako se monitoring organizira od početka građenja neke infrastrukture, tad on ulazi u građevinske i BIM procese. Oprema je dedicirana za monitoring, nije projekt ovisan o ljudima i o opremi i o vremenu. Što se produktivnosti tiče, kod manualnog monitoringa imamo trošak svakim odlaskom na teren, znači trošak nam nije velik na početku jer već imamo opremu i ljude, dok kod automatiziranog monitora moramo na početku više uložiti u opremu, ali tada troškovi su puno manji, pa povećanjem trajanja projekta se smanjuje trošak kod automatiziranog monitoringa. Upravljanje podacima je mnogo jednostavnije nego kod manualnog monitora jer nam sve se stora na jednom mjestu i možemo do podataka kada god želimo. Ako nam trebaju svježi podaci, ne moramo misliti gdje nam je oprema, gdje su nam instrumenti, kako je vrijeme vani, nego samo odemo u softver i izvadimo što nam treba, pošaljemo podatke. Kod GNSS monitoringa možemo dobiti najveću moguću točnost za veće udaljenosti, pa se GNSS uvijek koristi za veće projekte. Prednost je što nije potrebna optička vidljivost između točaka, ali moramo misliti na vidljivost prema satelitima. Isto ne ovisimo o vremenskim uvjetima, znači ne smeta nam magla kao kod totalne stanice, a fiksna referentna stanica može biti kilometrima udaljena. Recimo kod nekog mosta velikog ili klizišta, fiksne točke nam uvijek moraju biti na stabilnom području, pa kod GNSS-a baza nam može biti 20 km udaljena, opet ćemo dobiti pouzdane rezultate. Frekvencija opažanja može biti 100 Hz i alarmiranje može biti trenutno uz RTK mod. Kod monitoringa s totalnom stanicom imamo visoku preciznost. Jedino s totalnom stanicom možemo detektirati pomake, recimo manje od centimetra, sa kratkim vremenom reakcije. S GNSS-om možemo dobiti manje od centimetra, ali u postprocesingu. Ako imamo puno točaka na manjem području i puno nam je jeftinije praćenje točaka sa totalnom stanicom, jer prizma košta manje nego GNSS, a uz to do prizmi ne moramo vući napajanje i komunikaciju kao što trebamo do GNSS-a. Par bitnih stvari možda kod odabira instrumenta za monitoring. Ako je projekt monitoring tunela ili željeznice, nekih takvih objekata, onda je bitan najmanji mogući razmak između prizmi. To deklariraju proizvođači na toliko i toliko metara. Instrument može razlučiti dvije prizme na toj i toj kutnoj udaljenosti. Što i nije baš tako jednoznačno uvijek, jer ako je jedna prizma bliže, a druga dalje na istoj kutnoj udaljenosti, onda bliža prizma ima jaču refleksiju. Ako se monitoriraju ceste ili aerodromi gdje ne možemo zbog prometa postaviti prizme, onda nam je bitna veličina točke laserskog pokazivača jer ćemo s njime preciznije definirati točke koje monitoriramo. Što se tiče zaštite instrumenta, instrument moramo zaštititi što zbog vremenskih uvjeta, ali više zbog krađe i vandalizma, jer instrumenti su obično otporni na uvjete. Ako ćemo staviti instrument u neku komoru sa staklom, bitno je da je staklo jednoslojno jer nemamo onaj dodatni sloj između dva stakla, dodatni sloj zraka. I moramo paziti da nam prizma nijedna nije ortogonalna na staklo. Moramo paziti na IP rating, znači da je otporno na kišu i prašinu, ali osim toga ako instrument će biti vani cijelo vrijeme, bitna je i otpornost na kondenzaciju vlage. Kada vlaga prelazi iz pare u tekuće stanje, onda može prodrijeti kroz tipovnicu instrumenta te prouzročiti kvar. Tako da je bitna ta druga stavka osim IP ratinga. Napajanje komunikacija, znači naravno spojamo se na mrežu, na struju, uvijek mora biti UPS u pozadini kada da nemamo prekide kod nestanka struje. Ako se radi o nekim zabačenim područjima, onda imamo opciju solarnih panela i vjetroturbina. Što najbolja praksa bi bila kombinacija jednog i drugog, jer nemamo uvijek sunca i nemamo uvijek vjetra. Moramo misliti na pouzdanu vidljivost do meta kod postavljanja meta, da ne bi došlo do prirasta nekog drveća, te da moramo misliti na to. Bitna je iskoristivog instrumenta nakon projekta. Da li ćemo instrument nakon projekta moći koristiti samo za takve monitoring projekte, za neke druge monitoring projekte ili ga možemo koristiti za geodeziju. Par značaka i kod Trimblovih totalnih stanica. One imaju pogon pomoću elektromagneta. To znači da nema nikakvog kontakta, nema četkica, nema trenja, nema zupčanika, nema kvačila. Jednostavnije održavanje, duže traju instrumenti, mala je potrošnja energije, a uz to je i precizno okretanje instrumenta. Mala potrošnja energije je bitna ako imamo te zabačene područja gdje imamo struju pomoću solarnih panela, na primjer. Još jedna stvar kod Trimblovih totalnih stanica je Trimble Sure Point tehnologija. To je otpornost na vibracije, sitna propadanja stativa i vjetar. Znači, inače kad se instrument pomakne mrvicu ili mu se malo stativ propadne, kompenzator namješta instrument u dobar položaj, ali to je kompenzira nagib. Ali tada nam nitni križ je otišao i nije više na meti, pomaknuo se. To sam demonstrirao sad na ovom kratkom videu. Znači, kut ostaje isti. Kut se naravno vraća na istu vrijednost, ali i kod propadanja stativa, točka laserskog pokazivača desno dolje, evo ponovit ću. Znači, kad ću pomaknuti podnožni vijak, simuliram propadanje stativa i točka laserskog pokazivača odlazi u jednom smjeru, ali taj sustav je vraća na sredinu. Trimble Vision tehnologija je integracija kamere sa totalnom stanicom, to je opcija kod kupnje instrumenta. Možemo gledati s time što instrument vidi. Za monitoring to znači da je moguća vizualna inspekcija. Kao što vidite na ovoj slici, možemo slajdati vrijeme, gledati grafove i uz to gledati šta je bilo u tom trenutku na terenu sa metama. Uz to može biti korisno za dodavanje novih meta ili ažuriranje postojećih. Jer, na primjer, ne možete uvijek možda instrument postaviti, možda bi vam bilo optimalnije da ga postavite negdje gdje ne možete do okulara. Ne možete sami definirati prizme, na primjer na čošak zgrade ako ga stavite imate najveći vidokrug, ali tad ne možete do okulara. Onda ako imate kameru možete time s kamerom definirati mete. Naš instrument koji ću pokazati uživo u softveru zapravo nema kameru pa vam to neću moći pokazati. Setup M1 je komunikacijski uređaj koji je neophodan za automatizirani monitoring. To je jedan router, komunikacijski uređaj koji upravlja instrumentom. U njemu se definiraju mjerenja, definiraju se girusi i runde, a u njega ide SIM kartica, znači može ići ili na LAN ili na 4G mrežu, šalje podatke do servera, a ima i internu pohranu. Znači kad gubimo komunikaciju, tada setup M1 on sprema te podatke, te ih naknadno šalje na server kad se komunikacija obnovi. Uz njega je senzor za temperaturu, pa uz barometrijski senzor u totalnoj stanici možemo uzeti u obzir atmosferske uvjete. Kod geotehničkog monitoringa, koji god vam parametar zapravo padne na pamet, vjerojatno postoji senzor koji to mjeri. Kako funkcionira? Senzor snima podatke, data logger je spojen na njega, on ih zapisuje i šalje dalje. Šalje ih dalje radio vezom do gatewaya, a gateway ih šalje u drugi protokol, te preko interneta šalje do softvera za obradu. Kod geotehničkog monitoringa par bitnih stvari. Ako se provodi dinamički monitoring gdje nam trebaju opažanja, na primjer svake sekunde, onda ćemo vrlo vjerojatno trebati napajanje vuč do svakog senzora, što je problematično ako imamo puno senzora, puno kopanja rovova, postavljanje kabla. Zato ćemo uvijek u svim drugim slučajevima koristiti statički monitor, odnosno senzore na bateriju. Domet gatewaya je bitan, jer što je veći domet gatewaya, to manje gatewaya trebamo, gatewaya i repeatera. I koliko senzora ide na jedan gateway, o tomu ovisi isto koliko ćemo gatewaya trebati. Gateway je najskuplja stavka u geotehničkom monitoringu, pa nam bilo bi dobro da ih koristimo čim manje. Bitna je jednostavnost postavljanja senzora i promjena postavki i kompatibilnost s drugim proizvođačima. U geotehničkom monitoringu neki proizvođač možda proizvodi najbolje te senzore, a drugi neke druge. Bitno je da ih možete integrirati ono što vama treba u vaš projekt. Trimbleov gateway koristi long range radio do 15-16 km na otvorenom, to je nekih 2 km kad je senzor bio postavljen u šahtu u urbanoj sredini. Mi smo ga testirali tu sa Kostanjeka do Stupnika, nekih 7,5 km i nije bilo problema. Nije bilo ni optičke vidljivosti, ali podaci su dolazili frekventno. Do 250 senzora ide na jedan gateway, napajanje samo do gatewaya jer su data logeri i senzori na bateriju. Znači postoje data logeri i senzori koji su odvojeni ili su neki senzori ukomponirani sa data logera. Postoje 3 vrste data logera i on podržava sve 3, znači digitalni, analogni i data logeri na osnovu vibrirajuće žice. Trimble 4D control, znači tu ću samo na brzinu proći jer ćemo o tome, uživo ću vam pokazivati nešto. Znači to je softver u koji se ukomponiraju podaci geotehničkih senzora, GNSS-a i totalnih stanica. Sva izjednačenja se provode u tom softveru i totalne stanice i GNSS-a. Analiza i vizualizacija, uvjetno alarmiranje i izvještavanje. Možemo koristiti koordinatne sustave, izjednačenja, korekcije mjerenja, različite vizualizacije, analize, ažuriranja mogu biti u stvarnom vremenu i zakazujemo uvjetovane alarme, znači postavljamo uvjete kada bi alarm trebao biti aktiviran, izvještavanja i možemo kreirati javne URL-ove s nekim prikazom. Ok, sad ćemo malo izaći odavde. Ući ćemo ovdje. Znači na home screenu, to je sad Trimble 4D web, znači software za vizualizaciju gdje su mi spojeni svi ovi senzori. Odmah imam sve u bojama i ako mi je sve zeleno znači da je sve u redu. Alarmi nisu aktivirani, to je sve u pragovima tolerancije, a svi senzori dobivaju podatke redovito, znači senzor data flow je uredan zelen. Malo ćemo ući u administraciju, samo kod kreiranja akaunta nema softverskog ograničenja koliko korisnika može koristiti jedan projekt i svakom korisniku mogu dodijeliti ulogu koju želim. Znači neko admin, možda je neko analitičar samo za analize, neko da može samo pregledavati podatke, neko je gest. Kako će on dobivati notifikacije, SMS ili mail, ali ne samo to, nego mogu svaku tu ulogu customizirati koliko god želim. Recimo ako idem add role i za svakog kom ću dodijeliti pristup monitoring softveru, mogu izabrati točno šta on može i šta ne može raditi. Da može samo pregledavati alarme, ali može editirati grafove ili bilo šta drugo. Znači imam potpunu kontrolu nad svim korisnicima kojima ću dati pristup u softver. Projekte mogu definirati, možemo imati više projekata i sa istim senzorima. Možemo recimo na većim projektima razdvojiti konstrukcijski čelik u jedan projekt, a beton u drugi projekt ili tako dalje. Prvo idemo na terrain view gdje možemo vidjeti sve senzore, to jest map view. Oni imaju ikone ovisno Znači prizma, geotehnički senzor, totalna stanica, GPS. I kad stavimo miš na njega vidimo pomake. Možemo uključiti imena ili možemo staviti da vidimo displacements u 3D, u 2D, znači strelica gdje se miču točke u realnom vremenu ili odstupanja u visinskom smislu. I sad gdje mi ova strelica ide prema dolje, znači da sve točke snižava im se visina u odnosu na referentnu. U charting and analysis imamo grafove. Znači svaki senzor koji smo definirali kad smo ga uvodili u sustav, definirali smo parametre koji nas zanimaju. Recimo za svaki senzor mogu otvoriti graf. I sad imam parametre odstupanja po N osi, po E osi i po visini. Mogu ih isključivati kako me volja, da lakše se vizualizira. Mogu staviti da su sad ovdje satna mjerenja, znači sredina mjerenja svakih sat vremena ili mogu i prikazivati minimalne i maksimalne vrijednosti. Znači min-max. Isto odavde mogu direktno eksportati u Excelu ili u CSV. Ako mi trebaju podaci za neku daljnju analizu. Pod scatter plot ili dijagram raspršenosti je drugi prikaz, recimo za isti senzor, gdje možemo lijepo scrollati po vremenu i gledati koliko točke bježe u kojem smjeru i kad su te točke snimljene. Pa možemo lakše naći kad je bilo neko veće odstupanje. Također ovdje možemo odmah eksportati ili recimo neke druge postavke mijenjati. Analize, ako su grafovi, graf je recimo prikaz mjerenja parametara od jednog senzora, a onda je analiza prikaz mjerenja od čega god želimo, koji god parametara iz kojeg god senzora želimo, znači možemo ih kombinirati na jedan prikaz na jednom grafu. I onda imamo više ovih y osi, pa možemo gledati u isto vrijeme, na primjer, temperaturu, možemo ih maknuti da lakše uočimo o čemu pričamo. Možemo gledati samo temperaturu i pomak po N osi, ili ako imamo totalnu stanicu, znači odstupanja, pa gledamo da li ima korelacije sa temperaturom, da li odstupanje ima korelaciju sa temperaturom, na primjer. Možemo također kreirati regresijski pravac ili izbacivati neke točke iz izvješća naših. Vizualnu inspekciju ne mogu pokazati jer ovaj instrument nam nema kameru, ali još mogu pokazati composite view, što je neki grupni prikaz, od njega možemo i URL kreirati pa svako može ga vidjeti, gdje možemo više toga, znači i analize i grafove i što god želimo stavljati na jedan prikaz, customizirati koliko toga želimo na ekranu. Sad je ovdje ekran manji pa sad nema smisla, na primjer, neki ovaj graf, ali ovdje imamo live prikaz ili možemo imati znači ažuriranje fotografija svakih jednom dnevno ili kako god želimo. I kad stavimo miš na senzor vidimo koliko su njegova odstupanja ili možemo staviti da odmah vidimo njegov graf njegovih odstupanja. Pa ovdje imamo analizu, ovdje imamo scatter plot, ali sve to kontroliramo sa ovim slajderom i tako vrlo lako možemo vidjeti, uspoređivati podatke. Na primjer da imamo sad meteorološku stanicu spojenu, a nemamo, onda bi isto mogao staviti ružu vjetrova da mi je jedan od ovih grafova, pa kroz neko određeno vrijeme gledam pomak je bio u ovom smjeru, a vjetar je puhao tamo, temperatura je bila tad tolika i tolika. Analize mi služe da mi je puno podataka na jednom mjestu i da se lako snalazim u vremenskom periodu. Još dvije stvari. Reporti i alarmi. Alarmi su ono najbitnije zašto radimo automatizirani monitoring. Dodat ćemo jedan alarm. Bitno. I dodajemo uvjete. Znači, želim da se alarm aktivira kada, recimo, odstupanja u stvarnom vremenu. Ovdje biram samo da li ću koristiti delta x, delta y, delta z ili ću koristiti brzinu i invers brzine kao da praćenje trendova. To se više koristi kod geotehničkih senzora i naročito kod klizišta. Nas zanimaju sad delta x, delta y i delta h. od specifičnih senzora, znači pokaži mi kada, želim alarm kada ovaj GNSS po visini pređe 5 cm, recimo. Ne, želim alarm kad bude 6 cm, a attention i warning na manjem pragovima. Mogu se sad igrati sa standardnom devijacijom. Mogu postavljati no data alarm. Znači recimo da sa totalnom stanicom mjerim runde svakih 2 sata, onda bih možda stavio želim da mi javiš kada 4 sata nemam podataka, želim alarm da znam da nešto nije u redu. Dodan je jedan uvjet. On je zelenom bojom jer su trenutno odstupanja manja od ovih 2 cm. Uvjeta mogu dodavati koliko god želim. Može biti da moraju biti oba uvjeta ispunjena ili samo jedan ili 50%. Mogu raditi što god želim. Merge operand nek bude end, znači da moraju oba uvjeta ispunjena biti za alarm. Znači želim odstupanja kada su veća od 6 cm, a temperatura sa ovog senzora je veća od, sad ćemo neki manji broj staviti, 20. I taj uvjet je crven, znači taj uvjet, prag je pređen i ovaj za alarm, znači ovdje bi se sad aktivirao alarm, ali nije jer prvi uvjet nije ispunjen. Uvjeta mogu dodavati koliko god želim. Mogu birati kom će ići ti alarmi i da li trebam potvrdu toga da je netko vidio alarm. To je korisno kad imamo dijeljenje odgovornosti na nekim projektima. Također mogu customizirati poruku za alarm, poruku za warning, za attention, što želim da dođe tom i tom korisniku. To je što se tiče alarma. Oni mogu dolaziti SMS-om, web notifikacijom ili e-mailom. Još imamo reporte, znači izvješća, koje možemo sad kreirati još jedno novo izvješće na osnovu alarma, analize ili nečeg drugog. Dobro, znači želim da mi izvješće dolazi recimo tjedno, ponedjeljkom, utorkom, srijedom i petkom u 8 sati u PDF-u. Želim da dođe svim koji su u grupi analist u projektu i recimo još dodam nekoga. Želim da uključuju series, grafove i podatke. I to želim za ovu analizu. To je to. Znači izvješće je kreirano, svaki dan koji sam definirao u to vrijeme ću dobiti mail sa izvješćem o odstupanjima. To je to što sam htio pokazati ovdje. Gdje početi ili kako naučiti više? Pa Trimble ima dosta resursa o njihova monitoring stranica, njihov monitoring YouTube kanal koji ima preko 100 videa. Webinari, svaku 3. srijedu u mjesecu izlazi webinar o monitoringu i to već tako 5-6 godina, pa se i toga nakupilo. I help portal ima za prilično detaljan za ovaj software. Svaka S-serija se može pretvoriti u automatizirani monitoring. Znači nema kod Trimble nema dedicirane stanice da je samo ta za monitoring, nego bilo koja S-serija može biti monitoring stanica. Samo treba setup M1 uređaj. Znači možda neko već ima instrument za monitoring, a to ni ne zna. Podrška je brza od nas i od Trimblea lokalno koja se nalazi u Minhenu. A možemo vam omogućiti koga zanima besplatan pristup jednom ovakvom projektu. Možete se javiti meni ili skenirati QR kod pa mi pošaljete svoje podatke pa vam dam ovlasti da možete gledati i kreirati svoje analize. To je to od mene. Hvala vam na pažnji. I ako ima kakvo pitanje, rado bih odgovorim. Nema pitanja. Hvala vam. Samo da se Evo, samo da se odlogiram ako sam ulogiran, samo da provjerim.
A tu će biti.
A dobro. Što daš? Pa naravno da može biti svašta kad nestane, ništa drugo. To je to.
Kako niko? A od ovih predavača. Je šta pišemo tu ili?
Ništa. Kao fora da treba najaviti samo sljedeću, sve su.
Poslije, jel?
Da.
Obavijesti nemaš nikakve?
Da, uopće nema nikakve sve su.
Daj, neku vodu otvori da se... Imaš tu otvorenu, daj. Aha. Nemoj to računati. Čekaj, nije mi jasno gdje je ovome prekidač. Dobro, mi tu ne trebamo ništa. Dobar dan svima. Dobrodošli na poslijepodnevnu sesiju. Nakon dobrog ručka malo će biti teško pratiti, ali pokušajte se koncentrirati. Imamo 4 zanimljiva predavanja. Ovo je sesija broj 2. BIM i 3D modeli od zgrada. Ja sam voditelj Miodrag Grojića, pomagat će mi kolegica Doris Pivac. U ovoj sesiji imamo 4 prezentacije. Po sadržaju i naslovu čini mi se da su zanimljive, ali to ćemo sada provjeriti. Pa možemo odmah krenuti sa prvom prezentacijom, a to bi bilo BIM-based Construction Progress Monitoring System. Rad će nam prezentirati Tomaš Funtik. Please, Tomaš, the floor is yours.
Dobar dan. Hello, I'll continue in English. So you don't want to hear my Croatian language. I know something from summer, but that's not enough, obviously, for presentation. So let me start my presentation. Let's see where it is. Okay. All right, so I will tell you something about BIM-based construction progress monitoring system that we are basically developing, and we have and how we approach to that. In case you're seeking for any contact information, here are some of them. I work for Faculty of Civil Engineering in Slovak University of Technology in Bratislava, and the Department of Building Technology. So I'm not surveyor. I don't know almost nothing about surveying, but I have some friends that do that. So yeah, so if I don't do anything correctly, as you're used to, sorry for that in advance. But I'm quite experienced with the BIM. I'm basically the chairman of Slovak Technical Committee for Building Information Modeling, and I'm trying to engage also with international groups that focus on this topic. And I'm vice president of BIM Association in Slovakia. Why we are dealing with BIM? Basically, for over years, the productivity in construction sector has remained the same almost, or sometimes we're talking about that it decreased. So we need definitely some tools to be able to do digitization and in order to raise that. And BIM may be the tool that can contribute significantly in order to do so. So basically, BIM is the enabler that allows the transformation of technology and bring us to the digital era of 21st century. But in Slovakia, currently we have no mandate for BIM, but our legislation and the one that we're preparing has the roadmap for 2032, and they set basically some goals, and they're trying to reach them. They want to create digital image of the country, including information about the spatial, cultural, and also environmental, and the information about buildings. And this is where we have some overlap, because how to obtain the data about buildings from the architects and engineers, because they're creating and developing models. Even so, if we have BIM models, we can have data behind in a structured form. So basically, we can use it for urban planning and so on and so on. Just really quickly, the overview about BIM adoption in Slovakia. For over the years, from 2007, we are measuring that, evaluating every single year. For this year, we don't have the data yet. It's usually done in October. So from previous year, we see the blue color are those people that are already using BIM. Orange color are those that are interested in the technology but don't use yet. And the gray one is the people that don't really see future in BIM. So as you can see, from 2023, almost 24% people are declaring they already do BIM in Slovakia, which is, let's say, quite a lot, but we still have some work in front of us. I use this opportunity and I present this slide as well. From this year, I was basically creating the survey also for Croatia, but unfortunately, I didn't have basically the opportunity to report it and to write it in topic or present it in conference. So I have full report with more details in. So I recall only for short time only this one. So it shows that basically In Croatia, it seems that you are almost the same ratio of BIM adopters, around 23.7%, which is nice. And, which is very nice that you have only 33% people that really they don't see future in it. So it's better in Slovakia. So if you will be interested, I can share with you the full report with all the disciplines, comparison between the buildings, infrastructural project, use of CDE, use of BEP on projects, and so on and so on. Yeah, I don't know how basically pro are you with BIM, so I've just recalled one the definition of BIM from the standard. I believe you also have standards or set of standards for BIM in Croatia. We have those one in European level, the series 19650 that define BIM as shared digital representations of built assets, so basically any building or the bridge or whatever, and they can contribute it for us. They create a reliable basis for decisions. So some people are basically incorrectly defining BIM as some 3D software. Mostly they say that it's a Revit, which is not really correct. We have hundreds and thousands of tools to create and manage data for BIM, but it shouldn't do anything itself. It should really contribute in a form that give you the information and you do the decision. So the BIM is not here to eliminate any profession, even though we have new professions rising. If you're working with BIM, we have BIM managers, BIM coordinators, or CDE administrators. So we really, this is the transformation of the sector. Basically, creates new opportunities for new professions. So this is how I see building information modeling. These are the data. You know where to find them, how to take them from the correct spot and to use them. So I don't see it as a drawings or any sections or technical reports. I see it as a structured data that can be used, and this allows the digitization. Quickly, the readiness of the sector. Basically, as I said, BIM is the tool for digital processes and enables automation because we have structured data. The absence of BIM mandate, which we have in Slovakia, probably you have the same in Croatia, affects the adoption speed. We're moving really, really slowly. And non-standardized outputs reduce the possibility of further use of the model. So those are the information we want to recall. But if, for example, non-graphic information are not really defined on the national level, it's really, there is need for additional adjustments that consume time. So basically, you need to modify, search for the data, work with the parameters and so on and so on. And now the more important part, the construction progress monitoring system, that was the topic of my presentation. So it was basically the background to it, because we can't do what we suggested without BIM, because BIM provides crucial inputs for our system. For monitoring, I believe you have much more to say to me about methods of monitoring that I can tell to you, so I'll skip that one. But we focus on visual system or wireless technologies. For our purposes, the visual systems were not really suitable because we were focused on the processes inside, with the finishing processes, where you can't really engage with visual systems. So we choose wireless technology that allows us to do and install the infrastructure without wiring. That is on the construction side, this is really crucial. If you have any wiring, it's a potential damage and you can ruin all the work. So we found that with our cooperation with another faculty for engineering and information technology, they developed the technology that doesn't really need any single wire. So we have devices that records the contact, the duration of the contact between two sensors and the distance. And through the gateway, we collect the information. And the other point, so this is what we have, is basically the technology to capture the data about the motion of the workers on site. And then we have another that is basically information about the building that are withdrawn from information models. We are collecting, basically the BIM provides information about technological structure, time structure, and spatial structure. What we know, basically spatial structure, where it's located, how many rooms, how many floors, so on and so on. Technological structure, that's the interconnection between the technological processes, and time structure. For every single building, there is a schedule, time plan. we can follow that. There are even tools to create the schedules in automatic way based on the basically location-based scheduling techniques. So we can interconnect the existing data. So it's nothing new, basically. We're just interconnecting the data that couldn't be that you couldn't do before. So data from the schedule, from the model, about location, and about plan. So basically, we know how many people were supposed to be there, what are the processes that should be taken on the 4th floor, and so on and so on. And that's why we can interconnect everything together. And this is the whole map. I will explain further in following slides. So we even tested this technology on site. You know, it's important to investigate. We created the schema, so we basically represented the building with the possible location of sensors, and you know, suggested where the sensors will be located. Basically, we measured it on the space unit where basically the apartment, so not every single room, but the apartments. And we have the prototype. Firstly, it was basically watches, but then we find out that the workers on site, especially during the winter time, it's covered. Sometimes it makes interference with the sensors and gateways, so it wasn't really good. So the next prototype was the small wearable device. You see about 7 centimeters that you can place on helmet, or you can have it on the belt. And basically let's say the wide one with the number on, it's basically the stationary device. Basically, in the principle, they are the same, but the other one has the bigger battery, so because it needs to be installed on site and stay there for a couple months. The other one, it's basically plugged in the electricity every single day. So this is the installation on site with the chargers as well, and the testing and verification. The colleagues from the faculty create for us the platform where we could see eventually where the tracker, the wearable one or the static one met the time frame, and then we can investigate whether you were on that apartment or not, when you've been there, and so on and so on. Basically, originally the technology was created for the corona, for the huge factories, in order to see whether some people met, and to see whether if they met for longer than 15 minutes, you say, okay, for next day you need to stay at home. You know, so this was the original purpose of the technology, but we find it really suitable for tracking people on site as well. Of course, there are some limitations. We don't know who is that person, because you can't know that. So we can employ that only on the teams with a group 6 and more. Okay, so you can't really identify who's that. We don't know the real-time position. We basically collect the information after the work, so every single day, but after work. So basically, because you need to work with the people and explain them, you don't really monitor them. You don't know where they are and how long they are, maybe somewhere. But next day, you know, for example, the electrician was on the 4th floor, was in that apartment, another apartment, and so on, but you don't know who that was. Yeah, and this is the full methodology, but it's maybe not really visible, so I'll try to interpret it. So it's basically simple with data collection. We take some information from the BIM models because they are being created. As I mentioned, 25% of the industry already does that, so we can have that information. So from the BIM model, we know how many stories, how many apartments. If they work with the schedule, we know how many people were supposed to be there working with the bricklaying or concreting works. So we can then at the end compare whether 6 people were supposed to be there in the apartment or on the level, and we can see like only 3 of them were there. So we can really measure then the real-time, real productivity based on visualizations. So if I may conclude, because it was already almost 20 minutes after us. So this methodology is based on the open exchange formats. So we focused on the IFC in this particular time, and the information about the position of worker, how long they were in the space, in particular in the apartment or at the floor, how long they were in the intended space. Like we can evaluate it, of course, within some disciplines. you need to supply material. There is not only the work, particularly or the time where you need to be, but this is also really important for those that measure productivity. And we can break down for the professions that I mentioned, and we can create, update, and standard hours. Standard hours are used in order to calculate how long the processes shall take, basically, the duration. And this really contribute us to estimate better and allow better decision making for construction management, because they can see if they are in delay, or they need more people or so on, or they know that, for example, their estimate were not really correct, and next time they can do better. And we can also motivate employees for performance. So this was it. Thank you very much for your attention. If you have any questions, I'll be glad to answer them.
Thank you, Tomasz, for your excellent presentation. Very clear. Are there questions? Please, one question here.
My name is Josip.
Okay.
My name is Josip from Faculty of Geodesy here in Zagreb, Croatia. I was wondering regarding the BIM being mandatory in the future. Is there going to be a minimal value of the building for it to be mandatory, or every new building will have to be built using a BIM during the construction and the project?
Okay, this is the discussion across the world. Basically, as far as I know, most of the countries, if they have a mandate, they're usually talking about the mandate for public works, only for public buildings, not for the private sector. But what we do in Slovakia, and we're not aiming to mandate, but we are seeking for the data for building permission. So if you give us the model, you'll get the permission faster because we have the data. Otherwise, you need to fill a lot of forms. No?
Yeah, I know.
So you can choose freely. You can give us a lot of data. You need to fill in manually, or you will hand over your BIM model and you can deliver it really easily or modify it. So yes, this is our approach.
Probably help with the faster adoption in the...
Yeah, of course, this will dramatically raise the level, but we're still seeking. This is the idea. It's not on the paper yet. We're preparing the strategy, but it's really going really, really slow.
Yeah, as most new things are.
Yeah. Okay.
Thank you.
Welcome.
Hello.
So most of the people here are surveyors or geometric people nowadays called, right? So where do you see the main role of surveyors and geomatics people in BIM modeling? What would be interesting for them? People who have offices and so on.
Yeah, of course, they need to be aware of the technology, where to fall, because they are within the stakeholders and the project participants. So they need to be able to read the data and to be able to deliver maybe new services based on if I see in Slovakia, the development, so the surveyors are able to offer new service with digitization of existing assets. They can do it without, of course, but at the end, usually the owners, they are asking for a BIM model. Not all of them, but some of them. But this is what you haven't been doing before. So this is as the new service, as I can see. But the other one, you would probably need to tell me how you see it, because I'm not the surveyor. So
yeah, it could be mostly on data collection and building 3D models and then delivering them outside to build really the BIM model and adding semantic segmentation and particular objects to this. So mostly with data collection, data processing, using laser scanners, total station, georeferencing them in the field so that you can deliver them, connect them with the data which is already georeferenced and so on. But yeah, and another question is, where do you see legislation going? So trends in legislation in terms of, will BIM become a must or required for countries or not, or how is this field? For example, in Switzerland, as far as I know, they decided that it's for all new buildings actually required.
Yeah, from the European perspective, there is no such a mandate on European level. So some people sometimes says on presentation that there will be mandate from Europe that every single European country will need to have all projects in BIM. There's not such a thing yet. And there probably will not be. The European Union led this on the national level. So you can decide, really, basically. You have the ability now, since 2014, you have the directive. Basically, you can mandate or require BIM on the public procurement project, okay? But it's on the country. I'm not really well informed about the Croatia, what is the situation here about the mandate. But in all countries in Europe, I know that basically, as I mentioned before, you can set mandate for public projects. You cannot send mandate for private companies. If you're a private owner, you can say, okay, you will draw everything on a paper. I don't even know or need AutoCAD or MicroStation or whatever, you know? So that's really, I want to be clear that every time we talk about regulation, we are talking about public segment only. Which, for example, in Slovakia, we have really low, from just to be, if you're curious, if I mentioned we have 24%, the adoption rate, if we're talking about infrastructural projects, it's only about 8%. So buildings, 32 or 33%. But the private sector, even though there is no mandate, there are developers and investors in Slovakia, they say, okay, if you don't do BIM, you don't work with us no more. They have books. They have exchange information requirements defined, and you need to really, if you're engaged, if you want to go to enter the tendering phase, you need to work with CDE, Common Data Environment, to be able. So there will be also maybe, it's not really complicated, but for surveys, it's good to know that Common Data Environment exists, how the process is behind works, and this. But I see the other works are. Will probably be done like you're doing now, because for you taking measurements, and if I don't know if I'm wrong, but you don't really care if it's the wall, it's made of concrete, or it's the wall made of bricks or whatever. For you, it's just the wall and has the dimensions you need to measure. You know, so maybe some of the data or most of the data from BIM model will not be interesting for you.
Thank you. It's very interesting, especially for the public sector and for infrastructure project. Here is maybe a low interest for BIM. Maybe we are all scared, but it's the future definitely. And do you know in Slovakia how many companies of private sector adopted BIM?
From the private sector, most of the adopters are from private companies. You know, the state has a usually problem with it, but we can take it from the report. I mean, we have the same report for Croatia, luckily, than for Slovakia, and if I recall, I have the same for Slovenia. It's fairly near, so we can compare that. If you're interested in data, I can send it over to you, and you can see what's the size of the companies, what's their focus. What part of them are surveyors?
Yeah, but because we are all interdisciplinary and we are all connected with all of those. Yes, we are measuring, but all our colleagues are doing some other things, and it's beautiful when you have project on one place and everything is archived, and you have everything for the next generation. Thank you.
Thank you.
Thank you. We have a nice discussion, but I have one short question. What is later after the construction? We are a profession, they are registering apartments. I'm interested in question, who is owner of any apartment you constructed? Is there any way to make data flow to the cadastral or such registers?
Okay, they're preparing it in Slovakia. You know, it's basically as-built documentation. It's easier to produce if you have BIM model, and then it's more
accepted from the state administration.
Yeah, but currently you still basically submit in old-fashioned way, so there is no BIM use in this as-built basically documentation. Okay. We can see there might be really progress, and the progress is there. The technology is already there. But in the state regulation, there is no basically requirement for that yet.
Okay, thank you, Tomasz, once more.
Thank you very much.
And we are going further. The next presentation is checking the geometry of building structures using building information models and point cloud. Authors are Jan Erdeli, Richard Honti, Aset Madiev, Tomasz Funtik, and Alois Kopacik. And the paper will present Jan Erdeli. Jan, the floor is yours.
Thank you very much. To be honest, I have to find my presentation. Okay, here I am. Thank you very much. Just to be clear, I'm a surveyor, so I'm going to talk about also BIM and the connection with some surveying tests, but I'm a surveyor, not as so much. So, yeah. No, here it is. Okay, probably you can see it. Okay, thank you very much. So, ladies and gentlemen, I'm glad to be here with you, and let me introduce our approach we developed at the Faculty of Civil Engineering, Slovak University of Technology in Bratislava, for the geometry check of the selected building structures using the data extracted from a BIM model and the spatial data collected by some effective data collection techniques, where the result is a kind of a point cloud. Basically, we don't need a point cloud, as we know. So basically, for some of our processes, it's enough just to have a set of points with XYZ coordinates, so 3D coordinates. But in some stage of our workflow, we are also using the radiometric data, but I will explain it in my presentation. I hope you can hear me clearly. But oh, I have something wrong. It's because I started it, but okay. I was.
It's okay.
Okay. Because the problem is that here I see something different than you see on the screen, but okay, that doesn't matter. Fine. As Tomasz already said, the information technologies enables for us nearly fully automation in a lot of processes in terms of building industry, of course. And the biggest contribution in the last decade, let me say, is building information, of course. Such a model consists of 3 parts. For us, as for a surveyor, there was a question. The most important part is the graphic data, the geometry. Of course, there are other parts, parameters, the information, documentation, etc., etc. They are also very important for us in terms of what Professor Roig asking some parameters, who is the owner, etc., etc. But in terms of geometry check and focusing on engineering, surveying, setting out, geometry control, as-built documentation, the graphic data, of course. What is maybe a little bit different, what is an advantage for us is how we can assess the data. When we are using, Tomasz already mentioned a common data environment, CDA. So a software using which we can manage all the data. And for example, as I'm a surveyor, I'm registered there, and there are some permissions. What can I do? What can I edit? What can I record there? By the way, this is the print screen from the common data environment, the d.o.o software we are using together in cooperation with a private company, actually, where I'm, as a surveyor, I'm registered, and I can access the data, and it's a print screen from real data, basically. So we can see that if we have a model with a high level of geometry, there's a lot of information, much more than before. Then we have just some PDFs or some drawings, and it's up to date. That's the most important thing. It's up to date. I can click on it, I can access it, and I know that, okay, that's the current version. Nobody will call me that, sorry, we have a new version, but you use the old one. And if we want, and when we take into account this amount of data and the quality of this data and the quality of the data we are able to collect with our techniques, laser scanning, photogrammetry, a lot of SLAM technology outside, So why not to put it together? Because if we are talking about some geometry inspection, so for example, of the wall flatness, let me say, what's the usual way? We have a straight edge and we're measuring the difference from the straight edge to the surface inspected, etc., etc. I'm not really a complex image about the geometry or about the surface inspected. So if we are able to put these data together, we can somehow to automate the processes, maybe not fully, semi-automated, but at least we have much more information about the geometry. And all the approaches, existing methodologies, methods, we can categorize somehow. Of course, there is a manual modeling or manual inspection. That's the most time-consuming, but the most more accurate, of course. But you have to manually select the part you want to inspect, and it needs a very good knowledge of the project. I mean, the S-plan. And of course, also the as-built data, not really effective, but very accurate. But then the automated or semi-automated approaches we can categorize into some other approaches. Let me say point-to-point, point-to-plane, feature-based, etc., etc. But always there is a comparison between the S-plan and S-built. So okay. So let's talk about our approach. I'm sure that here in this screen I'm lost. Doesn't matter. Okay. What is it? So we developed an approach where we combining the BIM and the point cloud, basically. It's for the verification of the parts of the raw structure. It's important to know we are not wanting to inspect like detail like windows, just the structural opening. Okay, so the walls, columns, rectangular or cylindrical columns and structural openings. What is the advantage? It enables also a verification of relative geometry. So the flatness, not just the position and the orientation, but also the flatness, the roundness, the regularity of the inspected part. Because we're using detailed segmentation, not just kind of that, okay, so this part belonging this one, and we just calculating some distances or something, but really detailed segmentation to be able to filter all the objects not belonging to the inspected surface, like, I don't know, sockets, curtain boards, paintings hanging on the wall, whatever. And of course, based on the results, we try to calculate some statistical characteristics of the results. And on the very end, we compare the S-plan with the S-build, and also we're creating some results or some comparison for the relative check. So let's go through this workflow. The first is the data collection. It can be, as I mentioned, it doesn't matter which technique you are using. Basically, we are using point clouds. In the ideal case, also with the radiometric information, so X, Y, Z, so the coordinates and RGB and intensity if we have, or if not, then for one part or just the basic segmentation is enough just to have the geometry, so the 3 coordinates X, Y, Z. Then in the next step, we extracting the data from the BIM model. For that, we are following the open BIM idea. So we are not using native formats or whatever, but we are using open exchange file format, which is the IFC, the industry foundation classes. It's fine for us because it's basically, it can be represented, it's a text file, so we can extract the data for walls, for columns, for the openings, the position, the location, orientation, corner points, dimensions, etc., etc. So all these data we need about the geometry. Of course, it's not so easy as I'm talking about it, but it is. Then the next step is the alignment of the point cloud, so the S-build model, let me say, with the S-plan, so with the BIM model. For that, we are using target-based registration, or I'm recommend to use target-based registration. Of course, the first step is the registration of all the point clouds for different stations of the different position of the instrument together, and then as a hole to register it into the coordinate system of the building using corner points, artificial target, whatever, if you have survey points on the construction site. And yes, what is important is that the registration error we used to calculate after some point called registration directly affects the results of the S-build verification when we are comparing the B model and the S-build point cloud. But it has no influence on the relative geometry inspection, of course, because it doesn't matter where the wall is. If it is a flat wall, it's a flat wall. And the next step is the segmentation of the modeling itself. So, of course, prior of it, we making some pre-processing. We calculating the normal vectors in each point of the point cloud using some planar surfaces from the k nearest neighbors. Then from these, according to these normal vector orientations, we're calculating the local normal vector variations because we want to identify so-called seed point candidates. So the points where we wanted to start the automated segmentation process. So some points that we know that, okay, this point is lying on a smooth part of the surface or a regular part of the surface, is not a corner point or something like that. Then for the segmentation of the fabrication of the models, so the flat models or the planar models or the cylindrical models, we're using model-driven segmentation, region growing method or model-based method. For the walls, it is a modified Ransack. But for it, on the first stage, we're using two criterion, a distance threshold-based criterion and a normal vector orientation-based criterion. It's important for us because we wanted to, of course, we wanted to filter all the objects which are not creating the surface of the wall. If let me explain it on the walls. Then for the cylindrical objects, we're using half transformation. So we're estimating all the parameters of the cylinder and segmenting final the points. And in the second stage, if need of the segmentation, if it's needed, we perform the detailed segmentation when we're using an Lagrangian evolving curve. When randomly placed curve, as you see, I hope so you see on the animation, then on the right-hand side from the OU, we are able to find the separate parts of the point cloud. So when we starting on the very first picture, we have the original point cloud. We can not see nothing there because there are some. It's, by the way, it's from a theater and door is covered by wallpaper. So on the first look, you can't see anything there. You just a wall, and of course some posters on the wall and some other objects. But the result of the distance threshold filtration is the right picture there. So you can see that, okay, then we see the contours of some other objects on the wall. Then the normal vector orientation based criterion creates for us a little bit wider areas and boundaries around these structures. And then when we're using our curve segmentation, the multi-channel curve segmentation, when we're using all the available channels, if we have just color, so RGB, then that's mean free channel, of course. But if we are talking about the TLS data, so we have also the intensity that we have 4 channels. So we perform a multi-channel segmentation, and the final result is the segmented point cloud without any other things on the wall, without the posters, etc., etc. And from that, we can create our deviation maps. So we expressing the results, or we representing the results using deviation maps and tables, of course, some numerical results, but basically with signed color maps on the left side, S-plane versus S-build, and on the right side, relative geometry. So basically the flatness of the wall in this case. And to demonstrate all of these, I have just 2 slides, so I try to be very short on the end, and I'm come to the conclusions. We scanned part of a residential building. By the way, the same what I presented the print screen from the common data environment. I choose just the part 5 different walls, and here are the results. We scanned we scanned the object with a laser scanner Trimble TX5 it was, if I'm right. Yes, it was. So but it's not the same. Important thing is that the level of the geometry of the model, of the BIM model, was LOG 300, which means that every single part, every single structural part is modeled as a separate system. It has its orientation, size, etc., etc. Even there are some deviations. I will show it, and you see the chosen part of the data on the slide. And now here are the results, the comparison of the as-planned, so the BIM model, and the as-built, so the segmented, the detail segments in point cloud. You see the planned position of the structural openings. So there is a difference between the design and the executed works. And what you see on the top, there is a approximately 10 centimeter thick layer of nothing. Something is missing, and it was because even if the level of geometry was 300, then the isolation panels were not modeled. They were not in the model, and there's the 10 centimeter thick isolation on the ceiling. So that's what is missing there. And here are the results from the relative geometry. So in this case, in the picture you see is the flatness of this wall. Yes. So this was our approach. And as you see, when we putting together the data, what is offered from the architects, so from the BIM model, and our spatial data, what we are able to collect with high efficiency. So we are able to create some automated approaches, some automated solutions. And just a note on our future work, as I'm from the university, so we are planning to put all these together into one algorithm in Python, and hopefully next year we will publish it for testing for the public. So we want to receive as many feedback as possible. Thank you very much for your attention.
Thank you, Jan.
I have my own.
Thank you, Jan, for your presentation. Now we have the time for few questions. Is there questions in auditorium?
Feel free to ask me whatever, or if not now, I'm here during the whole conference, so you can meet me outside. So, oh.
Hi, I have a question about automatization of segmentation of other objects than walls. Have you made any?
Yeah, so basically, So basically now we are focusing on the rough structure when we identify that it's in this phase for us, for these early stages, enough to handle with the planar structures, which walls, columns, etc. Cylindrical, so cylindrical columns, spherical, and basically that's it. Because we are not going to model some furniture or something. Maybe in the future, now not. But it's not just planar. Okay, so not just planes, not just planes, but also cylinders and this. What do you mean? How effective? I mean, okay, I know what I'm asking, but how to explain it? We have a study when we tested just the part of the algorithm dealing with this. So maybe we can send you or share with you some information. Of course, it was developed by step by step. So every single part was differently, separately and tested, etc., etc. Basically, we are also able, if we want, to put there some predefined diameter, not just to find random cylinders or whatever, but if I'm looking for, I know that this column has to be with the I can, because that part was previously used for some pipeline extraction, but it's not the case of the rough structure. You know, if even if in the beam model we have a, I don't know, diameter of 300 millimeters, because of some inaccuracy in the real world, it's not. So it's really not need to predefine some diameters or something like that.
And if you have a design model, can you find it in as-built measurement in a scan?
Sorry, once again, if I have as planned.
Yes.
Okay,
Can
that's
you
the beam.
use that diameter and then get the automated result?
It's, you know, it's possible, but because we want to identify the deviation from the S plane, it's not really smart, because I will put there a cylinder with the predefined diameter, but maybe in real world it's not. But what we are using is that, maybe I forgot to mention, that from the seed point candidates, when we starting the segmentation, it's not a randomly chosen point on the somewhere on the surface of the column, let me say, or on the wall, but it's calculated from the data extracted from the beam model. So we calculate it for the inspected surface or for the cylinder center of gravity, and the closest point from the seed point candidates is the start point. So it's not just randomly we are start to find all the cylinders, and then we will decide which one is the right column. So it's not like that. Based on the beam model, we're starting also the segmentation process. Yeah.
Great.
Thanks. You're welcome.
I don't see any hand. All right. So, and then thank you once more, Jan, for your presentation. We are going further. The next presentation is a 3D model with extended reality of Lausanne Cathedral. The presentation will be held by Matej Varga, and the authors of the paper are also Yamini Patankar, Nando Grossenbacher, Merlin Alfredson, Anja Weichbrot, Robert Flatt, and Andreas Wieser. Please, Matej, the floor is yours.
Thank you. Okay, thank you once more. Hello, everyone. I'm happy to present you the model, the 3D model with extended reality of Lausanne Cathedral. This was in fact a student project of 2 students. And the background is that Professor Flatt from physical and chemistry of buildings from ETH asked geosensors and engineering geodesy to build a 3D model for their projects. And therefore we found 2 students, master students who did it with help of a PhD student who did VR experience, and BIM model, which is still in the pipeline for working. To show you the object, this is the Lausanne Cathedral. Here you can see an interesting structure. Actually, it is already 850 years old and therefore prone to reconstructions and building works and so on. Here you can see a structure, and this one is equipped with geotechnical sensors to measure humidity of the cathedral, since the meteorological factors are affecting the cathedral structure. Actually, the construction material is sandstone, which is prone to long-term deformations and so on. And therefore, actually, the entire cathedral as an object is in part of monitoring the structure, how it deteriorates with time and so on. And therefore, they need a precise 3D model of the full cathedral. You can see two towers, so it's a pretty complex building. Especially here, you can see a lot of geometrical features. And the size is better if we compare it to a woman here, or to the car, or to the sign. So it's a pretty huge object to model.
Then I will present you the general workflow. It's more or less the standard, I would say, for any geodetic project. It consists from some planning, acquisition, data processing, then evaluation of results, and then finally visualization. So for planning, we had to get some permissions, access, prepare instruments, teach our students how to use instruments, and do reconnaissance. For permits, it was a bit hard because it is in the middle of the city of Lausanne, and we wanted to fly drones, especially a BLK to fly, which has a drone with which is a drone with a lidar. Afterwards, due to weather constraints and so on, we couldn't fly, so we didn't do it. But in essence, this was the preparation work. We had also one of the co-authors is a specialist in photogrammetry, so he gave us all a bit of the specialistic knowledge and experience from his side. Then we did data acquisition. It lasted 2 days. And as I said, we did only interior due to heavy weather. So primarily it was super windy and rain, and combination of those didn't allow us to fly and measure outside. But then we adopted on site and did more measurements, more photogrammetry, and so on. The field team consisted from 5 members, and we did both laser scanning and photogrammetry. In order to have control points and in order to georeference the models, we also had the reference field. We started from outside, from geodetic points, and established some with GNSS, and then got with a total station, total station and prisms inside. We set up some backup points and also georeferenced our targets. Georeferenced some targets which we established. So we had some natural targets, essentially geometrical features inside the cathedral. So the things which strike your eye like in a geometrical sense, and which you could isolate or see in the 3D model which you built very easily. So for these features, we estimated coordinates using targetless total station measurements. Of course, it was a bit of work. But this allowed us the full control of the quality of the model in geometrical sense. So the team consisted from 5 members. Yeah, 2 full days. Then we did data processing, consisted from alignment of the data sets, because as you might know, if you collect from different stations, you are going from the local station of your instrument. And if you want to combine different measurements, and you want in the end with both from cameras, which were 2 or 3 shooting in the same time, then from the laser scanner point clouds, you want to combine these data sets and therefore do the alignment using these reference targets which we established. During the processing, of course, there was a cleaning due to noise, external, internal, people walking there, or just the noise of the instrument, and some extra facts and so on. So data processing goes iteratively, in fact. So first you pre-process some, align, georeference, and so on. Then you do the quality control. Then you see if you're happy. Then you might want to change some things, see some false points, and so on. So it's not a straightforward process. And finally, the most important, which actually produced our results, is reconstruction of the model. What we did is building 3 models. The first model only from photogrammetry data or only from camera data. The second one only from LiDAR data. And then the final model, which we supposed is the most accurate one, the most realistic one, from combined photogrammetric and LiDAR data. Then we did evaluation, and we did cloud-to-cloud comparison. It's more or less straightforward, where you get few clouds. I said we got three and compared them mutual to see differences. I will show you the results, and then with these targets and references. In the end, also visual inspection is important. You can zoom in, zoom out to the model, and see especially those things which one finds interesting or relevant, and so on, to see how this was reconstructed and are there any problems. Of course, there are always some things which could be better. So in the next iteration, let's say, which we will maybe do, if we will have enough capacity, if there will be necessity from others, we would then make more denser measurements and so on, especially at the upper side of the cathedral.
yeah, I find very good contribution of this paper visualization, which is virtual reality. I will show you in the end. From the instruments, we use the Leica RTC 360 time of flight scanner. It has 360 degrees in the horizontal plane coverage and 300 degrees in the vertical plane. We selected the medium settings, so one can select either to go for the full details or less full details, and then balance a bit between time collection. Of course, if it's high detail, it demands more time, and so on. We selected middle settings, and the resolution is 6 millimeters at 10 meters. Then we used two full frame mirrorless cameras, Sigma FP and Nikon D3X, with the wide range lenses. We used tripod to stabilize it a bit and hopefully not have any vibrations in the pictures. Then we set up settings, and one must say that cathedral is not an ideal surrounding, because one cannot have artificial light inside, and inside it there are parts which are completely in shadows, but there are also parts where they're changing shadows, and also since we collected the data during 2 days, the light changed from one side to another one. Anyhow, we wanted to have the control of it, so we played a bit with the parameters and so on. Determined ISO setting at 800, then FO for the aperture, and with the shutter speed we played a bit, going with super fast shutter speeds, so that we don't collect any vibration and so on. We did control measurements with GNSS receiver and total station. This, you can see a nice infographics which cover all the steps after we collected the data. So we collected around 2,000 images, and stations for the laser scanner around 150. This brought around 500 gigabytes of data. Of course, in the reconstruction and cleaning, we had to shrink this to be able to even work with this continuously. I think I will not have time to go through all the steps. I would just maybe it's useful for most which software we use. So more or less one is judged when using the Leica equipment to one software, of course. So Leica cyclone register for getting registered scans, and also for cleaning a bit of the point cloud, aligning them, and so on. And then after building this, one can go outside of the Leica environment, exporting it to the E57 format of point clouds, also can adjust colors in it, and import it to the software for reconstruction. How we reconstructed is using reality capture. So all the building of the modeling was done there. You can see here the steps. So we first calculated mesh, then we simplified, downsampled it a bit, did the cleaning, checked integrity, topology, unwrapping, closed the holes, and so on. So this is a procedure which lasts, and it's more or less manual. Automatic tools doesn't work ideally, of course. They do a bit of the job, but one has to have the control of it. Then we did cloud-to-cloud distance comparison and visual comparisons. And then the last step which we did was creating the VR experience using the Unity. So the checking we did with the cloud compare, it's more or less standard for kind of the quality control issue, and it's free. Also, the Unity is free software. Okay, so now I got already 2 results, and here I want to show you 2 pictures. The first one shows the doors. The doors we actually scanned and measured much more denser with cameras and the scanner, and therefore here you have cloud to cloud compared. So the first cloud from the camera, from the photogrammetry, and the second one from the TLS. And here you can see a very good agreement, actually, especially here until the incidence angle become smaller. So we measured from the ground, and therefore, of course, that we can expect the agreement is much better on this horizontal level from which we measured. So there you could see that the differences between these 2 point clouds at the level of 1 millimeters or even below. We have some problems, of course, with here. Here we should maybe use a larger tripod, or we could already use the drone to measure this higher part. It's already 15, 20 meters, right? So not really ideal for ground level measurements. But anyhow, the mutual match showed the accuracy of 1 centimeter. Then we did the same for the interior of the cathedral. Here is the same comparison, so cloud to cloud between TLS point cloud and photogrammetric point cloud. And here again, you can see that the differences are at the level of 2-3 centimeters. Of course, one can see that as the above, as the higher elevation, the differences are larger. So of course, point spacing of measurements is smaller. Noise level also increases as the distance from the scanner and from the camera increases, and so on. So these are all familiar factors for people. Anyhow, also worth of mentioning is the agreement between the models which we built and control points, and these were on average 5 centimeters. So this is what we could say as the average measure of the full model. Okay, then I would like to show you actually the differences. It is more or less known that laser scanner will provide cleaner geometry or better geometry reconstructed, and that camera will provide good colors, right? Good radiometric information. And this is what we see here on one detail. So here we have photogrammetric model, TLS model, and combined model. So for photogrammetry, if we see the geometry, you could see, I don't know how much is visible here, but may I zoom? Okay, I will not zoom, but here you could see a bit of the noise, not a bit, but large amount of noise. If you could zoom in, you would see that actually windows, for example, here are not reconstructed as windows, so there would be problems with BIM modeling and so on, fitting some planes there, and so on. As expected, but of course, it's good to have it here. But texture information or color information for photogrammetry is photorealistic. So as we see it with eyes, it's almost identical, right? Then we have TLS model. Here, geometry is almost perfect, right? Here on this scale level, we cannot see any differences. Of course, if we would zoom in the model, we would still see some artifacts and noise. But here on this level, it really looks nice. And people who will do virtual touring through the cathedral will really not notice this. It's a high quality model. But since the camera on the laser scanner is not comparable to the cameras which were used for photogrammetry, the colors do not look photorealistically and nice. And therefore, we tend to exploit the combination, of course, not at the full extent. It's a research topic in essence and so on, but there is program and there's also software who can do it. One of those is reality capture, and then one could combine so radiometric information from photogrammetry and geometric information from TLS and get the really nice model both for geometrically and radiometrically. So you can see here, and with this one we selected then as the final model which we delivered. Okay, then I will just leave you a presentation, leave you a video in the presentation to see the result. Maybe we have time for the full presentation. So these are the doors, as I said. We scanned them fully, nicely, because the client wanted to see this. Now we will enter inside the cathedral. Here you could see some targets, which I mentioned. There were around 30 of them, I think. For those, we measured coordinates. Then here you could see the model. It's for those who are not professionals and so on, and for the purpose of visualization is very high quality model, or it will be efficient for the client who wants it. What you can see here are a bit of shadows. This is because of the reasons I mentioned. So this is like what happens in the cathedral, right? You get some lights from all around, and then these shadows are simply affecting the data. Of course, one can play with this and so on, even add artificial or remove. I would then. Okay, yeah, and for the final slides, I have VR goggles here. So if one wants to walk inside the Lausanne Cathedral now, please, here is my contact, and just contact me, or you can find me here, and we can set this up. It's a nice experience, especially for those who haven't already seen it. It's a very cool experience, I think. So please just contact me if you want. Thank you very much for attention.
Thank you, Mate. We have time for a few questions, please. Have you a question? Any question from?
Maybe I have just one short question, because I see such detailed model as this. So in terms of data, how it is big?
What's
in I don't know, in any phase of the production of the model, if you can maybe just somehow to describe the point cloud, I mean the amount of the data.
Yes, so the first model which we built from the data had 1 billion. So the first mesh model had 1 billion points, and then we drastically reduced it to 20 million, and then we worked with 20 billion. And the reconstruction with very good machines lasted maybe 24 to 36 hours, something like this. So it's very demanding. And then there is this question, right, how to approach it, whether segment by segment or what to do and when to merge it and so on. So this we handle, but one needs to have really hard machine to have this processed. Yes. A good thing is that software is prepared for such high resolution and data. So we had some problems, but essentially we didn't have like any kind of troubles with the software itself, which is a good sign, right?
Thank you. We have one question from Dario Panic, participating online. He asked, what was the number of stations for TLS?
Yes, very good question, actually. It was around 150 stations on the ground floor of the cathedral, but the absolute number is actually derived from the station to station distance, and we set this to 5 meters. So every 5 meters along the cathedral, we put the scanner and measured. And approximate distance between the wall and the scanner was also around 5 meters.
Okay, thank you, Mate. Once more, we should go in next presentation. The next presentation will be the quality of a mobile phone laser. The quality of a mobile phone laser scanner for creating 3D models of buildings. The presentation is from Josip Križanović, and authors are also Vinko Stančić and me.
Hi, everyone. My name is Josip, as Professor already has introduced me. This was also part of the student's work of our former student, Vinko Stančić, who is the second author of the paper. He has compared the coordinates of total station, TLS, and one of the most recent the most recent devices, the iPhone's LiDAR, which is available from the Pro versions. We have already today heard a lot about terrestrial laser scanners. There are many integrations of the laser scanners onto other devices. They are usually mounted on the tripod. Some integrations include mounting them on the vehicles, and some in the backpack, and then walking and scanning the surrounding reality. The most recent one is the integration of LiDAR in the smartphone. It is actually an iPhone. In 2020, it was introduced in the Pro versions of the iPhone and then the Pro version of the iPad as well. We have here some pictures. We have used the total station manufactured by Topcon. The TLS was a Photon 120 and the iPhone slider from iPhone 13 Pro. Some of the previous research indicated that Apple has developed the iPhone Pro with a LiDAR to improve low light focusing and to aid augmented reality, but application developers have come with an idea to develop applications for scanning, laser scanning the building and the reality around us. It is well known that terrestrial laser scanners are usually expensive, require high financial resources, elaborate logistics for managing the stations around the area for measuring, and in some cases, more sophisticated scanners require additional staff training. Some of the other disciplines, such as the preservation of cultural heritage, because of the high financial demands, urge the need for some less expensive solutions, so-called commercial off-the-shelf sensors. This is where the iPhone comes into play. Some of the authors have already examined the quality of an iPhone and other instruments. For example, iPhone and the terrestrial laser scanner for the calculation of the volume from the point clouds. iPhone was also tested against the unmanned aerial systems. That paper also tests the calculation of the volume. And since I already mentioned, there are many applications currently available in the App Store. Some of the authors have also examined the similarities and differences between those applications. In this work, we have used the application 3D Scanner app, and it's free of charge in the Apple Store, and most of the applications are actually free. Some of them include some paid options in the application. So in keeping with the preserving the cultural heritage, we have chosen the study area to be the Church of Saint Rocco in Stari Grad Hvar. It's an island in Croatia. The church itself is old several hundred years. It was built, I believe, in 17th century and contains a lot of details on its facade, stonework, on the steps, text, and other details. So it is very hard to capture these details using only classic instruments such as the total station. But as we have chosen the basis for our comparison to be the total station, we have firstly developed 3 traverse networks. I'm not going to list them right now, and have measured all the details of the church, as many of them as we could recognize. And we have taken the field sketches to mark the points and keep track of which point is where. The second survey of the church was conducted with a terrestrial laser scanner, as I already said, Photon 120. It took us around 12 stations to surround the church and scan the entire building, including the roof. So we had to take some greater distances to capture the upper parts of the church. As you can see in the figure on the left side, I believe, we had markers which were also measured with a total station. And during the processing of the point cloud, we have used target-based registration, and point cloud from the TLS was also georeferenced using the points surveyed by the total station. So the third survey of the church was conducted using the iPhone. iPhone has, I would say, a significantly lower range for scanning than the terrestrial laser scanner. some of the research papers indicated that the optimal distance for scanning with an iPhone depends on the application and is usually around 2 to 5 meters to get the best results. Because of the church height, we couldn't capture the entire church as we could with a TLS. So we have more detail in the lower parts of the building, which also had windows, stonework, carved text into the stones, and so on. We have totally captured, I believe, 6 point clouds with an iPhone. One part of the building was not accessible by foot at the time of the survey, so we have omitted that part from our further analysis. The point clouds of the iPhone were aligned using the identical points in Cloud Compare and georeferenced using the points from Total Station. Here we can also see the overlap of our details from the measured with a Total Station on the georeferenced point cloud from an iPhone. I should also state that the comparison results are heavily dependent on the quality of georeferencing, so I believe Vinko and I did our best to provide as accurate as possible georeferencing of the point clouds. Then we have conducted some statistical analysis. The first one on the left side is the average coordinate differences. The blue pillars represent the differences of a Faro TLS. As you can see, it is below 2 centimeters and is pretty much consistent on all of the axes, while the differences of an iPhone vary from 3 centimeters to more than 5 centimeters on the y-axis. Then we have grouped the coordinate differences in several ranges according to the centimeters. As you can see on the right graph, we have majority of the points with differences from below 1 to 3 centimeters. I would say some mid number around 3 to 5 and 5 to 10 minority. And in case of an iPhone points, we had some differences above the 10 centimeters and up to 20 centimeters. We believe these points were actually in the higher parts of the point cloud from an iPhone because of the scattering of the rays from a device, plus the uneven walking around the church and shaking the hand while holding the phone. We believe these are the gross errors in this range from 10 to 20 centimeters. We have compared around 150 points which were surveyed using the Total Station, even though we have surveyed several hundred points across the church. But since the range of the iPhone scanner is limited, we could only compare the lower parts of the building. We have also compared 2 point clouds, one from TLS and one from an iPhone. The majority of the distances were up to 5 centimeters, and these differences, which are even greater, are again in the higher parts of the facade and the building due to the scattering of rays. In the right figure, you can see the overlap of the 2 clouds. In our instrument for TLS only provided the clouds in black and white, while iPhone offers high quality, high definition point clouds in color. Finally, to conclude, as I already mentioned, our results are highly dependent on the georeferencing. We have conducted the analysis of differences of absolute coordinates. It might have been better to compare relative differences from the point clouds. The use of the iPhone slider should depend on the use case. We would not recommend it for the jobs or tasks with a high required accuracy. It is best used for I don't know, informal 3D models, some visual representations, and it's very easy to use, and you can literally carry the device in your pocket. The accuracy and range are also limited. There are no manufacturer's guarantees of the accuracy, and this all could be fixed with some GNSS integrations. I have personally tested the integration of an iPhone with a VDOC GNSS device. It provided, I believe, when compared to the TLS, around 2 centimeters differences. But these GNSS solutions are usually low cost and may provide false fixed solutions, so it should be taken with care when using them for developing models. That will be it. Thank you for your attention.
Thank you, Josip. We have time for questions. Please, questions.
Very nice presentation, Josip. Did you maybe use gimbal with iPhone?
What, sorry?
Gimbal, like to compensate for the movement of the iPhone?
No, the iPhone has a gyroscope and accelerometer inside, so it calculates your moving, but since the terrain is not entirely flat around the church and there are some vegetation like bushes and when you are walking, you can, I don't know, trip or something, and also your hand is shaking when you are, especially when you are trying to hold it as steady as you can.
Mm-hmm.
So we believe that also had an impact on our results.
Yes. I mean, I saw a video, maybe when there was a paper with using gimbal, and then it compensates for this, movements of the hand and so on a bit. And I recall that there was an improvement of maybe 10 to 30% because of just using, maybe not 30, but at the level of 10%.
Yes, I believe that because of the flexibility of such a small device, there will be in the future many more gadgets to improve its accuracy in the field of laser scanning.
Mm-hmm. And one more question, if I may. So iPhone has already 3 or 4 models, 3 or 4 generations of LiDAR.
Yes.
Are there any differences between them?
Well, I haven't examined the differences, but I believe the applications are growing even better for processing data and capturing the data. I don't know if the camera has changed anything in those versions because their initial intention wasn't for laser scanning. It was for augmented reality and improving the low light focusing. But the cameras on the iPhone are improving in every version, so I believe they will also address the LiDAR improvements if necessary, and due to the popularity of the device.
There is also time for one more question. When it's all, thank you, Josip, once more. I will then close this session. This session was 4 papers and all are interesting. We was listening from construction progress monitoring system, then mostly about the quality control at BIM applications, also quality control of this low cost cameras and LiDAR, and this can be maybe a future that we go more mobile with our instruments. That's for this session. Next session will start in half an hour. We have a coffee break now. In next session, we have deformation measurements. Chairman is Jan Erdeli and Vice Chairman Loris Redovnikovic. We have also 4 papers. I expect interesting presentation and come here again after the coffee break.
4 presentation on the plan, but actually somebody, mislim, Ante, you honest me that there will be 3 of them, but very interesting topic, which is deformation measurement and deformation monitoring. One of the papers are from the field of load test of bridges. We have some non-destructive testing of runways using, let me say, not really conventional, not non-conventional surveying methods, and also we have some laboratory test of a model of a column, if I'm right. So very interesting presentation, very interesting topics. Welcome in the conference room. Also welcome for our guests who are connected online. And let me introduce also my co-chair, who is
Boris Redovniković.
Thank you. It's just because of the pronunciation. And thank you very much. And he will help me with the Croatian language if it will be needed. Thank you much. So let's go. Let's do it. So our first speaker is, there's also a change, I think. It's Mrs. Anna Kosor. Yes. Yeah, it's right. Okay, thank you very much. And the topic of her presentation is, sorry, you are from the Faculty of Geodesy University in Zagreb and from the Institute of Applied Geodesy, if I'm right.
Yes.
Yeah, okay, excellent. I'm prepared. And the title of her presentation is Monitoring and Determination of Displacements and Deformations of the Main Span of the Pelješac Bridge by Load Testing. So the floor is yours.
Thank you very much for your introduction. I will continue in Croatian. Dobar dan svima. Danas ću vam prezentirati rad na temu monitoring i određivanje pomaka i deformacija glavnog raspona Pelješkog mosta probnim ispitivanjem. Da uvod ono što ćemo proći kroz tematiku ovog rada, neke osnovne tehničke podatke o mostu, program probnog ispitivanja, metodologiju i izazove, te pomake glavnog raspona Pelješkog mosta i ostvarene rezultate. Na ovoj slici desno možete vidjeti panoramski prikaz Pelješkog mosta. Što se tiče dosadašnjih istraživanja, most je uvršten u projekt cestovne povezanosti s Južnom Dalmacijom 1997. Prvi put je tadašnji dubrovačko-neretvanski župan Ivan Šprlje spomenuo ideju o izgradnji mosta. 2000. godine uvršten je u prostorni plan županije. 2005. i 2007. godine svečano su otvarani radovi na izgradnji mosta, a do 2010. godine tek je izgrađeno 3% prvotnog projekta. S obzirom da je Republika Hrvatska pristupila Europskoj uniji 2013. godine, 2015. godine je osigurano 85% sredstava za izgradnju mosta iz Europskih unije. Natječaj je raspisan 2017. godine, a 2018. je izabrana kineska tvrtka China Road and Bridge Corporation koja je dala rok za izgradnju mosta od 36 mjeseci s iznosom od tadašnje 2 milijarde kuna. Početak radova je u travnju iste godine, završen je most u siječnju 2022. kada je provedeno probno ispitivanje mosta, a pušten u promet je u srpnju 2022. godine. Pelješki most premošćuje Malostonski zaljev između Komarne na kopnu i Brijeste na poluotoku Pelješcu i tako je ostvaren cestovni kontinuitet teritorija Republike Hrvatske, te je teritorij napokon postao jedinstvena cjelina nakon dugih 305 godina. Što se tiče osnovnih nekih tehničkih podataka o mostu, to je ekstrados most s kosim zategama, takozvano više rasponskog zavješenog tipa s ortotropnom čeličnom pločom. Ukupna duljina mosta i pristupnih cesta je nekih 4 km, dok sam most je duljine 2404 metra. Imamo sliku mosta, ima 13 raspona, ukupno 12 stupišta, sa svake strane obale je postavljen jedan upornjak i jedan stup, dok se ostali stupovi nalaze u moru. Na 6 stupova su postavljeni piloni. Ovo je pobliža slika pilona, znači piloni su visine od 40 metara, imaju 10 parova kosih zatega, punog su presjeka, te most ima 148 čeličnih pilota koji je najduži od 130,6 metara. Ovo nam je uzdužni presjek mosta s prikazom upornjaka i stupišta te mjernim mjestima, dok je ovo poprečna dispozicija. Za potrebe dobivanja uporabne dozvole, a prije tehničkog pregleda mosta potrebno je provesti probno ispitivanje. Probno ispitivanje je provedeno u siječnju 2022. prema važećoj regulativi. Provela ga je katedra za inženjersku geodeziju, Sveučilištu u Zagrebu s Geodetskog fakulteta u suradnji s građevinskim fakultetom i Pippenbacher Inženjering tvrtkom iz Slovenije. Probnim ispitivanjem provjerava se ponašanje objekta pri statičkom i dinamičkom ispitivanju, utvrđuje se usklađenost s projektom, znači usklađenost zahtjeva kvalitete radova sa zahtjevima u projektu te podobnost preuzimanja probnog opterećenja. Ispitivanje smo proveli kroz 65 faza, koristili su se kamioni s poznatim ukupnim i osovinskim opterećenjem, svaki kamion je težio po 40 tona. Kamioni su se u ovisnosti o fazama opterećenja koristio različit broj, postavljali su se u zaustavni i vozni trak, simetrično i nesimetrično u odnosu na glavnu os mosta. Ovo su vam slike, znači, s probnog ispitivanja s kamionima. Što se tiče određivanja vertikalnih pomjaka objekta, njih smatramo najmjerodavnijim u ocjeni objekta, znači izdržljivosti, njegovoj kvaliteti te nosivosti. Uz vertikalne pomake objekta određivani su i pomaci, znači, vrhova pilona. Uvjeti za mjerenja nisu bili najidealniji. Što se tiče orijentacije stajališta na poznate točke, nije bila je omogućena jer je most de facto zatvoren, odnosno s pješačke strane podignuta je ograda u visini od 4 metra, te orijentacija na poznate točke geodetske osnove nije bila moguća i tu je već bio prvi izazov koje metode u određenoj fazi ispitivanja koristiti. Metoda koju smo koristili je modificirana metoda geometrijskog nivelmana, trigonometrijski nivelman, GNSS statička metoda, GNS RTK metoda u kombinaciji s inercijalnim mjernim sustavom. Instrumentari koji se koristio, znači precizni nivelir, totalna robotizirana stanica, Trimble R12 i inercijalni sustav, te Trimble R10 i Net R5 za bazne stanice. Rasponi prvi, drugi te predzadnji i zadnji određivani su modificiranom metodom geometrijskog nivelmana. Za treći i 11. raspon koristila se modificirana metoda trigonometrijskog nivelmana. Ovdje je trigonometrijski nivelman služio za određivanje korekcije stajališta nivelira, a raspon od 4. do 10. su mjereni sa GNS RTK metodom izmjere u kombinaciji s inercijalnim mjernim sustavom. Ovdje, znači, lijeva slika prva prikazuje nam, znači, geodetsku osnovu i crveno je iscrtano, znači, pristupne ceste i Pelješki most, a ove ostale dvije slike pokazuju bazne stanice na geodetskoj osnovi koja je uspostavljena još 2005. godine, a korištena je i pri probnom ispitivanju i za vrijeme izgradnje mosta. Što se tiče monitoringa samog objekta, još smo, znači, opažali vrhove stupova, Pelješki most s panoramskog prikaza, vidite s ove desne strane, vrhovi pilona pratili su se sa GNSS statičkom metodom izmjere, prikupljali su se podaci s frekvencijom 1 Hz, na Trimble R10 antenama, znači na 6 pilona postavljeno je 6 antena koje služe za monitoring sustava Pelješkog mosta. Nakon što su se odredile i prikupile koordinate vrhova pilona iz njihovih razlika visina, prije, za vrijeme i nakon opterećenja mosta izračunali su se vertikalni pomaci vrhova pilona. S obzirom da je most velike duljine, ima puno faza i kompleksnost ispitivanja, u nastavku vam prikazujem, znači, samu analizu glavnog raspona mosta i vrhova pilona. Glavni rasponski sklop, znači R7, duljine cca 300 metara, pri maksimalnom opterećenju opterećivan sa 16 kamiona. U 4 faze je provedeno ispitivanje ovog raspona. Znači, 2 su faze bile dok je most bio rasterećen, jedna faza je s maksimalnim opterećenjem, a još jedna faza kad je most bio opterećen s 2 kamiona. Izazov su stvarali piloni koji su bili visine 40 metara, te je zaklanjao se čisti horizont. Stoga smo izvodili mjerenje s GNS RTK metodom izmjere u kombinaciji s inercijalnim mjernim sustavom, kako bi se, znači, uređaj s integriranim inercijalnim sustavom omogućio se ukloniti nagibi instrumenta. U tablici vam je prikazan znači očekivani projektirani pomak koji iznosio 42,8 cm, a ono što smo izmjerili je 37,4 cm, što odlično korelira s projektom. Sljedeće slike prikazuju maksimalno opterećenje u fazi 34 glavnog raspona sa 16 kamiona. Znači, formacija je išla u voznom i zaustavnom traku po 6 kamiona i 2 kamiona simetrično. Ovo vam je prikaz znači s dronom. Za analizu pomaka pilona, znači most sam po sebi kompletno ima ugrađen monitoring sustav. U odnosu na core stanicu u okolini u gradu Metkoviću, u odnosu na nju stvara se virtualna kropostanica u okolini sredine mosta. Možemo pratiti ponašanje konstrukcije mosta, vremenske parametre, seizmičku aktivnost te samotrajnost mosta. Za praćenje vrhova pilona, što sam već spomenula, znači Trimble R10 su antene. Naknadna obrada je išla u TBC programu, PPK obradi. Za raspon smo gledali pilone na stupištu S7 i S8. Rezultati će vam biti prikazani u narednim slajdovima. Znači gledali smo odnosno na bazne stanice pomicanje pilona u smjeru 3 osi. Sljedeći prikazi znači odnose nam se na pilon S7 prve 3 slike i onda sljedeće 3 slike se odnose na pilon S8. Prikazujemo 3 osi E, N i H. Znači ovo zadebljanim svjetlo-plavom bojom, ne znam koliko dobro vidite, su kinematička opažanja. One su dobivena kao srednja vrijednost kinematičkih opažanja u odnosu na 2 referentne bazne stanice. Znači spomenula sam vam da su bile smještene jedna na kopnu, jedna na poluotoku. Crvenom horizontalnom linijom imamo statičko mjerenje, isto u odnosu na referentne stanice, dok tankom tamno-plavom linijom znači su podaci usrednjavanja. Znači gledali smo da su podaci usrednjavanja kinematičkih opažanja, znači za prethodnih i sljedećih 30 sekundi. Na ovom grafu na vertikalnoj osi nalazi se e-koordinata, okomito na nju nalazi se vrijeme koje smo proveli za opažanje. Možemo vidjeti znači pomak e-koordinate u fazama 34 i 35 kad je most bio pod opterećenjem. Sljedeći grafički prikaz znači prikazuje nam isto za pilon S7 za N koordinatu pomicanje te H koordinata. Što se tiče položajnog pomaka, on je bio 2 do 6 cm, dok je vertikalni za pilon S7 bio do 1 cm. Za pilon S8 to su malo manji podaci. Znači za E koordinatu je neki do 4 cm, a za N koordinatu do 6 cm. Što se tiče H koordinate, to je bilo nešto manje, do nekih pola centimetra. Ova dva grafička prikaza prikazuju vam pomak vrhova pilona S7 i S8 u odnosu na glavnu os mosta. Ovo je kompletirani prikaz glavnog raspona. U sredini raspona pri maksimalnom opterećenju pomak je bio 37,4 cm, znači da je došlo do slijeganja sredine raspona, a u tom slučaju piloni, vrhovi pilona S7 i S8 nagnuli su se jedan prema drugome. Na kraju, da vam zaključim ovu prezentaciju, Pelješkim mostom spojili smo teritorij Republike Hrvatske. Nakon dugih 305 godina postao jedinstvena cjelina. Norma pro kojom je provedeno ispitivanje je potvrđena, znači most je u skladu s projektom, kvaliteta izvedenih radova je u skladu s projektom, te most na sebe može preuzeti projektirano opterećenje. Izmjereni pomaci glavnog raspona, znači sredine i vrhova pilona, izvrsno koreliraju s projektiranim pomacima i za ovaj dio koristili smo GNSS metodu u kojoj je bilo moguće provesti ovo mjerenje, s obzirom da je projektom tražena subcentimetarska razina točnosti, to smo i zadovoljili. Hvala vam na pažnju.
Okay, thank you very much for your presentation. So, ladies and gentlemen, now we have a lot of time for questions. And also, I want to remember for our guests who are online connected that you can also ask, but just drop the message into the chat of the Zoom application, and we will translate it or we will manage it somehow.
Okay.
Yeah, there is a question there.
Pozdrav, Nikola Kraljić iz GP Krka. Čestitke na lijepoj prezentaciji. Pa zanima me, u početku prezentacije si spomenula da ste imali problema jer je stavljena čelična ograda koja je prekidala vizuru do poznatih točaka koje su izvan područja pomaka deformacija. Pa me zanima da li ste zbog toga izabrali GNSS RTK metodu i statiku koja zadovoljava uvjete ili je bio prvi plan opažati sa totalnom stanicom, ali zbog nemogućnosti vizure ste ipak izabrali GNSS?
Pa da, mislim na početku dijelove raspona smo ispitivali normalno sa niveliranom stanicom, a onda smo ove sredine, znači zbog velikih vizura, koristili GNSS.
Dobro, hvala.
Ništa.
Any other questions? Maybe, if I may, just because when we are talking about a job like this and load test, so it's about not just the measurement, but a lot of preparation, etc. Can you describe us just roughly what does it mean in this case? How many people? How many hours of preparation? Just you know.
It was a lot of time.
Yeah, I'm sure.
It was a lot of people. From faculty, it was 5 people. There have also from the other faculty and Pippenbacher engineering people, and for the bridge, for the just to find me a word, it was about 7 days. So it was really tough measurements, and it was a lot of people and a lot of time in this monitoring.
Yeah. So basically it's challenging also in terms of management, not just the measurement, but all the people, all the stuff, etc. So, okay, thank you very much. Are there any other? Yes, Professor Wunderlich?
Thomas Wunderlich, Technical University of Munich. I'm interested if you had some multipath influences from the cables, because your GNSS receivers on the deck must get influences from these reflected waves. Did you have some deteriorations in your material? How did you filter it?
We don't have.
So you think your material was perfect from the beginning?
Thank you.
No,
we make that in the TBC program in the PPK. How to describe it?
Because I remember some 20 years ago or so, we did some observations at the Rose Bridge crossing the Danube in the vicinity of Vienna, and there we had a lot of troubles with multipath effects. Yeah, so maybe a second time you look for some effects.
Of course.
On the other hand, the results are absolutely fair, yeah, and correspond to the design.
Yes.
Yeah? Okay.
Okay, thank you very much. Any other questions? Maybe regarding this, if you can show us, because you have some graph, I think, when the antennas were placed or some sketch of the bridge or something, just to explain maybe the question of professor. No, not this one, or sure. No, I mean the position where the antennas were located, the GNSS antennas.
Oh, of course. You think on this one?
On the bridge, if you have. I mean on the bridge, because I'm just want to. If you have one, I don't know because I don't see.
I'm not sure.
I have to be okay. Doesn't matter. Okay. Or with the pointer, just to show us if you have a picture of the bridge deck, I mean the main span of the brick, where approximately where the antennas, if you can point that there were or something.
Do you see a mouse?
držiš stisnuto malo miše duže, onda će ti se paliti.
No.
Yeah, of course, any help is
There
welcome.
also. We have our GNSS receiver in the middle of the deck, but next by the trucks, which is not good position. But we have 30 seconds measurements with the GNSS. We also have, which Anna didn't show, the TLS total station measurements and geometric level, also to check all the results at the moment.
So you took
Everything.
Time, it was 30 seconds.
Yeah,
Okay.
and we check it, everything that we had. Yeah. Right. No.
Okay.
More questions?
Any more questions? Or I'm done.
Okay, if there are no other questions, thank you very much once again for the presentation. And I would like to invite our next speaker, who is from Slovenia actually, and it's Boštjan Kovačić. Currently, if I'm right, an independent researcher. Okay. And the next two planned presentation will be stuck in one, but Boštjan, it doesn't mean you have now 30 minutes.
I don't know where it is.
But the floor is yours, and do you need some help?
No. You said I have 24 minutes. I have time. Okay. Thank you. Pozdrav svima. Najprije da se izvinjavim, ja ću pričati na hrvatskom koliko se još sjećam, studirao sam u Zagrebu, a ostalo sve iz mora što smo se naučili. Najprije isto sam se bavio ispitivanjem mostovima. To nam je bila 20 godina, mi je bio to trend na fakultetu kad sam još tamo radio i sve ove ispitivane mostove smo napravili u Sloveniji. Ja mislim tamo oko 300 i više mostova smo ispitili. Dakle, meni je bilo jako interesantno predavanje prije i mi smo bili kandidati za probno ispitivanje, ali nismo uspjeli u kandidaturi, ne? Tako da bili smo preskupi najvjerojatnije. Ali dobro, ne, jeftini da smo bili, dobro. Ne, ali to je bilo znanje sa autorima, smo radili i zajedno, tako da smo jedni druge nešto naučili, ali stvarno bilo mi je to interesantno. Sada smo se bacili u novu svrhu mjerenja pomaka i deformacija sa mom kandidatom koji je isto suautor ovog rada, Damjanom Dolerom. To smo radili za njegovu doktorsku disertaciju i tražili smo koja metoda bi nam bila najbolja za mjerenje aerodromskih staza, odnosno rujnih staza. Znamo, treba isto napraviti ispitivanja staza zbog oštećenja, zbog svega što je tamo. Metoda smo počeli razvijati u Mariboru, na aerodromu. Zašto baš u Mariboru? Jer tamo slijeti avion svakih 14 dana. Dakle, imali smo vremena ovu stazu premjeriti, sve ove metode testirati i pronaći metodu koja bi bila stvarno najefikasnija za staze gdje avioni slijete možda svaki 7 dana. Staza je napravljena bila nova, novi asfalt, sve su napravili, ali ispitivanje u Sloveniji nije zapisano u nijednom zakonu da to treba svake godine, recimo svake 2 godine napraviti neki monitoring. Oni imaju optički pregled, dakle voze se autom gore dole, nešto vide, ne, i oni papiri što su dobili stavi se negdje u stolicu i gotovo. Oni su to napravili i to je to. Ali nam je to bilo interesantno, gledali smo puno ovih filmova, gledali smo članke kako se to radi drugdje. I tako je došlo do ove ideje za doktorsku disertaciju da nešto novo napravimo. Problem kod ovih staza je da to treba napraviti jako brzo. Geodetska mjerenja treba da se naprave brzo, jer vrijeme kad ti otvore frekvenciju za mjerenje je prije 6 ujutro i onda poslije 9 na večer. Ne? Dakle, između kad je radno vrijeme aerodroma, pa ne samo aerodroma, cijele frekvencije, recimo u Sloveniji, ne možeš ostalim metodama mjeriti jer to su prevelike smetnje u frekvenciji. Dakle, potražiti metodu koja bi bila brza za ovakva mjerenja. Najprije što je bilo, ili ćemo sada ispitivanje napraviti na cijeloj pisti, dakle 3 km, ili ćemo samo izabrati koji dio piste. Iz ovih historijskih podatka mi smo malo to pogledali i vidjeli smo da je najopterećeniji dio ove piste je samo ovaj dio gdje avioni sletaju. Dakle, ovo mi kažemo touchdown zona, gdje oni udare na pistu sa velikom silom i ostalo naprijed nije više oštećeno, nema više. I sa druge strane isto, jer avion je sletao sa jedne i sa druge strane. Ne? Dakle, uzeli smo ovaj dio 500 metara i tamo smo počeli raditi ispitivanje, samo na ovom dijelu. Ali, nije problem u ispitivanjima. Znamo, geodetski to možemo napraviti mjerenjem, totalnom stanicom ili GPS-om, ako ti frekvencije dopuštaju. Problem je naprijed. Ti dobiješ oštećenja piste, ali šta sad naprijed? Dakle, model koji smo razvili sad dopuštava i druga mjerenja koji ide u isti informacijski sustav unutra i sada ove to premelje i naprave zajedno sliku gdje i koliko je pista koliko oštećena. Dakle, to je bio cilj ove dizertacije. Ovih ispitivanja je bilo puno. Kinezi to prave, recimo sa invalidskim vozilom, ide preko, tamo stave gore sve aparature, ide polako, vozi se gore dole, dobije cijelu snimku. Mi toga nismo imali. Dakle, treba uzeti ove metode koje su nam bile na raspolagu. Dakle, vidimo u dosadanjih ispitivanju bilo toga puno napravljeno. Mariboru, naš aerodrom, vidi se sad na slici. Dakle, uzeli smo ovaj touchdown zonu. Samo ova smo počeli ispitivati, jer nas je bio samo ovdje interes kako sad doći do rezultata. Mjerenja sa jednim mjerjem neće još ništa dobiti. Dakle, treba je to napraviti poslije 3 mjeseca, opet 3 mjeseca, 4 puta godišnje, da smo dobili neku sliku kako sad ove epohe ide jedna na drugu i gdje su sada ova mjesta i koliko je pista se u godinu dana oštećila. Ali, to je bio trend, ali sad je bilo napravljeno, prvo je bilo da se treba napraviti snimka cijele piste, to nam je kao bila referentna ploskva i na ovo sad smo sva ostala mjerenja gore lijepili. Ne? To je u programu MATLAB smo to napravili i kolega Damjan je to naprijed to razvijao metodu. U prvo što je bilo, treba je mreža. Napraviti snimku ovog dijela 500 metara, dakle na svakih recimo 2-3 metara, točka po točku i napraviti da dobijaš prvi grid, prvu mrežu, samo dijela gdje ćemo mi to mjeriti. To ti uzme najviše vremena. U Mariboru 500 metara nije bio problem, to se jako brzo napravilo. Vidimo, i to nam je bila ova prva mreža. Onda što je bilo, ovaj dio smo razbili na manje dijelove, da smo mogli sa drugim metodama napraviti još probna mjerenja da smo dobili neku usporedbu rezultata. Probali smo sa Dopplerim deflektometrom, ali je bio domet jako kratak, do čini mi se 25 metara, to nam nije bilo dovoljno. Ne? Dakle, ova metoda za mjerenje vibracija otpala. I sad smo tražili šta naprijed. Sa nivelirom, sa totalnom stanicom sve smo napravili mjerenja. Dakle, napravili smo jedne sekcije i sad smo nove sekcije počeli praviti sa matematičkom regresijom rezultate i na kraju rezultati svake ove sekcije su nam bili u 3D prikazu da smo dobili koliko je pista oštećena. Pa nije tako veliko kako se vidi na slici, to smo promijenili smo da se baš vidi gdje i koliko je na kojim mjestima. Normalno touchdown zona, samo tamo gdje letala sletaju, napravi ovo izboltinu unutra i to je problem. Kad je kiša, tamo nastane ovaj aquaplaning, a u Mariboru, kako sam kazao, trend našeg aerodroma je samo ova ultra laka avioni, skratko ovi sportska. Ne? Ovi ima, šta znam, 300-400 kila i kad je naljeti na ovaj aquaplaning, desilo se da ga okrenulo i prebacilo. Dakle, samo koliko je bilo ovo malo, bilo vode na pisti, već su bili problemi. Ali sa okom to ne vidiš. Ne? Možda kad je bila kiša bi trebalo napraviti okometrično mjerenje, ali u kiši niko ne izađe. Dobro, naša mjerenja naprijed. Dakle, ovaj dio smo uzeli, ovdje se sad vidi trend mjerenja i u Mariboru smo razvili ovaj model. Naša pažnja se došla do toga da stvarno sa ovom metodom možemo mjeriti, da su rezultati efikasniji, da su dovoljno točni i sad smo išli naprijed. obavili smo 2, 3, 4 članka na tu temu i odjednom zvone telefon i zove nas iz Bosne, isto ima aerodrom, da ako možemo doći izmjeriti pistu. Zašto? Tamo su sve još vojnički aerodromi i sad treba dobiti status međunarodnog. I za status međunarodnog treba napraviti mjerenja koliko su aerodromi statičko imaju nosivnost i ova metoda nam je bila interesantna, mislim je bila interesantna, nama je bila isto interesantna i išli smo to mjeriti u Tuzlu. Aerodrom je tamo, čini mi se, 2,8 km dug i jako oštećena pista bila. Sa GPS-om nije išlo, tamo nisu ugasili frekvencije. Sa liderom nije bilo moguće, sa dronom nemoguće. Dakle, rezultati su nam bili tamo oko 10 do 15 metara točni. Dakle, ova metoda nije. Onda jedino što je bilo, napraviti grid, opet mjerena, klasičnom geodetskom, cijelu pistu, 2-3 km i šta znam, 50-60 metara široko, treba napraviti mjerenja klasično. I ovdje, kako smo na jednom predavanju, mislim da je bilo u Opatiji, treba i geodetska kondicija. Ne? Dakle, to mjeriti, ne? I to je bio problem, jer ovi koji smo već 20-30 godina geodeti, nama to nije više problem. Problem je bio kod mladih. Ne? Znate kako zvoni telefon, Facebook, treba malo to pogledati. I onda se izgubi kojih 5 metara naprijed, nazad, lijeva, desna. Ne? Dakle, ovdje treba imati stvarno dobru ekipu. Ne? Dobru ekipu da se to napravi. Imamo opet, sat i pol smo imali otvoreno aerodrom, koliko možemo sat i pol napraviti. Onda treba sve maknuti. Sve instrumente, aute van iz aerodroma, sad čeka da dođe avion. Onda opet, kad otvore, možemo se vratiti nazad. I opet sat i pol vremena. Dakle, tako smo imali neke periode i u to vrijeme je bilo treba napraviti mjerenje. Ti si isto treba znati da sat i pol izmjeri toliko da sljedeći put prebaciš instrumente naprijed. Ne da se opet vraćaš na isto mjesto. Dakle, to je bilo u tem timingu jako puno mjerenja, stvarno hodane gore dole. Ne, to je bilo super. A svaki ima svog jednog koji je stojao pored nas da ne bi nešto ukrali na aerodromu. Ne? Tako da smo imali svoje osiguranje. Aerodrom je bio jako dug. Opet, sa ovim metodom ne možeš odjednom da napraviš cijeli aerodrom u jedno mjerenje. Dakle, isto smo ovdje napravili posebne sekcije i svaku sekciju smo mjerili posebno. Ovdje je bilo 5 sekcija, na 5 dijelova smo razbili cijeli aerodrom. Na ovoj slici pored vidi se pista i vidi se sve ove rulne staze pored piste, taksi staze, sve tamo gdje je slete avioni, gdje parkiraju, sve bilo potrebno izmjeriti, ne samo samu pistu. Dakle, ovo je bilo na kraju svaki dio isto po istom metodom, ovom registrijom izračunat i ovakve slike smo na kraju dobili. Ne? To je baš ova touchdown zona gdje se vidi sa crvenom najviše oštećena staza gdje udaraju avioni. Ali sada oprema koja nam bila na volja, robotska stanica, za mjerenje prizme, normalno to sve nam treba, GPS uređaj koliko nam je bio potrebno jer točnost je bila jako loša i osobno vozilo na kojeg smo pravili jedan trailer, jednu prikolicu bez amortizera, dakle to je bila sasvim dole na podu, na malim točkovima i gore su bile stavljene svi ovi senzori za praćenje. Dakle, vozilo, onda ćete vidjeti, vozi jako polako, u istom brzinom i vozi samo gore, dole u ovoj sekciji. Instrument ga prati i za svaku točku dobije koordinatu. Onda se ove sve rezultate naprave opet jedna površina, što se baci na ovaj grid što si prvo mjerio i dobiješ one pomake što se tražilo. Dakle, to je bila ideja od našeg Damjana što to napravio i sami napravio ovaj trailer, ne, i tako smo na ova mjerenja onda ovdje počeli raditi. Ali nije samo geodetski, dakle mi smo sad dobili ove crvena mjesta gdje su pomaci. Ne? I normalno, sad bi sad video slike bi bacio i gotovo. Idemo naprijed tražiti. Šta je sad tamo i zašto je došlo do ovih crvenih mjesta? I sad dođe druga metoda. To je malo geomehanička metoda koja dođe sa isto autom. I iza toga ima jednu prikolicu na kojoj ima, mi kažemo ovaj deflektometar, gdje su ovi batovi i sa različitim silom udara u pistu, u asfalt. Čini mi se 90, 120 i 150 ili 110 newtonova udara. Dakle, 3 puta isto mjesto udari i on dobije koliko vibracije, koliko duboko to ide. Ne? Dobije rezultate na različitim mjestima. Dakle, ako je bilo svugdje isto, bilo bi super. I treća metoda, gdje sad si dobio ove loše rezultate, dođeš još sa onim ultrazvučnim radarom i napravi snimku terena, snimku zemljine, tamo 10 metara dubine i dobiješ sastav unutra koliko u zemljini. Dakle, sve 3 metode treba da bude jedna pored druge. Dakle, jedni rezultati geodetski, geomehanički i radar. I sad treba to sve staviti u jednu vreću. No i to je bio trend što smo napravili ovaj informacijski sustav. Ova je pista još iz Tuzle, dakle ovih 5 sekcija, vidi se svaka sekcija posebno gdje je najviše oštećena. I pored toga, kad smo mi to završili, još sa ovim FVD-em, sa deflektometrom, bilo potrebno izmjeriti cijelu pistu. Dakle, on ide, recimo, po sredini, na svakih, recimo, kada znam što je bilo, 10 metara, stane, udari i ide napred. Onda ide od sredine 3 metra levo, 6, 9 i do kraja. Dakle, ovaj puta prevozi, za jednu pistu bilo je oko 8000 mjernih mjesti, samo za pistu. Dakle, puno rezultata. I obrada, što je bila na kraju, vidi se samo slika, ovo crveno, modro, crno. Ovo su rezultati ovih mjerenja i na istom mjestu vidi se gdje je pista najviše oštećena bila. Gdje su bili najlošiji rezultati. Dakle, ovaj dio treba da se sanira. Ovaj model, što nabre, razvijete sada rezultate, sve bacimo unutra. Geodetska mjerenja, geomehanička i radar ide kroz jedan takav proces i vidi se ako sad rezultati ide jedno na drugo, ako su rezultati ekvivalentni, onda ide naprijed. U drugi proces, gdje sada to sve matematički preračuna kroz ove regresije i izbaciti mjesta i koliko je pista oštećena. I to je baš dobro sad za ljudi koji nisu terenski, koji sad unutra samo sjede i kišom ne izađe, ove rezultate vidi. To je njemu sad sve na kompjuteru i on iz toga sad vidi koliko i gdje je pista oštećena ili je potrebna sanacija ili nije. I kada je potrebna sanacija. Dakle, njemu to sve javlja jer to su unutra protokoli, unutra su svi standardi ubačeni i sad on dobije na kraju rezultate. I na kraju ima ovo oštećenja od 0 do 5, koliko pista oštećena, dakle damo gdje je crveno, potrebna sanacija. Recimo zeleno, mjerenje, dok dođe do crvenog. Dakle, ima još vremena. I na kraju njemu izbaci rezultate u ovakvoj slici. Sad još za njega to super vidi, oštećeno nije, ali gdje i koliko? Ili da sad nazove opet geodete da mu dođe to istrasirati, da mu nacrta pistu gdje? Ne, nije potrebno. Ovaj program naprijed mu na slici piste oboji ovako, ova mjesta. I šta sad? Aha, tamo gdje su crte, na sredini vidi se crveno, ali točno gdje može ove podatke se prebaci u ovaj interaktivni kompjuter i ide samo po pistama ovim i baš ga vodi do mjesta gdje je oštećeno. Dakle, ne treba više geodeta, to njemu sada sve, ide po pisti i vidi mjesto oštećenja. Ali koliko je sada to oštećeno? Nama kaže crveno, dakle to je možda jedna mala izbokljena gdje je malo vode, ali po standardu ne, ili sad potrebno to sanirati ili još nije. No, to je baš ovaj raspravi što smo naprijed išli. Po našim standardima na duljini letve od 3 metra ne smije da bude na sredini više od, šta je bilo, 3 cm ovog pomaka. Dakle, na dužini od 3 metra, letva od 3 metra se postavlja gore i ako je na sredini 3 cm, onda treba sanacija. Ako ne, ne. Dakle, ko će sad ovo letvo ponašati po terenu i stavljati ovako na 3 metra? Ne, niko. To je baš standard koji je napisat, ali čini mi se da niko nije to ni probao na terenu kako to ide. Dakle, kod nas je to sad bilo ovaj rezultat. Geodetski smo dobili sliku mjerenja, gdje su ti pomaci najveći. Geomehanski sa FVD-em dobili smo rezultate koliko je tamo sada nosilnost stala. I na kraju sa georadarom smo još napravili šta je bilo ispod toga. Najgore je na ovim vojničkim aerodromima, svi aerodromi bili su minirani. Bili su minirani, ako bi došlo do bilo čega, oni bi to sad pustili u zrak sve. A ti sad tamo praviš mjerenja sa 150, lepo udaraš, ne znaš ako je sve bilo možda maknuto ili nije. Dobro, u Mariboru nije bio to problem, ali našli smo zašto to bilo, zašto došlo do toga. Dobro, ovdje baš piše ovi rasponi, mi smo dobili više od 3 cm pomake, ali letva nije bila duga 3 metre, bila na 2,80 i kaže to nije još dovoljno, može se još letati. Dok opet neki avion ne sleti na piste dole. Na kraju, normalno prvo, svaki aerodrom bilo bi potrebno svake godine napraviti monitoring. Metoda ima puno, to je samo bio jedan primjer kako bi se to dalo riješiti. Recimo da smo za to bilo potrebno za mjerenje mreže od 500 metara, recimo 2 sata, a za mjerenjem autom gore dole, čini mi se to bilo 15 minuta, da smo vozili 20 minuta za jednu sekciju. Ne? I to, i maknuli smo stvari i gotovo. Dakle, brzo to ide, ali ako je interes. Ne? Novi aerodromi, znam da to nije problem, još su u dobrom stanju, ali najgori su oni stari što su se samo asfaltom sanirali, samo nova stava, niko nije gledao što je bilo ispod toga. Ne? To je u Mariboru, smo onda stavljali gore ove letve od 3 metre u sve možne pozicije, da smo vidjeli sada gdje ako smo ispod ili na ovoj granici pomaka. Na ove slike sad vidimo šta je bilo. Pukotine, ove pukotine, one malo sa ovim sikom saniraju, ali ostane. Opet dođe ti voda unutra, kiša, ispod toga polako ti ovaj materijal ti ispire i polako se ti pista počne slegati na ovom mjestu. Ne? Ovdje ne bi bio nikakvi problem ovo samo napraviti novo. Ne? Samo sa ovim novim asfaltom bi se samo premazalo preko, napravio bi se to i gotovo. Tako, ako bi došlo sad do više sleganja, onda opet sve otvoriti, zatvoren, dobro, imamo 14 dana do sljedećeg aviona, to bi bilo vrijeme da se sanira, ali to ide polako. Ne? Opet, ljudi koji treba da to odlučuju, onda to ide na ministarstvo, za to vrijeme se mijenja ministar i opet idemo snova. Ne? Tako da ide to polako. Čini mi se da to je svugdje ista priča, ali mi smo ovdje, trend našeg bila samo to da svi geodetski rezultati, mi uložimo jako puno truda i vremena za naša mjerenja. Svi idemo, to je sve točnije, najtočnije što moguće, oprema je skupa, a da naši rezultati stvarno negdje ne ostaje onda u predalu negdje unutra, da se baca i niko više to ne vidi. Dakle, bez veze nešto se mjeri, onda ti isto plate, satove što si potrošio i to je to. Ne? Tako da to je to bilo kod naših mjerenja, malo da vidite da je trend i u nečem drugom, ne samo više u mostovima. Ne? Hvala za sada.
Okay, Boštjan, so thank you very much for your presentation, and now we have time for questions. Are there any questions? Once again, for those who are connected online, just drop a message into the chat if you have any questions. If not, or until you, I have one. This is a kind of crosscraft, let me say. When you collecting all this data, if I understand correctly, then put all this data and the results in some system according to your flowchart, and there is a decision-making procedure, right?
Yeah.
And in terms of decision-making, how it is works? I mean, from the delivering of the results of the measurement till the decision of everything is correct or something is happened, because it's like different levels of decisions. How long it takes or how it is works?
Super is if you measured every year 4 times, so and winter and summer and per year is 4 measurement is enough for this. But then you must every year replace this measure. So maybe next 10 years.
No, I'm not asking about the frequency of the measurement. It's clear. It's like some for 4 times in a
yes.
every quarter of it.
Every 3 months.
Okay, but the decision making, who make the final decision? Okay, so these are the correct results and nothing happened, or how it is working? If you have any information.
Yes,
about it.
the Ministry for Infrastructures is in Slovenia.
So all this data you have to deliver to send them.
Yes.
There are some people who will study all the results. So it takes.
The first is the chief of the runway. This is the first.
Okay.
Okay. He must this results shown and sent to another step. Another step is the ministry.
Okay.
Okay. But on the ministry, it's not the people who understand this. Okay, because it is not from geodesy or geotechnics. It's only from politics comes. Okay.
Okay. Thank you.
Maybe it's in another country it's the same this in Slovenia.
Yeah. Thank you. Any other questions? Okay.
Evo, ako nema pitanja, ja bih se prvo zahvalio, jako zanimljiva prezentacija i svidjelo mi se posebno ovo kad ste rekli da mladi nisu toliko za trend, vi stari ste se rastrčali, znači ove klasične geodetske tehnike, ali na kraju onda ispada da su zapravo ovo kasnije mladi napravili za mlade. Jel? Ova baza podataka je ovo da se zapravo skoro vozite i skupljate podatke.
To je baš, sad se to malo polaga na studente koji su ovdje, nije samo studij. Ne? To što naučite za ispit, to je to. To tako zaboravite sljedeći dan. Mi isto tako ne znamo sve na pamet. Dakle, učite za sebe, učite za naprijed. Šta napraviti ako ne ide? U geodeziji nema izraza ne ide. To si zapamtite. Uvijek treba naći rješenje. Uvijek rješenje. To smo pričali, ne, Ante, oko toga puno. Ne, oko geodetske kondicije, geodetskog, ne znam šta bi to bila. Dakle, to radi se sad za sebe. Isto to smo mi sad izmjerili. Možda, ja neću to dočekati da se sanira neki aerodrom, ali to će mladi. Šta će sad ovim rezultatima? Dakle, radite to za sebe sve. Ne treba sad gledati ova desetinka milimetar, samo treba napraviti. I nemate imati pored toga telefone, najedite se prije, stavite u džepeve neku drugu studentsku hranu, jer to se mjeri, kad se mjeri se po 12 sati i više. Nema pauze. Nemojte se žuriti na randi ili nešto drugo, to zaboravite. Na terenu je na terenu i bolje napraviti u jednom sve, nego ide 10 puta na teren. I napravi možda malo više, jer ćete neko za mjesec dana pitat, imaš možda one rezultate, još onog dio što si mjerio, joj nemam, opet na terenu. Sad si bio tamo, pola metra više bi izmjerio, imao bi rezultate. Dakle, uvijek pravite nešto na rezervu. To se vam polaga. To je naša iskustva koje smo dobili za ovo vrijeme.
Još jedno kratko pitanjce, jeste našli ove mine ispod stvarno?
Ne, a sad nas čeka sljedeći aerodrom u Bosni, tako da nadam se da na sljedećoj konferenciji se opet vidimo. Ako nećete samo pročitati, opet geodeti stradali, kod mene. Dobro, puno hvala svima.
Okay, I wanted to ask if there are other questions, but obviously Boston is okay. Thank you very much. Okay, so last but not least, I would like to ask Professor Zlatko Srbinovski from the Faculty of Civil Engineering, Science, Civil and Method Use University in Skopje, from North Macedonia. Welcome. And the title of his presentation is the determination of the deformations of the Antonini column model in laboratory conditions. So some laboratory test of a sculpture, if I'm right. So Professor, the floor is yours. If you need any help with the technique, just tell us.
Some help will be fine.
You want to play this or something else?
Slobodno vi hrvatski, ja da. Ali to nije moja prezentacija. Evo, Srbinovski gore.
Ovo je prvi,
da. Dobro. Evo, nakon slovenačke verzije hrvatskog jezika, kolege Boštijana, slijedi makedonska verzija hrvatskog jezika. Tako da se nadam da će to biti simpatično malo ovako auditoriju. Dakle, ja sam Zlatko Srbinovski, dolazim sa katedre za višu geodeziju Građevinskog fakulteta u Skoplju i koristim ovu priliku da pozdravim organizatore na izuzetnoj organizaciji Simpozija inženjerske geodezije. Naša prezentacija je u vezi jednog našeg malo starijeg projekta, ali meni jako dragog, pa smo se odlučili da uradimo rad i prezentaciju namijenjenu za ovaj simpozij. Naime, radi se o ispitivanju deformacija Antoninijevog stupa koji se nalazi u Rimu, realizovanog kroz model u određenom mjerilu, izgrađen u našem institutu za zemljotresno inženjerstvo i inženjersku seizmologiju. Dakle, ispitivanje kvaliteta stupa u laboratorijskim uvjetima, što daje neku posebnu težinu samom tom mjerenju, geodetskom mjerenju, imajući u vidu da su laboratorijski uvjeti uvijek malo skučeni, vrijeme je uvijek problem i tako dalje. Dakle, radi se o stupu imperatora Marcusa Aureliusa, koji se naziva Antoninijev stup, koji se nalazi u povijesnom centru Rima. Vjerujem da je većina vas bila u Rimu, meni je to omiljeni grad. Nalazi se na Piazza Cologni, to je baš onaj centar centra, na nekih 200 metara od Fontane di Trevi, još toliko od Panteona. Izgrađen je koncem 2. stoljeća naše ere, izgradio ga je imperator Commodus, koji je bio sin Marcusa Aureliusa i tu možemo vidjeti na ovoj slici da je čitav stup, odnosno njegovi cilindrični segmenti, valjkasti segmenti, da su obrađeni sa ilustracijama koje ilustruju pobjede velikog imperatora Marcusa Aureliusa. Tu su robovi koji su uzeti nakon bitaka i tako dalje. Ono što je ovako interesantno za istaći je da ovaj stup ima svog dvojnika. Nije to digital twins kao što je sad moderno, to je pravi, pravcati dvojnik u stupu, Trajanovom stupu koji se nalazi, evo sad možemo da, bilo je neka crvena tačkica, kako se to, ili... Aha, ne, ništa, ajde. Znači, evo ga, Trajanov stup se nalazi, samo vi dajte, Trajanov stup se nalazi odmah preko puta Vitorijana, znači spomenika te velike zgrade Vittoriju Emanuelu, nakon Rimskog foruma, znači na 100 metara od njega, a evo ga Antoninijev stup, evo ga Panteon, tu je Fontana di Trevi. Oba stupa su udaljena nekih 600 metara između sebe. Evo, s desne strane možemo vidjeti stup imperatora Trajana koji je izgrađen nekih par desetljeća ranije nego što je Antoninijev stup. Na vrhu Antoninijevog stupa u 16. stoljeću je postavljena figura Svetog Pavla, a interesantno je da je na Trajanovom stupu postavljena figura Svetog Petra i oni su okrenuti jedan prema drugom. Sam stup je visok nekih 40 metara sa promjerom od 3,6 metara i izrađen je u poznatom italijanskom Rose Carrara mramoru. Interesantno je da Antoninijev stup, da je u toku ovih skoro 2000 godina pretrpeo značajne štete tokom zemljotresa i da je na njemu vršeno više sanacija. Prva takva poznata sanacija je koncem 16. stoljeća koju je finansirao Papa Sixtus V. A također interesantno je da Trajanov stup je u relativnoj ili u apsolutno dobroj kondiciji. Baš ova naša mjerenja su bila u funkciji zadnje restauracije Antoninijevog stupa. S tim ciljem u našem laboratoriju, to je laboratorij Instituta za zemljotresno inženjerstvo i inženjersku seizmologiju, koji je sastavni član našeg univerziteta Sveti Kiril i Metodij, izrađen model u mjerilu 1:6 i on se sastojao, kako se može vidjeti, ja se nadam da se može vidjeti s desne strane, od nekih 25 segmenata, od kojih je par donjih, 6-7 su kvadratičnog oblika, znači prizmatičnog oblika, dok je 17 segmenata ili 18 segmenata sa cilindričnim oblikom, uključujući, ajde, evo sad, uključujući i ovaj mali segmenat koji tako, igra ulogu statue Svetog Pavla. Ovo je klasična inženjerska geodezija, možda u principu ono što je profesor rekao, profesor iz Bona na uvodnom pozvanom predavanju, to je bilo prije 2014. godine, tako da su se analize i sama mjerenja radila na diskretnim točkama. U principu ima više razloga zbog čega je to bilo tako. Znači, mi u tom trenutku nismo raspolagali ovim suvremenim geodetskim tehnologijama. Kada vidite instrumente koje smo koristili, vjerojatno će izazvati osmijeh na vašim licima, pretpostavljam. Međutim, ja sam prilično uvjeren da to ni danas ne bi moglo baš tako lako ići sa suvremenim tehnologijama zbog toga što je pred nama bio postavljen cilj da dobijemo tačnost unutar 1 milimetra. To je prva ovako značajnija prepreka, a druga prepreka je bila fizička prepreka zbog toga što je oko stupa bila izrađena ograda, žičana ograda koja je pokrivala djelimično taj stup i teško bi se to moglo izvesti mjerenjima, recimo ovim novim tehnologijama. Bilo kako bilo, na svakom od tih 25 segmenata postavljene su po 4 tačke u gornjoj i donjoj zoni, što znači ukupno 200 mjernih točaka je bilo reprezent ovog modela Antoninijevog stupa. Sa ciljem mjerenja tog stupa postavljena je mikrotrigonometrijska mreža, to je klasični geodetski četverokut koja je bila izmjerena preciznim i u tom trenutku i u današnjem trenutku instrumentima Leica TC 2002, to su krasni instrumenti iz prve generacije, ali veoma precizni. I nakon mjerenja mreže postavljena su 4 instrumenta koje se nisu micala do kraja mjerenja. Bio je to, profesore Boštijan, dugi dan, kao što ste i vi sami rekli. Znači, mjerilo se sa svake stanice po 100-tinjak točaka, u 2 girusa, u 3 serije, tako da bilo je dosta tih mjerenja. A mjerenja su izvedena sa 2 Leica TC 2002 i 2 Wilda T2. Mlađi od vas sigurno i ne znaju koji je to instrument, to je divni, klasični geodetski instrument sa sekundnom preciznošću mjerenja horizontalnih i vertikalnih kutova. Mreža je izravnata kao slobodna mreža i pri tome je korišten jedan naš dragi softver, recimo Geonet. Nakon toga su uslijedila mjerenja na stupu, na modelu Antoninijevog stupa i ukupno je urađeno 3 epoha. Prva epoha je bila prije testiranja, druga epoha bila nakon testiranja sa simuliranim zemljotresima malog intenziteta do 1,15 G, a druga epoha, odnosno treće mjerenje, serija 2, je bila nakon simuliranih jakih zemljotresa sa 0,4 ili 0,40 G. Ja se još uvijek živo sjećam te serije kada se toliko stup ili model njihao da je gotovo udarao u ogradi, što bi značilo da se od svoje ose da je odstupao nekih skoro metar. Tako da je za nas koji smo stajali na 6 metara od tog stupa i probali da to mjerimo, nije bilo baš najprijatnije. Po projektnom zadatku koji su sastavili kolege seizmolozi iz instituta, znači to je bila jedna velika grupa, znači interdisciplinarni projekat, zato mi je i posebno drag. Znači to su seizmolozi, građevinski inženjeri, konstruktori, betondžije i geotehničari. Oni su od nas tražili visoku preciznost, 2D preciznost, ne 3D. Zbog čega? Zbog toga što to su betonski segmenti bili. Betonski segment se ne može vertikalno deformisati bez horizontalno da se pojavi pukotina. Takve pukotine se nisu predviđale i nisu se desile. Tako da što se toga tiče bilo je sve u redu. Nakon toga je uslijedilo određivanje deformacije ili pomaka segmenata. To je bilo predviđeno da se uradi kroz centre tih segmenata. To su neki izrazi za određivanje P i Q, odnosno nekih Y, X koordinata centra segmenata u nekom lokalnom koordinatnom sustavu definisanim sa našom mikrotrigonometrijskom mrežom. Dovoljno je bilo iskoristiti prostor, aritmetičku sredinu, zbog toga što iz 4 tačke možemo odrediti 4 kombinacije sa kojih se definiše centar kruga. Tako da kvaliteta izrađenih segmenata je bila prilično visoka, tako da su ta 4 određena centra po svakoj horizontali bila unutar 1 milimetra, što je bilo više nego pristojno. Samo određivanje pomaka segmenata se odvijalo kroz određivanje pomaka centra tih segmenata ili centara tih segmenata po 2 lokalnih osi, kao i ukupno pomjeranje DS, ovdje tako prikazano. I evo kako izgleda tabela sa jednim dijelom tih rezultata. Može se vidjeti, znači, nulta serija je serija koja je urađena prije testiranja. Prva serija nije prouzrokovala gotovo nikakve deformacije, budući da se one nalaze unutar pola milimetra, dok je druga serija bila ono pravo, što bi rekli, tako da su deformacije bile reda veličine oko 12,5 milimetara. Sad ako se to skalira 1x6 i to ne ide baš tako direktno skaliranje, to su značajne deformacije. Naše zadovoljstvo je bilo veće s time da su to deformacije koje su oni manje više predvidjeli i dobili su potvrdu svojih predviđanja. Govorim o kolegama seizmolozima i građevinskim inženjerima. Ono što se može vidjeti ovdje je da se gotovo čitavo odstupanje odvija po Y osi lokalnog koordinatnog sustava. Y os je bila postavljena u pravcu simuliranja zemljotresa, tako da nije bilo iznenađenja u vezi toga. To su neki grafički prikazi. Nažalost, ti podaci su mi negdje izgubljeni kroz tih par kompjutora koje sam promijenio u međuvremenu, tako da nemam puni obim tih podataka da možemo izraditi bolje prikaze, tako crveno, plave, zelene, koje se šta gdje premjestili i tako dalje, ali u principu vidi se da su to pomaci u pravcu Y osi, to se i na tlocrtu može vidjeti. Sekundarni produkt je bio određivanje rotacije segmenata, to se isto može uraditi na osnovu promjene direkcionih kutova dijametralno suprotnih točaka. Rotacije su bile moguće zbog jedne interesantne stvari. Naime, kad je stup urađen, kroz njega su bile provučene čelične šipke ili željezne šipke. Nakon toga, tokom vremena, stup je demontiran, te su šipke izvađene, iskorištene za izgradnju oružja, za odbranu Rima ili već čega. Nakon toga, sad su samo posloženi ti segmenti, zato se može javiti rotacija. U drugom slučaju se to ne bi moglo javiti kao tako. Bilo kako bilo, segment koji je imao najveću položbenu deformaciju imao je i najveću rotaciju, a ta je rotacija bila 1 stupanj i 40 minuta. To je segment broj 19 pri vrhu negde modela Antoninijevog stupa. Generalni zaključci ove prezentacije upućuju na značaj inženjerske geodezije u određivanju deformacija inženjerskih objekata. U ovom slučaju je to malo specifičnije zbog toga što se radi o modelu jednog veoma značajnog kulturno ili spomenika iz kulturno-historijskog nasljedstva, u ovom slučaju Italije pa i svijeta. Evo, s ovom krasnom vedutom iz 17. stoljeća na kojoj je prikazana kolona Antonina i čitava pjaca Kolonje, ja vam zahvaljujem na pažnji.
Thank you very much for your presentation. And I would like to ask you to make questions, if there are. Yeah, okay, there is. But please use the micro because of the translation.
Hvala na vrlo zanimljivoj prezentaciji i jako zanimljiv projekt. Pitanje, znači, kad ste pripremali mjerenje, jeste provjerili instrumente i kalibrirali ih? Kako ste to riješili?
Apsolutno da. Znači, nije se radilo o onoj klasičnoj kalibraciji u smislu, to su male duljine. Znači, razmak između točaka je bio nekih 12, recimo, do 15 metara. Znači, nije što se tiče duljina. Što se tiče kutne točnosti, sve je bilo pod kontrolom. Mi radimo s vremena na vrijeme one klasične kalibracije, a prije svakog izlaska na terenu moramo provjeriti optičke viskove, to je pod obavezno čak i kod manje zahtjevnih radova.
A jeste li primijetili razlike između dva instrumenta? Da li je tu postala nekakva sistematika ili nešto? Jer ako stari instrumenti i tako dalje, postoji mogućnost da odu u različitim smjerovima ili da dođu neki efekti koji... Pa jeste li tu neke probleme vidjeli?
Ne. Znači, sama mreža je izmjerena jednom totalnom stanicom. Nije bilo vršeno upoređivanje dvije totalnih stanice.
Aha.
Da, a onda je uslijedilo mjerenje kutova, to su veoma precizni instrumenti. Evo, za ilustraciju vi već pretpostavljam da to znate. Jedna kutna sekunda na 200 metara je 1 milimetar, na 20 metara je 1/10, na 6 metara koliko smo mi bili udaljeni od stupa, to je 0,03. Tako da mi smo prilično, recimo, lagano, uz dosta truda, dobili traženu točnost koja je bila svakako unutar milimetra.
Za koju razinu vjerojatnosti? 1 sigma, 2 sigma, 3 sigma?
Nismo vršili takve ispitivanja, to je urađeno softverski, znači izjednačenje, imamo rezultate tog izjednačenja koje ukazuju na preciznost. Ne mogu vam tačno reći jer ne znam pozadinu softvera, ali znači, srednja pogreška je bila oko 0,3 mm.
Ok, hvala.
Hvala vam.
Okay, there is...
Čestitke od mene na lijepoj prezentaciji. Pa zanima me, rekli ste da je model stupa 1:6, je to i težina isto bila odrađena u 1:6, neka procijenjena težina? Jer vidim da ste tu radili betonske elemente, a pretpostavljam da je kameni stup, da je stup u originalu kameni. Pa me zanima da li je težina bila...
Pretpostavljam, za to su bili zaduženi. Rekao sam da je to bio neki ovako interdisciplinarni projekat. Pretpostavljam, sad ne bih vam znao tačno reći specifičnu težinu betona nasuprot specifičnoj težini mramora. Ali pretpostavljam da je vođeno računa o tome, ili ukoliko to nije, kako bi mi rekli, red veličina, onda je to softverski, pretpostavljam, uzeto u obzir oko interpretacije deformacija.
Professor Wonderly?
Thank you. I have a similar question. What was the pre-knowledge of the interior of the real column? Yeah, it is marble, but how are the segments fixed together in reality there? You said you had some steel in your model, but there won't be steel in that historic column.
I don't know if I was translate correct. The original column have a iron rods. Yes, but they are removed, I suppose, during the Middle Ages, and because of that, our model also doesn't have vertical connection between the segments. That's why we have a rotation of the segments.
Evo, može. Hvala na prezentaciji, stvarno jako zanimljiva tema po meni. Evo, ako sam ja dobro shvatio, samo bih htio provjeriti, znači vi ste određivali koordinate 4 točke kružnica segmenata, je li tako? Znači određivali ste ih presjekom pravaca, presjekom naprijed, je li tako? Kako ste označili točke na koje ste mjerili sa 2 stajališta da bi 2 instrumenta pogodila, odnosno vizirala istu točku?
Da. Urađene su, nisam to u prezentaciji umetno, urađene su specijalne markice koje su bile nalepljene na segmentima. To je križ sa minijaturnim kružićem sa bijelom pozadinom. Tako da se izuzetno dobro vidi, ta pozadina promjera nekih 0,5 mm, ali sa takve blizine se to može jako dobro primijetiti. To je nalepljeno i čak nije u principu ni bilo jako važno da to bude precizno nalepljeno. To je otprilike 2 dijagonalna na 2 dijagonalna, ali kad se to posloži, kad se određuju centri, bilo gdje da stoje te 3 točke, one određuju jedan centar.
Hvala.
Hvala.
Thank you. Are these results what you presented in accordance with the expectations? I mean, did you have any theoretical values of the shift of each parts or not?
Yes, as they told us, our colleagues, seismologists and civil engineer, the expectations are achieved. That's why we were satisfied.
Without any values, without any numbers, or
I can tell you the numbers right now.
So that was the model, and now time
I can
to
tell
show the
you
original
if it is 19% or 80% or more or less. But they were satisfied, and when they are satisfied, we are satisfied also.
Okay. Okay, thank you very much. Are there any other questions? I can't see, so feel free to ask. Yeah, okay.
Još jednom hvala, dobro bilo. Možda ste napravili simulaciju kod kojeg G-a bi se stup srušio, da znam kad idem u Rim na koje varne doline da treba da ga slikam.
Pa ne, nije, ali pitanje je sasvim u redu, mislim, ovako malo se šalim, ali pitanje je sasvim u redu zbog toga što te naše kolege, to je njihov posao, znači Institut za zemljotresno inženjerstvo stalno radi, pretežno su to europski projekti, kod nekih projekata ide do rušenja modela, ovdje to nije bilo predviđeno. Tako da, evo, ja ne mogu da kažem na kom G-u bi to bilo. Zbog toga što kod ovih 0,4 G je gotovo išlo do ograde. Znači, to je otprilike valjda bilo je nešto krajno, a da se ne sruši kao tako.
Dobro. Još samo komentar na one instrumente. Mi smo puno pravih ovih različitih testova, koji instrument ili kod monitoringa, kad imaš više instrumenta, šta ti je najvažnije? Da uvijek mjeriš sa istim instrumentom na istom mjestu. Dakle, može imaš 10 različitih instrumenta, ali uvijek treba upotrebljavati isti instrument na istom stajalištu. Ne? Tako ste vi to dobro napravili, da se to ne promijeni, jer onda dobiješ različite rezultate i to nije.
Budući da to nisu bili stupovi u laboratoriji, mi ne bi mogli garantirati da će instrumenti s optičkim viskom svakog puta biti postavljeni na isto mjesto. Zbog toga se instrumenti uopće nisu micali tokom čitavog testiranja koje je trajalo čitav dan, ali dobili smo ono što smo htjeli.
Okay, thank you very much. Any other questions? If no, then or yes, sorry.
Evo, hvala na zanimljivoj prezentaciji. Imam jedno pitanje možda. Kako ste vi došli do tog posla? Da li znate? Je li to bilo na vašu inicijativu ili su vam oni to ponudili sami?
Ovako, to je interesantna malo priča. To je naša sestrinska organizacija. Institut za zemljotresno inženjerstvo je ustanovljen nakon velikog skopskog zemljotresa 1963. godine i on je ustanovljen u zgradi Građevinskog fakulteta. tamo gdje je moj kabinet, bio je direktor Instituta za zemljotresno inženjerstvo. Tako da mi imamo stalne kontakte unutar univerziteta. A sad, kako da vam kažem, tako je došao posao, a što se tiče novca, bilo je jako malo. Znači, bilo je jako malo. Da. Zato je lijepa prezentacija.
Yeah. Okay, so that was our last question. Yes, and answer, of course, on the end. Okay, dear colleagues, let me close this technical session. Thank you for all our speakers for their presentations. Of course, applause. Yeah. And also, thank you very much for your kind attention. And now I would like to invite you to take some coffee. I need one. And see you back in the conference room at 5:45. Am I right? Yes, everything goes according to our plan, or not? Ante? What did I say? 5:45. 5:45. Okay. Thank you.
Dobar dan svima. Na početku tehničke sesije broj 4, geoinformacijska infrastruktura. U sklopu ove tehničke sesije imamo predviđena 2 rada. Prvi je od kolega Damjana Dolera i Nikola Šarlaha, informacijski sustav prostornog uređenja, te drugi Matija Mirtel i Milenko Kundit, moderne baze podataka za monitoring Red Line Metro. Nakon ta 2 predavanja, bez pauze, održat će se i drugo pozvano današnje predavanje koje će održati kolega Igor Grgac. Evo, znači, krećemo sa prvim predavanjem. Kolega Doler, izvolite.
Hvala. Ne radi baš ova miška. Evo jesam. Okay. Lijepi pozdrav. Moje ime je Damjan Doler i dolazim iz Slovenije. Radim na ministarstvu koje je kod nas zaduženo za prostorno uređenje i graditeljstvo. Inače, moja tema danas neće biti baš geodetska, tako da nadam se da ćete naći nešto zanimljivo. A ako poznajete vaš sistem e-dozvola, onda ćete moći malo uspoređivati i naći koji sistem je bolji, koji ima neke mane, pa možda ćemo kasnije o tome razgovarati. Inače je svrha ovog mojeg rada i rada kolege Nikota je ukratko opisati informacijski sustav prostornog uređenja koji smo razvili u Sloveniji, te ga na neki način usporediti s sličitim sustavima razvijenim u drugim zemaljama. U nastavku prezentacije ću koristiti kraticu PIS, što je kratica za naziv sustava na slovenskom jeziku, znači prostorski informacijski sistem. Današnji način života prisiljava nas svjesno ili nesvjesno na snažnu interakciju s digitalnim svijetom koji je postao dio našeg svakodnevnog života. Javna uprava, uključujući područje gradnje i prostornog uređenja, također se moralo suočiti s tom činjenicom. Digitalizacija javnih usluga trenutačno je prioritet u mnogim zemaljama. Svi su bili svjesni da samo učinkovita i inovativna javna uprava može građanima nuditi, pružiti brzo i visoko kvalitetnu uslugu. Razvoj digitalnih sustava koji bi u cjelini obuhvatio područje gradnje i prostornog uređenja jedno je od područja koje se razvija u većini zemlja Europske unije. Osnovni cilj takvog sustava je najprije ubrzati i unaprijediti procese izdavanja građevinske dozvole, onda unaprijediti procese prostornog planiranja i isto osigurati učinkovito upravljanje građevinskom zemljištu. To se sve može postići samo ako imamo pouzdane i lako dostupne skupove prostornih podataka, te ukoliko se uklone nepotrebne administrativne ovjere i omogući se elektroničko poslovanje. Naš sustav, znači sustav PIS, obuhvaća 4 glavna skupa digitalnih usluga. Kao prvi su elektroničke usluge za podršku aktivnostima s područja prostornog uređenja, takozvani podsustav e-plan. Onda su tu elektroničke usluge za podršku aktivnostima s područja gradnje, takozvani podsustav e-gradnja, isto za podršku aktivnostima iz područja upravljanja građevinskim zemljištem, takozvana evidencija građevinskih zemljišta ili kraće SZ, i onda na kraju podsustav za praćenje stanja prostora. Svi ti dijelovi sustava
su dostupni preko web portala, jedinstvena ulazna točka, kraće EVT. Sustav PIS obuhvaća sve razine procesa donošenja odluka, odnosno uključuje niz različitih sustava i registara koji su uključeni u različite procese i podprocese. Sa razvojem takvog sustava, kao što sam rekao, najprije smo htjeli omogućiti elektroničko poslovanje, onda ukloniti nepotrebne administrativne uvjere, smanjiti troškove investitora, uspostaviti zajedničku IT infrastrukturu koja uključuje međusobno povezane različite baze podataka, osigurati takozvani one-stop shop, znači sve informacije na jednom mjestu, i na kraju javnosti omogućiti dostup do svih donesenih prostornih i administrativnih, bilo to aktima ili odlukama. Pa pogledajmo najprije prvi podsustav e-plan. To je podsustav za podržavanje, taj podsustav podržava elektroničko poslovanje u pripremi, usvajanju, provedbi, primjeni državnih, regionalnih, isto i lokalnih prostornih planova. E-plan obuhvaća sve ključne dionike u tom području, znači uključeni su investitori, izrađivači prostornih plana, ministarstvo nadležno za prostorno uređenje, tijela prostornih uređenja i na kraju isto je uključena i javnost. Podsustav radi zajedno sa bazom prostornih planova gdje su pohranjeni svi podaci. Podaci su dostupni korisnicama, dostupni su im u mjeri koja im je određena u okviru e-plana. Baza prostornih planova čuva podatke o pravnom stanju na nekom području. U toj bazi su evidentirani državni prostorni planovi u pripremi, općinski prostorni planovi, isto se, mislim, još nije regionalna razina, znači nema još regionalnih planova, ali u teku je već jedan projekt sa kim će se i ta razina popuniti. Općine trenutno masovno pripremaju tehnički ažurirane prostorne planove. Pripremu tih podataka sufinancira ministarstvo u okviru jednog projekta Zeleni slovenski lokacijski okvir ili kraće 104D, možda ćete čuti za tu kraticu. Onda drugi podsustav e-gradnje. Taj podsustav je za elektroničko poslovanje u području gradnje. Podsustav podržava razne građevinske aktivnosti, znači sve od pripreme projektne dokumentacije, ishođenja posebnih uvjeta i uvjeta priključavanja od nadležnih tijela, cjelokupni administrativni dio ishođenja dozvola, znači sve od početka, od predaje zahtjeva, pripreme, izdavanja, dostave dozvola, skratka sve oko tog administrativnog dijela. Podsustav e-gradnja nadgrađuje podsustav za evidentiranje upravnih akta na području gradnje, takozvani PIS-UA 2. E-gradnja isto radi sa bazom podataka u gradnji zgrada. Isto kao e-plan, u e-gradnju obuhvaća sve ključne dionike na tom području, znači sve od investitora, projektanta, javnopravna tijela koja izdaju posebne uvjete, upravna i inšpekcijska tijela, ministarstvo i na kraju isto je uključena i javnost. Kao e-gradnja, isto kao e-plan su fleksibilni podsustavi i slijede principu modularnog sustava. Takav sustav uključuje manje zajedničke module koje se mogu lako promijeniti, zamijeniti ili ako treba čak i ukloniti. Razlog je u tome što se i zakonodavstvo koje definira postupke u oba podsustava često mijenja. Ne? Zbog toga da se može brzo sve promijeniti, takav je način tog sustava. Treća je evidencija građevinskih zemljišta. To je podsustav za evidentiranje i upravljanje građevinskim zemljištima. U evidenciji su osnovni podaci temeljem kojim je moguće planirati nova te regulirati postojeće građevinsko zemljište i na kraju može se i odrediti koji porez za građevinsko zemljište. SZ sadržava dva tipa podataka. Prvo su podatki o izgrađenom zemljištu, a drugi su podatki o neizgrađenom građevinskom zemljištu, koja su razvrstana u razredu prema njihovom razvojnom potencijalu. Evidenciju uspostavljaju i održavaju jedinice lokalne samouprave. Evidencija još nije popunjena. U sklopu projekta Zeleni slovenski lokacijski okvir ministarstvo sufinancira pripremu tih podataka i očekuje se da će biti evidencija popunjena do kraja 2026. To je evidencija koju puno se čeka na nju zbog toga jer je puno nekih novih podataka kojih bi već sad mnogi trebali, ali ih nema. Četvrti podsustav je za praćenje stanja prostora. Osmišljen je za praćenje ažurnog stanja i trendova u prostoru koji su rezultat prostornog uređenja, gradnje ili mjera zemljišne politike. Praćenje stanja prostora utvrđuje se korištenjem izvještaja i proučavanjem pokazatelja na osnovi kojih se vrednuje ostvaranje nekog cilja. Podsustav sadrži indikatore prostornog razvoja, infografike, bazu izvještaja, skratka sve što je potrebno za to da radi takav podsustav. Nešto malo u financijama. Održavanje takvog sustava u Sloveniji financira se iz državnih i EU fondova. Većino se neki razvoj financira iz EU fondova. Tako imamo trenutačno u tijeku taj projekt Zeleni slovenski lokacijski okvir. U okviru tog projekta fokusiramo se na dvije stvari. Prva je na informacijskoj razini, znači PIS ćemo integrirati sa povezanim sustavima. To su sustavi koji su na području voda, prirode i okoliša. A drugo je na razini podataka. Ključni dio dobrog funkcioniranja sustava je i uključivanje lokalne razine, što znači digitalizaciju baza podataka jedinica lokalnih samouprava i njihovo povezanost sa državnom razinom. Projektom 104D, znači Zeleni slovenski lokacijski okvir, financira se na toj razini podataka dva projekta. Prije sam već spominjao na njih. Znači prvi je usklađivanje prostornih planova s najnovijim grafičkim podacima katastra nekretnina. Podaci će se onda na kraju evidentirati u bazi prostornih planova, znači u e-planu, i priprema podataka evidencija građevinskih zemljišta. Znači to su oni podatki koji će popuniti evidenciju SZ. Na kraju još par riječi o informacijskim sustavima koje su razvijali države Europske unije. Prije svega treba napomenuti da je vrlo teško uspoređivati informacijske sustave, jer svaki sustav ima neku svoju logiku. Prvo smo provjerili kako su zemlje razvile sustav za potporu izdavanju građevinske dozvole. Građevinska dozvola je jedna od usluga javne uprave koje je Europska komisija definirala kao jednu od 20 javnih usluga koju treba svaka država članica EU obavezno nuditi u digitalnom obliku. Prema izvješću Digitalization in the Construction Sector proizlazi da je u većini europskih država omogućen postupak ishođenja građevinske dozvole elektroničkim putem. Valjda napomenuti da su neke zemlje više se fokusirale na informatizaciju i standardizaciju izrade projektne dokumentacije, poput Estonije, gdje su se više fokusirali na taj dio, druge su se više fokusirale na informatizaciju administrativnog dijela, znači podnošenje zahtjeva, vođenje postupka i izdavanje odluke, a treće su informatizirale cijeli proces, ne, poput Slovenije i Hrvatske, koje su se htjeli fokusirati oziroma informatizirati cijeli postupak izdavanja građevinske dozvole i pripreme dokumentacije. Kako bismo opravdali potrebna sredstva za uspostavu i održavanje sustava u Sloveniji, uspostavu sustava promatrali smo i s financijskog stajališta, usporedili smo resurse koje su neke zemlje upotrebile za uspostavu takvog sustava. Međutim, isto je tu malo teže napraviti takvu usporedbu, jer informacijski sustav pojedinih zemalja obuhvaća različita područja, ne, pa je malo teže uspoređivati, ali svejedno, analiza je pokazala da su zemlje dodijelile naravno sasvim različita financijska sredstva za uspostavu tih informacijskih sustava. Usporedba je možda relevantnija ako napravimo usporedbu po broju funkcionalnosti uključenih u sustav i broju stanovnika. Oni nam na neki način mogu predstavljati količinu posla ili možda opterećenje sistema. Na osnovi, to se vidi na donjoj tablici, na osnovi takvog pokazatelja usporedba je pokazala da je Estonija najviše uložila u razvoj informacijskog sustava, a najracionalniji su bili u Latviji. Slovenija je negdje na sredini, a za Hrvatsku baš nismo dobili svih podataka, tako da taj faktor nismo mogli izračunati. Za sam kraj, samo još par riječi. Kao što sam rekao na početku, današnji način života prisiljava nas na snažnu interakciju sa digitalnim svijetom i tome se trebamo svi prilagoditi. Uspostava digitalnog okruženja i uvođenja elektroničnog poslovanja je zahtjevan proces, ali kad govorimo u slučaju javne uprave, taj proces je i jako dugotrajan. U zemljama koje smo analizirali, za to su upotrebili 6 i više godina. Znači, treba si uzeti neko vrijeme za to da se uspostavi takav sustav. Na kraju možemo samo zaključiti da je uspostava digitalnog okruženja i upotreba digitalnih tehnologija na svim razinama prepoznata kao ključna u mnogim zemaljama i u tim zemaljama stvarno troše puno energije za to da se uspostavi i da se razvijaju takvi sistemi. Hvala. Ako ima kakvo pitanje, samo slobodno. A ako ne, ja ću biti sretan.
Ma, bit ćete vi sretni ovako i onako. Recite, molim vas, je li sustav e-gradnja u punoj funkciji za cijelo područje Republike Slovenije i ako je izmjerena brzina izdavanja građevinske dozvole, na primjer za običnu obiteljsku kuću ili možda malo složeniji projekt, prije ovog sustava i nakon njegovog puštanja u funkciju, kažite nam koji je to broj dana ili godina.
Na to zadnje će vam teško odgovoriti, ali od početka, ne? Kod nas je sa zakonom određeno na koji način i kako ide implementacija e-gradnje. Sad smo implementirali 3 območja. Tu bi mogli reći kako je sa vremenom prije na obični način i sad kad je e-gradnja. Inače ne se. A u cijeloj Sloveniji će biti sa 1.1.26. implementirana e-gradnja. A ako govorimo o e-planu, e-plan je već implementiran, a projektom koji će jedinice lokalne samouprave njihove planove uskladiti sa najnovijim podatkama katastra nekretnina, oni će isto dobiti neke nove planove, izradit će ih u standardima koji se zahtijevaju, ti će ići u e-plan. Znači i razini podataka će biti do srijede 26. Znači e-plan popunjen sa najnovijim podatkama. A isto drugo koje je isto jako važna je ta evidencija građevinskih zemljišta. Ta je jako, mislim da će biti interesantna i na području vrednovanja. Ti će podaci biti, kao što sam rekao prije, na kraju 26. Isto te podaci rade jedinice lokalne samouprave, onda ih šalje na državnu razinu gdje se na jedno mjesto onda prikupljaju.
Hvala. Evo još samo jedno pitanje. Zaboravio sam se predstaviti, Nikola Vučić, Državna geodetska uprava. Vezano uz ovaj projekt koji ste rekli SLO 4D, pa velite usklađivanje prostornih planova s najnovijim grafičkim podacima katastra nekretnina. Jel možete malo samo opisati kako je to usklađivanje prostornih planova i s kojim točno najnovijim podacima katastra nekretnina? Kako to mislite najnovije? Radite nove izmjere koje mi u Hrvatskoj ili?
Zbog čega se to radi? Prostorni planovi, stari prostorni planovi bili su rađeni na neki osnovi katastra nekretnina. Znači zbog toga da se može povezati nekretnina sa onim planiranim na tom području, tako možeš doći do vlasnika pa sve povezati sa njim. Onda se u jednom trenutku, vjerojatno znate za veliki projekt u Sloveniji sa kojim su nadgradili grafički dio zemljišnog katastra, onda sta ta dva slojeva sad bila malo pomaknuta. Sad nema baš tog presjeka između tih dva podatka, zbog toga treba te prostorne planove uskladiti novim podatkima o katastru nekretnina. Znači to će se pomaknuti tako gore. Onda su opet ti će biti u funkciji kao prije. Znači to je
sve jasno. Hvala vam puno. Samo još jedno vrlo kratko pitanje. Jel imate vi u Sloveniji ikakvih problema sa bespravnom gradnjom ili kod vas svi rade potpuno legalno?
Ne. Po jednoj analizi, jedan put smo, mislim ne baš sa nekom raziskavanjem ili bilo šta, da je vjerovatno negdje oko 70% gradnja nije, bilo da nema građevinske dozvole ili da nije izgrađeno u skladu sa građevinskom dozvolom.
Ali mene više zanima ovo novo, kad danas, da li se ljudi danas usude ići graditi bez građevinske ili ipak svi odu u ured za graditeljstvo i podignu,
Isto.
Ok.
Ipak smo na Balkanu.
Susjedi smo, ok, hvala. Hvala.
Je li ima još pitanje? Oprostite, jedno pitanje još od ovdje voditelja. A nas muči, barem mene muči ove tablice, pa nema podataka za Hrvatsku ovim usporedbama, pa me zanima zašto, jer ipak ste došli do podatka o financijama, znači koliko je koštao sustav, ali nemate ove druge podatke o funkcionalnosti, mislim, ne znam zašto ste istražili ili...
Istraživali smo, ali nismo dobili baš pravog podatka o tome, na tome je baš za Hrvatsko je radio kolega Nikolaj, tako da nemam ja baš pravog odgovora na to, ali nismo došli, nije zbog toga da ne bih htio kazati koliko je bilo to, mislim, novca potrošenog. Baš jučer su me upozorili na to da nije baš pametno govoriti o novcima, ali svejedno.
Dobro. Mislim, šteta da ostaje bez podataka za Hrvatsku, pa to malo ružno izgleda u tablici.
Ima li još pitanja? Nema. Da. Sljedeću prezentaciju pripremio nam je kolega Matija Mirtu. Matija.
Da se snađem. Gdje mi je miš? Čekaj. Znači, dobar dan svima, moje ime je Matija Mirtel, predstavit ću vam moderne baze podataka za monitoring koje su se koristili na Red Line metrou u Tel Avivu. Znači, Red Line metro u Tel Avivu. Mogu ovo već? Ne? Ovdje ja slabo vidim ovo. Znači, to je prva linija metroa u Tel Avivu. Nakon ove crvene linije će ići zelena linija. Duljine je ukupno 20 km, od toga je 10 km bilo podzemno. Ukupno je bilo 10 podzemnih stanica i 3 šahte iz koje su skretali TBM-ovi. Metoda iskopa tunela je 8 TBM-ova. Znači, ovdje na slikama vidite, na prve 3 slike su TBM-ovi, ovdje vidite jednu šahtu. Ima veliki broj objekata i zgrada u zoni utjecaja deformacija. Ukupno je postavljeno preko 10.000 mjernih senzora i sve to je išlo u bazu podataka Kronos, koju je razvila naša matična tvrtka Geodeta CT. Znači, moderne baze podataka se koriste kao one-stop station na projektima, omogućuje automatski manualni unos podataka kao dokumenata, zapisa i samih mjerenja. Imaju kompleksno grafičko sučelje sa raznim filterima mogućim, podatke o geometriji, objektima, geologiji, podatke o napretku izgradnje objekata i samih tunela, mjerne podatke svih senzora, omogućuju analizu normalno svih podataka, nude alarmiranje i izvještaje i prikupljaju real-time podatke TBM-a. Ovdje je struktura kako se to znači, unosilo u bazu. Bila su 4 izvođača, svaki je unosio svoje podatke u samu bazu i bilo je 8 TBM-ova koji svaki 60 sekundi slali podatke. U bazi je podijeljeni po ovim kolumnama geometrija, geotehnika, geologija, strukture, mašine kao TBM, monitoring, izgradnja, alarming i reporting i dokumenti, i to je izlazilo van preko same baze podatka Kronos Client, ili je išla na mobilnu aplikaciju Kronos Web, ili je išlo putem reporata ili izvještaja prema svima zainteresiranima. Ti su sami klijent, inženjeri na projektu, projektanti i tunelski stručnjaci. Ovaj sam pripremio mali video, čisto kao nekakav uvod, to video traje 2,5 minute, pa ću ga pustiti. Znači, sama duljina trase je nekakvih 12 km, sve stoje u jednom ekranu se sve vidi, znači nije rastjepkano. Različiti, znači, opcije zoomiranja i pomicanja, prikaz svih mjernih senzora, prikaz svih zgrada, prikaz samih tunela. Mogu se sačuvati različiti pogledi na zanimljive zgrade ili stanice, kako bi se olakšalo orijentacija u sustavu, pošto ima stvarno 10 km i preko 10.000 senzora. Postoje takozvani graduated simbol, odnosno krugovi koja veličina deformacija točaka odgovara je proporcionalna deformaciji. Postoje različiti filteri, ovdje se vidite, znači ovo su 3D mjerenja, bit će geotehnička mjerenja, bit će znači sami nivelman. Znači, kao što sam spomenuo, postoje različite opcije filtriranja, od vrste senzora, od pogleda na zgrade, na mape, na zgrade. Znači, tu je vizualizacija TBM-a sa njihovom pozicijom i također omogućuje nekakvu opciju analiza deformacija nakon samog TBM-a. Znači, ovo je pogled prema zgradama, znači za svaku zgradu su se unosile i dokumentacija prije izgradnje i dokumentacija za vrijeme izgradnje kada su se prijavljali ljudi i prijavljivali nekakve oštećenja ili pomake. I na kraju, znači na zgrade koje su nama bile crvenog rizika, znači da je bio rizik od urušavanja, svi mjerni senzori su postavljeni na samu zgradu, vizualizirani preko slike i zadnji podaci su se automatski uploadali i osvježavali na samim zgradama. Znači sad smo bili smo grafičko sučelje, ono se sastoji od katastarskih, topografskih mapa, geodetskih mjerenja. Zgrade imaju svoj položaj na mapi, imaju nekakav ID, imaju stupanj rizika. Stupanj rizika je prikazan u različitim bojama, od crvene koja je bila najvećeg rizika, do zelene gdje se nije očekivao nikakav rizik, zoni utjecaja deformacija. Vide se tuneli, podzemne stanice i šahte, status izgradnje, znači različite boje u samoj šahti prikazuju razinu iskopa unutar šahte, pozicije pilota i talpi, isto tako sa njihovim podacima, pozicije svih mjernih senzora sa vrijednostima, to su geodetski i geotehnički senzori, meteorološki, geofizički senzori, razina buke, razina vibracije. Vidi se zona utjecaja deformacije, to je ova plava linija koja ide oko stanice, položaj TBM-a i ringova u samom tunelu i kao što sam već rekao, postoje mogućnosti filtriranja da se svako od tih stvari prikaže ili makne sa grafičkog sučelja. Osim same grafičke sučelje omogućuje se ispod razine terena. Na ovoj slici, znači teren možete preprezati na bilo kojoj lokaciji na samom projektu i vidite šta se nalazi ispod njega i vidite pod broj 1 položaj tunela, vidite pod broj 2 razinu terena koja je dobivena iz nivelmanskih točaka, 3 je stanje iskopa, znači koliko je samo tlo iskopano u stanici, položaj talpi i pilota, same lokacije mjernih senzora, odnosno za dubinske senzore, inklinometre, ekstenziometre i njihovu dubinu. Monitoring zgrada, znači mjerenje geodetskim i geotehničkim instrumentima, za svaki objekt su upisani geometrijski podaci, tlocrt, visina, broj katova, upravitelji sa samim njihovim kontaktima, razina rizika svakog objekta, slike svakog objekta prije izgradnje, dokumenti i razni izvještaji ako je bilo nekakvih prigovora od samih stanara i mjerni senzori se, znači pokazuju se rezultati mjerenja automatski na samom objektu. Analiza podataka, znači senzori se mogu odabrati sa grafičkog sučelja ili iz predefiniranih grupa, vizualizacija deformacija, već smo pokazali graduated symbols, postoje drugi načini, znači to je 3D vektori, sa smjerom i duljinom linija proporcionalno deformacijama, moguće napraviti contour maps i napraviti presjeke tih kontura sa grafičkim prikazom. Ovdje vidite presjek iza jednog prolaza TBM-a sa deformacijama od cirka 12 mm. Normalno postoji i analiza podataka putem grafova, znači ili sa grafičkog sučelja ili grupa točaka, što je bilo ili jedan objekt, ili jedna zgrada, ili jedna stanica. Moguće na grafu prikazati više senzora. Ovdje je prikazano 3D mjerenje, nivelman, klinometar i razina vode. Također moguće prikazati i prolaz TBM-ova, odnosno izgradnju pilota ili talpi na samom grafu. Moguće su apsolutne i relativne deformacije prikazati i također prikaz alarma na grafovima. Alarmi, bilo je 4 vrste alarma, znači crveni alarm se definirao od strane projektanta, žuti je bio 60% vrijednosti od tog crvenog alarma, zeleni je bio 30% vrijednosti cirka i crni je bio 30% iznad predviđene vrijednosti. U trenutku crvenog se znao, znači action plan, šta se radi u tom trenutku. U trenutku crnog alarma sve staje i gleda se šta se napravilo krivo, odnosno ko je kriv, ili je projektant krivo izračunao, ili nisu materijali napravljeni dobro, ili izvođač nije napravio dobro i obično je to jako skup sport kad se sve stane. Alarmiranje, znači svi mjerni senzori imaju alarme, različiti korisnici primaju različite alarme, znači projekt menadžeri nisu primali zelene i žute alarme jer nije bilo smisla, nego su tek uključivali sa crvenim i crnim alarmima. Ja sam ih primao nažalost sve. Postoje znači, vrijednostni alarmi, to sam prikazao zeleni, žuti, crveni, crni, postoje frekvencijski alarmi, da li je točka dovoljno puta izmjerena sukladno monitoring planu, postoje i rate alarms, odnosno prirast mjerenja i postoje out of range alarms, to su znači, mjerenja koja su nemoguća, znači ne može točka se pomaknuti 4, 5, 6 metara, nego je nekakva očita gruba greška i to se slalo odmah izvođačima da oni provjere te točke. Prikaz alarma na grafičkom sučelju, znači u samom grafičkom sučelju je bio prikazan kod crveni trokutić, ako je crveni alarm, sa zadnjim vrijednostima mjerenja i samim vrijednostima koja su čitana na toj točci. Znači, alarmi se mogu slati SMS-om ili e-mailom, obično ljudi biraju e-mail jer je lakše. Ovdje je prikaz jednog maila koji je poslan, tu je bio load cells, gdje su prošli limit koji je bio zadan od strane projektanta. Osim alarma, znači, postoje razni izvještaji postoje za sve ugrađene mjerne senzore, postoje, znači, kao što vidite na ovim izvještajima, grafički prikaz same lokacije senzora, opet je moguće apsolutne ili relativne deformacije, unos različitih napomena i komentara, točka je uništena, točka je oštećena, itd. Vizualizacija graničnih vrijednosti alarma, to sam vam prikazao na onom grafu, za podzemne senzore i prikaz geologije, znači to vidite ovdje na ovim inklinometrima, su različite razine tla, ovisno o dubini. Postoje plan view reports gdje se cijela stanica prikazuje sa svim mjernim senzorima i na kojima se vidi njihove zadnje vrijednosti. Postoje TBM reports i nekakvi custom reports kada više senzora se kombinira u jedan izvještaj i to se može poslati. Znači, najčešće recimo geodetski to bio nivelman i 3D mjerenja. Osim ovih izvještaja postoje automatski izvještaj, znači rade se automatski zadaci koji šalju izvještaje prema korisnicima. Broj mjernih senzora izvještajima nije ograničen, također ni broj veličine izvještaja nije ograničena. Može se postaviti bilo koja frekvencija slanja izvještaja, za neke stvari je bilo jedanput tjedno, za neke stvari je bilo 3 puta dnevno ili više. Šalje se na email korisnika, šalje se kao link i vi možete doslovno kliknuti na bilo koji izvještaj vas zanima ili skinuti sve i šalje se normalno 24/7. Kao što sam rekao, znači gradilo se sa 8 TBM-ova, su se gradili tuneli, automatski se učitavalo preko 200 parametra, mislim da ih je bilo 234. Za svaki parametar je moguće napraviti grafove i također je moguće postaviti alarme. Vizualizaciju TBM-a na grafičkom sučelju ste već vidjeli, također vizualizaciju ringova i postoji izrada reporta sa napretkom TBM-a i postavljenim ringovima, znači to je obično išlo projektnim menadžerima ili šefovima gdje su oni vidjeli svaki dan koliko ti TBM-ovi napreduju. Na projektu je radilo preko 100 korisnika, postoji 5 osnovnih uloga koji imaju različita dopuštenja, sami broj uloga nije ograničen, tu postoji, mislim da ima 100-tinjak dopuštenja koje je moguće dati bilo kojoj ulozi ili tako je moguće zabraniti neke stvari, recimo brisanje mjerenja, ponovni upload mjerenja. Mi smo imali ljude koji su samo se bavili dokumentacijom, koji su samo imali dopuštenje za unos dokumenata u samu bazu. Također moguće staviti geografski da, znači jedan čovjek koji radi na jednoj bazi ima samo pristup točkama sa te baze ili recimo znači pošto je projekt bio podijeljen na 4 segmenta, da čovjek ima pristup samo jednom segmentu na kojem radi. Zaključak, znači to je risk management, project management tool, centralna baza podataka sa svim dostupnim podacima projekta. Koristi se obično prije početka gradnje za nekakva nulta mjerenja, unos dokumenata o zgradi, meteorološka mjerenja, za vrijeme izgradnje, znači sigurnost ljudi, objekata, zgrada, infrastrukture trećih strana, samu kontrolu kvalitete projekta izvođača ugrađenih materijala, također u slučaju zahtjeva trećih strana za monitoringom ili odštetama. Te se koristi nakon izgradnje do stabilizacije mjerenja, te analize i deformacija parametra za buduće projekte. Znači, kada će ići nova linija TBM-a, nova linija metroa, znači podaci skupljeni sa ovog projekta će se analizirati i koristiti za daljnju analizu za novu zelenu liniju. I dopušta inženjerima da na osnovu stvarnih podataka i stvarnih mjerenja, znači koje nisu predviđene, donose odluke 24/7. Evo, hvala vam.
Hvala Matija na zanimljivom predavanju. Ima li pitanja? Evo onda ću ja malo postaviti prvo pitanje. Ovaj projekt je predstavljao dosta veliki projekt. Kolika je bila lokacija?
Znači 10 km i 10 podzemnih stanica.
Jeste li imali projekte gdje ste uspostavljali baze podataka za neka područja, za gradilišta koja pokriva manje područje i gdje su svi ovi korisnici baze podataka de facto doslovno u kontejneru jednom pored drugoga i iznad?
Znači najmanji projekt na kojem smo mi radili je bilo u Americi, znači tamo je bio projekt u LA-u gdje se mjerila autocesta, duljina tunela ispod autoceste je bila cirka 110 metara, gdje su kalifornijske autoceste zahtijevali monitoring kao treća strana i zahtijevali su bazu podataka Kronos.
A situacija u Hrvatskoj?
Situaciju u Hrvatskoj bilo je pokušaja, bilo je pregovora, ali za sada nismo još uspjeli. Mi se nadamo da će se graditi metro u Zagrebu i da će biti prilike i za nas. Evo.
A po vama, od svih onih korisnika te baze podataka, ko najviše inzistira da jedna takva baza podataka prati izgradnju? Proces izgradnji?
Znači, uglavnom su to ili investitori, ali na kraju to se vrti novac. U zadnje vrijeme osiguravajuće kuće zahtijevaju baze podataka za monitoring kako bi uopće osigurale projekte i dale novce. To je, evo, u zadnje vrijeme.
Imamo li kakvih pitanja na chatu? Ima li pitanja iz publike?
Može i komentari. Morate na mikrofon.
Ma ne.
Koliko ste i u Karlovcu prije ovog, kad su počeli puštati?
Aha, i na Zvijezdi, a? Evo, nek nas zovu rado.
Evo, imam ja jedno kratko pitanje, Matija, vezano u sami software. Znači, ako sam dobro shvatio, software je vaš proizvod kao tvrtke.
Dobro.
Da li prodajete software? Recimo da neko sad dođe i kaže ja hoću kupiti samo Kronos software. Ili ne?
Ne. Znači, obično to uključuje i administratora koji prati taj software, jer stvarno je kompleksan, napredne su mogućnosti i obično treba neko ko ima iskustva s time da dođe i postavi cijeli sustav, ili iza softvera i dalje stoji jako puno rada.
Hvala.
Ako nema pitanja, ja bih se zahvalio Matiji na zanimljivom predavanju.
Hvala.
Sada nastavljamo prema programu sa pozvanim predavanjem broj 2. Sa velikim zadovoljstvom pozivam Igora Grkca da nam održi predavanje o lokata sustavu. Igore, izvolite.
Dobar dan svima. Hvala na pozivu za predavanje. Mikrofon zaboravio sam. Hvala na pozivu za predavanje. Čast mi je da mogu predstavljati tvrtku za koju radim, znači Lokata, firma za koju radim kao navigacijski inženjer u zadnjih 2,5 godine. I danas ću predstaviti sustav na kojem mi radimo. Znači sustav se zove Lokata, to je terenski sustav pozicioniranja pomoću radionavigacijskih valova koji služi kao nadopuna GNSS-u ili za pozicioniranje navigacije, ali isto tako za sinkronizaciju vremena. Ne znam, je li bolje da držim na hrvatskom ili na engleskom? Bolje budem, ja ću pričati dalje na engleskom, čisto iz razloga šta tav dio koji radimo sve na engleskom i dalje na prezentaciji, nisam nikad pričao o tome na hrvatskom, pa će biti vjerojatno jednostavnije pričati na engleskom, pa ću se samo prebaciti da znate. So for the start, this is the outline of the presentation, what I will talk about today. So first, I will talk about complementary or alternative PNT in general, what it is and why is it important today. After that, I will talk about our system that we developed, so locator positioning system. I will say a little bit just in theory how it works, what it is, and some of the biggest achievements that we made and that are different to everybody else, what everybody else is doing. After that, I will talk about the results of the testing that Department for the Defense Industry and Space of the European Commission did for the alternative positioning, navigation, and timing. So they did some tests for different technologies in the world. So different companies from all around the world could apply for that. And they basically, what they did, they make the test and then they publish the results. The final goal is to see what would be the direction in which the European Union would go in the case when they will need the alternative PNT. And in the end, I will finish with just a couple of examples of the networks that we established around the world, just 2 examples to make it shorter. So in general, PNT is positioning, navigation, and timing service. And the most recognizable PNT service today is GNSS, so different GNSS constellations. And they have some problems because they could have potential problems because they have low signal strength. So GNSS satellites are on great altitudes, on 20,000 kilometers from the Earth, and so they have low signal power. And because of that, they are prone to or vulnerable for the intentional or unintentional disruptions of the signals. So for the signal jamming and signal spoofing. And in the last few years, both all around the world, the terms alternative and complementary PNT started to become a thing. People are starting to talk about it, and that's why in different parts of the world they are looking for some solutions to have some backup in the case if something will happen to the GNSS, if the signals are jammed or spoofed. So generally, this complementary or alternative PNT, there's like these 2 terms. Alternative PNT is generally used in Europe. EU use term alternative PNT, and in the US, in America, they are using complementary PNT. But it's basically the same thing. So it's positioning technology that will deliver positioning, navigation, and/or timing, at least one of those 2, independently of GNSS, so that in the case of the disruption of GNSS signals, they can act as a backup. And then optionally, they should enable some extended capabilities compared to the GNSS. So like to work in the indoors or to work in some areas where GNSS is not working, or for some stuff that GNSS is just not applicable. So in the world, there are different solutions for the alternative PNTs. So one of the things that they're doing a lot of research of is using signals from the low Earth orbit satellites. Those are mostly the telecom satellites designed for telecommunications, and they're just trying to use those signals which are not designed for positioning. They're trying to use those to get some position and time synchronization. for some stuff. Other thing that's heavily researched and used is using fiber optic cables for time synchronization only. So connecting 2 points with the optical cable and with some devices, do some calculations, some stuff, some measurements, and you can very precisely time synchronize to the two devices on the different locations if they are connected with a fiber optic cable. Another thing is map matching and IMUs, combination of those. In the case when the GNSS is not available, this is only used for navigation. Also, there are different kind of terrestrial radio positioning systems and technologies. This is where our technology is also in this category. So we are terrestrial radio positioning system. And in the end, there is something that's called signals of opportunity. That's basically using all available signals that you have in the space wherever you are. So basically you're using LTE, so LTE signals, that's for cell towers. Then you use Wi-Fi, you use all kind of radio and everything else, which is not signals that are not designed for positioning, and you try to combine all of that and try to have some, to do some like calculation stuff, filtering, and get the position and timing from those signals. Why is it important? Well, in the US, the Department of Transportation, they are in charge for the complementary PNT in the States. They did some analysis and they have 18 categories of critical infrastructure. So in the US, and in analysis, they did that 17 out of these 18 infrastructures are dependable on GNSS. And if you cut off GNSS completely, GPS in America or in Europe is Galileo. If you cut it off completely, then you will basically have a problem in 17 out of 18 critical infrastructure areas. So here are some of them are in transport infrastructures. That's basically mostly transported goods, so shipping and traveling by planes. They're all dependent on GPS, even cars and everything else. But besides this transportation, which is dependable on position and navigation, a lot of other stuff is heavily dependable on the timing component of the GNSS, of the PNT. So the timing stuff is even more important than position itself. So even like energy supply networks that are dependable on GPS, GNSS signals, because you need synchronize different part of the networks. Telecommunications, so cell towers also needs to be synchronized. Otherwise, when you switch from one cell tower to the other, if they're not synchronized, you will just lose signals. You cannot continuously tracking signals. And how they do synchronization is actually they are synchronized to satellites, to GNSS. Also financial networks. So today, most of the stock market is done by computers, by bots, not by people. And it's very important to know exact precise moment when some stock is bought or sold. So it's very important to have all these networks to be time synchronized very precisely. And there is many more. Other than that, here are some just statistics, some benefits of GNSS. So there is, by the EU, when they did this report, they did some research, and there is some estimate that in the period from 1999 to 2027, there will be socioeconomic benefits of the GNSS in the range of up to 2 trillion euros. And there is, in this period as well, there is 100,000 highly skilled jobs. That's engineers and scientists and others that are employed just because of the GNSS. And there is another stat is that if GNSS was completely cut off, there will be losses of up to 1 billion euros per day, directly or indirectly. I will now just show a few examples because of this recent situations with the wars in the world. There is a lot of increase of jamming and spoofing of GNSS signals in the war zones. So there is some research that they did and make an estimate that Ukraine is losing around 10,000 drones per month just because of the GNSS spoofing. So next is this is in Israel. You know, there is a war. Israel is actually using spoofing of GNSS GPS signals actually, and when they anticipate that enemy will attack them, you know, they turn on the spoofing, and this is the map where they did research of where in the world is happening most of the spoofing and how strong it is. And this yellow part is actually Israel, and they're just trying to disrupt the signal so that the missiles doesn't hit the target that it's supposed to hit. But this also have impacts on the commercial use, on economics and other stuff. So spoofing the GPS signal spoofs everything, so they have problem with the planes and the ships. And this is one example. This is for the air. Finland air company, Finnair, have a flight from Helsinki to Tartu in Estonia, and they were flying from Helsinki to Tartu, and there was GPS jamming and spoofing happening, and they need to turn around and go back to Helsinki. So this is the route that they did started to landing, and they saw that they had a problem because of the GPS jamming, so they decided that the best thing is to turn around. This is a very small airport, so they didn't have backup system that's used for the automated landing. So that's why they decided that the best thing would be to go back rather than try to land. And all of this is the reason why in the world today, the alternative PNT or complementary PNT is starting to become a thing. So Europe is, as I said, I will show results from what we did in the Europe for in this project where Department for Defense Industry and Space of the European Commission did the analysis or assessment of the alternative positioning navigation systems that are available in the world, and to see what's potential for their deployment across the EU. Besides that, US is doing similar thing. They're doing the tests of complementary PNT. Their Department of Transportation's issued an action plan for that, and the testing for that should occur in the end of this year and beginning next year. And plan is for the US at least by the end of 2026 to have some plan to how to achieve backup in the States. Europe did a report, but they're still waiting to decide what to do next, what technology to use in and which way. That's for the intro about complementary or alternative PNT. Now I'll talk what we are doing as Locata. So we are basically from the start, from the beginning, goal of the company was to develop this real-time positioning system to be complementary to GNSS or that it can work independently, to work both indoors and outdoor, and to be able to give centimeter level positioning. So that was the goal from the start, and it's almost by definition this alternative and complementary PNT that they are talking about today. And we started doing, well, not me personally, but they started doing it on it in the late 90s and early 2000s. The concept was to use a network of ground transmitters. We call them locklights, Locata lights, locklights. And that they transmit signals that's similar to GPS that then enables positioning within this network. For that, main challenges, two of the main were at first time synchronization. Actually, time synchronization was the initial idea, and with time synchronization was came together with the idea to make it positioning system than to use time synchronization for terrestrial positioning system. And after that, the biggest challenge was multipath, and then it was a little bit solved. So I'll show briefly how it works. So for time synchronization, for start, GNSS or any GPS, they're having atomic clocks. Now, there is no any clock in the world that's perfect. So each clock have errors, but clocks don't have just noise. They also drift with time. Even the most precise atomic clock will drift. Even the clocks in GPS, they drift over time. So if you left satellites, GPS or any GNSS to just go around and you don't correct the clocks, then they will drift apart and you wouldn't be able to get positioning. And the way the GNSS solves that is to have ground control networks, and then they collect observations from satellites, calculates the corrections, send it to satellites, and then satellites corrects its clock. And this happens every few hours for the GNSS. And what we do, we actually have this time lock technology that is developed by Locata and patented, which enables wireless time synchronization directly between signal transmitters with sub-nanosecond level of accuracy. And we can do that without any atomic clock, so it's enough to have just the regular crystal oscillator clock, which is the clock that's used even in GNSS receivers. So any GNSS receiver have some clock. And we can do that completely independent of GNSS, so we don't need any signal from anywhere from GNSS or clock or anything. And we don't need any external correction. So it's directly just two transmitters, and they communicate in some way and wirelessly, and they synchronize each other. And that enabled positioning with the terrestrial system. The second problem was multipath, because that's when you have terrestrial system, then all of your signals are coming from very low elevation angles. So you're basically going to have sometimes negative elevation angles. If platform is tilted, then relatively signals come from negative elevations. And in GNSS, you can simply most of these low elevation signals, you get rid of them just because of the multipath and the diffraction. And here we cannot do that, because if everything is at these low elevations. So we are using different stuff to mitigate multipath. It's not possible to completely, eliminate multipath, but you can deal with it, improve it. So first thing is that we were using different antennas depending on which situation you are in. So basically, if you are doing something indoors, if you're putting antenna in the corner, local light in the corner, then you will put cube antenna that has around 90 degrees radiation pattern, and that way you'll let's say lower the direct multipath from the walls behind the antenna. And if you put it on the wall, you will use something that has some around 180 degrees radiation pattern, and so on. Other thing that we are using is what is shown to be very helpful was to using two transmitting antennas. So from one transmitter, one local light, we transmitting signals from two separated antennas. So if you use antennas with separation of 1 to 2 meters, it can help a lot, because on those two signals from the different antennas, multipath will affect them slightly different. And then from that, you can understand that multipath is there and eliminate that measurements out. But again, you cannot, it's hard to define which signals has multiple, because both of them look like they're just diverging from one another. So it helps, but for the indoors, it wouldn't be enough just to use this for the positioning. So for the heavily multipath affected areas, we are using this technology that we also developed in-house. So to solve for multipath, we developed this V-Ray technology for the rover antenna. This is phased array antenna technology. So it is orb antenna on the right, that's just one antenna, and each of these green squares on it, it's actually one small patch antenna. So this element, this antenna's whole consists of 60 elements, And each of these elements works like for a very briefly period of time. It's always just one element is receiving signals. And from that, then it's possible to do something that we are calling beamforming. It's basically from all of these measurements, you are looking just at the stuff that's coming from the direction where we're expecting to receive signals. And in that way, you can basically solve the multipath even in the indoor areas, in the metal sheds and wherever, almost anywhere. And this is what enables us positioning indoors and in heavy environments with high multipath influence. And another thing about technology is what frequency do we use. So for the prototype, when they started in the early 2000s, first device was actually like just they took the GPS receiver and they hacked it and make some changes in it to make it to be a transmitter, not receiver. And so the first device's prototype was using GPS frequency, LEN frequency, but the problem is that it's restricted. You're not allowed to transmit at that frequency, and if you do, it's only for the scientific purposes and very low power levels. So in the commercial use, for the commercial device, we switched to 2.4 gigahertz ISM band. This is industrial, scientific, and medical band, and this is license free. So you are allowed to transmit signals on that frequency, within that band, any frequency within that band without any special permissions. There's only some restriction on the power levels, depending on which part of the world you are. Different transmitting powers are allowed. So in the Europe, that's 100 milliwatts. In the Australia, it's 200, and in the US, it's 1,000 milliwatts. And this is basically the signals that are used by Bluetooth or Wi-Fi, and it's the same frequency. So the signals that we are using are basically just like Wi-Fi signals that are anywhere around us. In this band, this is very narrow band, where it's around 100 megahertz, a little less, and we are using two frequencies within that band. So basically, we are having 4 signals total. I said that we have 2 separated antennas and 2 frequencies. That's 4 signals for each transmitter. And the problem is that we are not able, because of these 2 frequencies, we are not using wide and narrow lane combinations, because it's just that we don't have enough diversity. So wavelengths are almost the same, just 3 millimeter difference between the 2 signals. But we are using it more also for the multipath, because when you have different frequencies, the multipath will behave slightly different, and this can help also to mitigate multipath problems. So it's more for that than what it is used in GNSS, this dual frequency. And having license-free band, transmitting in that band is good because you don't have any permission, but it's bad because anybody else also doesn't need any permission to transmit in that band. So there is a lot of signals in that band, and there is a lot of interference. So when we're designing a network or something, we need to check the area for the Wi-Fi signals. And if there is something and needs to stay on 2.4 gigahertz Wi-Fi, then we are basically what we are doing is changing the channels that Wi-Fi are transmitted and changing our transmitting frequencies so that they don't overlap, and use some filters to filter out Wi-Fi signals completely. And this is one of our customers, said like quote of our customer is that for GPS, that it's like a Swiss cheese, like it's full of holes. They was like using GNSS for different projects, and it's great when it works, but in some cases when it doesn't, then there's nothing you can do about it. So it doesn't work indoors. You have a problem in harsh multipath environments, in areas where you have lack of visibility to the sky, like deep mines. We have a problem if there is a jamming or spoofing of the signals. And we are located here actually to fill in this hole. So where GNSS doesn't work, we are here to cover these spots. And now I will switch to the testings and demo that we did for the EU. So DEFIS, that's shortened for Department of Defense and Defense Industry and Space of the European Commission, and they were assessing these different alternative and complement alternative, they call it alternative PNT technologies. And what they were looking for, companies around the world that can do any kind of alternative positioning or timing, and they wanted to test those technologies that exist. So they wanted indoor, outdoor, static and kinematic positioning, so anything of that or all of that. And for time synchronization, they wanted synchronization between two receivers and also holdover. Holdover would be when GNSS is off, then how long you can keep the time within some bounds. So how accurate you can keep time. So basically holdover would be how good is your atomic clock on the ground. And time synchronization is transfer of time from point A to point B. And for the whole tender, there was for positioning and timing, there were only 3 companies. So along us, there was a company called Satellis, which does LEO satellites technology, so low Earth orbit satellites. They're using telecom signals from telecom satellites to do positioning and timing, trying to do. And there was also a company called NextNow. Both of those are from the United States, and they're doing also terrestrial radio positioning system, but they're doing it completely different than us. They're using atomic clocks in each transmitter, and they're not using phase measurement, but only codes, and they're using specific their own proprietary frequency to transmit signal and use very high power level, and use case for their technologies to actually for detecting people in the emergency situations. So when you call 911 or 112 in Europe, then for them to be able to locate you, within which building you are and which floor and everything, which apartment, that's not possible today with GNSS or detect mobile phone. And they're trying to develop system that would then eventually come to the mobile phone that they can actually detect where you are when you call emergency situation. But that's very hard to do. And there was also four other companies that did only timing. So they mostly do the timing with the optical fiber optics. Almost all tests were done in the JRC, in the Joint Research Center in Ispra, Italy. That's the biggest research facility in the Europe. And DEFIS department has their laboratories there, and that's where they did this testing. Over there, I will first go with talk about timing, what we did with timing, and then after that, positioning, which is probably more interesting to you. So for timing, we did different time transfers. So we did like most simple thing to do would be to have two receivers and be in here in closed room, and from receiver A transfer time to receiver B, and then connect these devices to something that's called time interval counter, and measuring what's the difference between those two devices, what difference in time between those two devices. We do that indoor. And after that, we did it also with the cables, so directly connect one device to the other with the coax cable. So you don't have antenna, but directly transmit transfer the time. The problem is that with a lot of cables, you have a very, very strong power of the signals goes down very quickly. So you are not able to go to the longer distances. So maybe for 100 meters, that would be okay, or couple hundred, and that's it for the coax cable. But you can also do it with fiber optics cable. So there you don't have like range limit. So as long the optic cable is, you can transfer time as far as you want. So 1, 2, 3, 5 kilometers, it doesn't matter. Just like internet today in the home, it's go through optic cables from the station, and it doesn't have like any limits in the distance. And the harder part is this over the air, because you don't have controlled conditions like in cable. So over the air is the toughest part. And we did over the air this inside the room. We also did from inside to outside through the wall. So the signal travels through the wall. And we also did outdoor time transfer, which is We did it on the local area that's within this test facility, so within GRC test facility, and we also did the outdoor wide area, because for this timing, the point is for them to find something that can synchronize time across the country or across the Europe or something like that, so that they have backup in the case of GNSS fails. So we also did like big time transfer outdoor of the test facility. This is the test facility of the GRC. So here on the bottom, GRC1 and GRC2 transmitters, they're on the top of the building where GRC lab is located. And in the lab, there was like this time interval counter that was measuring the difference between this GRC1 and GRC2 locator lights. So we had 2 locator lights in the lab, antennas positioned on the top of the building. And then we did time transfers. So for the outdoor, we first wanted to go to this building, which is called workshop. In this building, we did actually indoor demos. So we wanted to have this indoor positioning network. So in this building, we set up the network for the indoor positioning, and we wanted that to be time synchronized to the time that they gave us. So they gave us feed of PPS of the Galileo time, and we then time synchronize, like make the hops of the time through these receivers. So the first local area time transfer was from GRC1 to this workshop. And then there is a big tower in the GRC. We time transfer there. This is picture on the right. There are these 2 antennas actually are parabolic dish antennas. This is what we used for these greater distances. And then we get back to the workshop. There are another local light. So basically there were 2 local lights in front of workshop and building, and then back to the starting point. So we basically did 4 hops of time. And we then keep this time synchronization for 24 hours, and they measure the distance, and later I will show the results. And besides that, we also did wide area time synchronization. So this is outside of the GRC building. This is something that they didn't require us to do. They didn't even ask for that, but we wanted to do that, because this is showing like true applicability of this system for the time synchronization on greater distances on bigger scale. So here, what we did is we make a time transfer for 8 kilometers over the lake to the Massino Visconti, and then another 34 kilometers to the Como, and then back. So total signal travel was 105 kilometers. Just for reference, that's from here to Austria, or from here to Plitvice Lakes, and that's the distance of 105 kilometers. And we did that with the signal power of just 100 milliwatts. That's basically what you are allowed to set the power of your Wi-Fi router. We managed that because we can track the signals at very low power levels, and also we used these parabolic dish antennas, which have very narrow radiation pattern, and they're directional, so you need to direct them pretty good. So this is the antenna that we use, and this is the distance that the signal traveled from the GRC to the Massino Visconti. So that's 8 kilometers, and then we slide it to the left of the GRCs, and 44 kilometers further away is Como. And this is the results that we get at first. Even we were surprised with the numbers that we get at this first initial, when we did the first initial run, because we get like less than 100 picoseconds. I don't know, doesn't mean a lot when you're not in timing, but later when I get to the whole results of the timing demo for all of us, then you'll see why we were surprised with these 65 picoseconds. But it's not always that you will get 65 over the air, and especially on that distance. This graph over here, this bottom noisy graph, is actually time difference between Galileo time and atomic clock. So this is actually during the period of time holdover. So actually our locator light GRC1, first starting one, can be time synchronized to external source. So let's say to Galileo time, which is basically perfect. And we consider that as truth time. And it's also connected to the atomic clock. And then when you quit the connection to the Galileo time, plug it out, then you are in holdover mode when your atomic clock is holding the time. And this graph, this middle one, but bottom noisy one, is actually difference between the Galileo and the time of the atomic clock over the period of 24 hours. I don't know, you can see the scale, but basically in 24 hours, atomic clock, this is cheaper atomic clock, rubidium atomic clock, and it drifted for 200 nanoseconds over the 1 day. And on the top is this difference between the Galileo time and the time that we had at GRC2. So after this 105 kilometers at 8 hops, we time synchronize all of that, and then we get this top graph. And when you compare them, they are basically not basic, but they are the same. This bottom graph is just a line that's different between those two in the same scale. Of course, it's not perfect. When you zoom it in, you get some noise. So this is what you get when you zoom in. So peak-to-peak noise that we achieved was 700 picoseconds, 0.7 of a nanosecond, and it's stable all across 24 hours. What's also important here is that signal travels through atmosphere, and atmosphere change, temperature change, everything changes, and you have corrections for the atmosphere, and technology that we built for time synchronization is actually takes into account, can basically cancel out the influence of the tropospheric changes, and basically we don't have any effect of the troposphere, and then in the end, we can then calculate what would be the tropospheric correction along this whole path. And in this period of 24 hours, we had total peak-to-peak difference of tropospheric corrections of 80 centimeters. 80 centimeters, yes, I said it right. And peak-to-peak noise that we had was around 20 centimeters. So this 0.7 of a nanosecond, when you recalculate that into distance, that's 20 centimeters. So we can basically determine tropospheric delay from our measurements of the time. And we also did this, as I said, from the outdoors to indoors, so through the wall, and there is a bookshelf or something at the wall, so signal was going through that, and it's all the delays that happens because of troposphere. When you go with signal through the wall, you get even bigger tropospheric delay, the delay for going through the wall. So that's all canceled out with the technology that we are doing. And these are the final results. Highlighted is our results. This is for timing. So first two columns are for the time for the holdover. So this is basically, first two columns are how good is your atomic clock when you turn off the Galileo or GNSS. So this is something that we don't do usually. I mean, it's not our technology. We don't do atomic clocks. We are doing time synchronization. So we just did this test. You can see with a very cheap atomic clock, and we achieved what was 200 nanosecond was the drift over the period of 24 hours. So that's why we have only 1 day and errors up to 1000